Hello and welcome to this full course on machine learning by Intellipaat. If you're aiming for a career in data science, artificial intelligence or a data analyst, you're already looking at some of the most in-demand jobs of 21st century. In fact, according to Forbes, job posting in data science and AI have grown over 650% since 2012. Now here's the truth. Machine learning sits right at the heart of all these roles. It's the common skill that every data-driven job demands. But this is also the point where many beginners face difficulties. If you have ever faced a technical interview for a data role, you probably know what I mean. The challenge is that machine learning is a vast field filled with layers of concept and mathematical foundation that need deep understanding. That's exactly why it can feel overwhelming. But don't worry, we have got your back. In this course, we are not just going to throw theory at you. We will walk through the core concepts that real interviewers focus on, based on insight from thousands of learners who have gone through actual interview experiences. You will gain a clear understanding of what to expect, how to think about problems, and how to explain your reasonings like a pro. So grab your notebook and pen, get ready to take notes, ask questions, and build confidence for your next big opportunity. Without wasting any time, let's get started with the very first topic on our list.
Machine learning was just considered to be just a niche subfield of computer science, but technology giants have been using it for years. Machine learning algorithms power Walmart product recommendations, search pricing at Uber, fraud detection at top financial institutions, content that Twitter, LinkedIn, Facebook, and Twitter display on social media feeds or Google Maps. Machine learning products are being used daily, perhaps without any realization. A report from TMR mentions that machine learning is expected to grow from $1.07 billion in 2016 to $19.9 billion by the end of 2025. Machine learning is a branch of artificial intelligence and computer science, which focuses on the use of data and algorithms to imitate the way the human learn and hence gradually improves the accuracy. How machine learning works? Step 1. A decision process. In general, machine learning algorithms are used to make a prediction or classification. Based on some input data, which can be labeled or unlabeled, your algorithm will produce an estimate about a pattern in the data. Step 2. An error function. An error function serves to evaluate the prediction of the model. If there are known examples, an error function can make a comparison to assess the accuracy of the model. Step 3. A model optimization process. If the model can fit better to the data points in the training set, then weights are adjusted to reduce the disparity between the known examples and the model estimate. There are three methods of machine learning. First one is supervised learning. In this type of learning, algorithms build a mathematical model of a set of data that contains both the input and the desired outputs. The data is known as training data and consists of set of training examples. Each training example has one or more inputs and the desired output, also known as supervisory signal. Second method is called unsupervised learning. This method of learning algorithm take a set of data that contains only inputs and find structure in the data, like grouping or clustering of data points. The algorithms therefore learn from test data that has not been labeled, classified, or categorized. Instead of responding to feedback, unsupervised learning algorithms identify commonalities in the data and react based on the presence or absence of such commonalities in each new piece of data. Third type of learning is called as semi-supervised learning. This falls between unsupervised learning and supervised learning. During training, it uses smaller labeled dataset to guide classifications and features extraction from a larger and unlabeled datasets. Machine learning is used in day-to-day life, like speech recognition, customer service, computer vision, automated stock trading, discovering data trends, and lot more.
I went through hundreds of courses, watched countless tutorials, and compared the most popular learning paths for machine learning. And you know what I found? Everyone says something different. Some tell you to start with Python, others throw complex math at you right away. It's no wonder so many people feel confused and stuck before they even begin. But here's the truth. You don't need to learn everything. You just need to learn the right things in the right order. And to help make your journey easier, I took a deep dive into how some of the top universities in the world like Stanford, MIT, and Oxford actually teach machine learning. I studied their course structures, the topics they prioritize, and how they build your understanding step by step. Based on that, I've created a simple and well structured roadmap just for you. This roadmap will guide you on where to begin, what topics to focus on, and it even includes free resources to help you start learning the smart way. Alright, so without wasting any time, let's get started with the very first step in your machine learning journey, that is to build a strong foundation in math. And by strong foundation, I don't mean you need to be an expert in every topic, rather, you just need to be comfortable with a few key areas. Start with linear algebra, which deals with vectors and matrices. These are used in almost every machine learning algorithm, so understanding how they work is essential. Then move on to calculus. It helps you understand how models learn and improve, especially when it comes to concepts like derivatives and gradients, which are used in model optimization. Next, focus on basic statistics. It will help you understand your data, compare results, and measure how well your models are performing. Finally, learn some probability. This is important for understanding how models make predictions, especially in classification problems. If you're looking for resources, there are free courses by MIT on all these topics. But if you want to learn these concepts in one place and in a simpler manner, I'd recommend the 6-hour Statistics for Data Science full course by Intellipaat. This free course will equip you with all the fundamentals of stats needed for machine learning algorithms. Step 2. Learn programming with Python. After building your math foundation, the next step is to learn programming, and Python is the best place to start. Python is simple, beginner-friendly, and widely used in data science and machine learning. Its clean syntax makes it easy to learn even if you're new to coding. So you can begin with the basics like variables, loops, functions, and object-oriented programming. These are the building blocks that will help you write clear and efficient code. Once you're comfortable with Python fundamentals, start learning the most important libraries for data science and machine learning. First is NumPy. This helps you work with numbers and arrays. Then comes Pandas, which is great for organizing and analyzing data. Matplotlib and Seaborn help you create graphs and charts to visualize your data. To get started, Google offers a free Python class that's perfect for beginners. And if you want to learn the libraries I mentioned, I have created full courses on NumPy, Pandas, Matplotlib, and Seaborn. You can find them directly on YouTube or on Intellipaat's channel. Step 3. Get started with supervised learning. Once you're comfortable with Python, it's time to step into the world of machine learning, starting with supervised learning. This is the most common type of machine learning where the model learns from labeled data. In simple terms, the data you feed into the model already has the answers, and the model learns to predict those answers for new data. You'll start with basic algorithms like linear regression and logistic regression. These help you solve simple prediction problems like predicting a number or classifying data into categories. After that, you learn about regularization techniques such as L1 or lasso and L2 or ridge, which are used to avoid overfitting and improve your model's performance. Another important part of this step is model selection. You'll need to understand how to balance bias and variance to choose the best performing model for your data. And then you also need to learn how to evaluate your model. Evaluation can be done on some key metrics like mean squared error, MSE, which is for regression problems, and accuracy, precision, recall, and F1 score for classification problems. These metrics tell you how well your model is doing and help you compare different models effectively. To learn these topics, I'm going to tell you guys about the free resource after the next step of our roadmap. So step 4, explore advanced supervised learning techniques. Once you're confident with the basics, it's time to move one step further and explore some advanced machine learning algorithms. These models are more powerful and can handle complex problems better. Start with naive Bayes, a simple but effective algorithm that's great for working with text data like detecting spam emails or classifying news articles. It's fast, easy to understand, and works surprisingly well in many real-world tasks. Next, learn about support vector machines or SVMs. These models are especially useful when you're working with data that has many features. SVMs try to find the best possible boundary between different classes, which makes them very effective for classification tasks. You'll also come across decision trees, which are known for being easy to interpret. They work like a flowchart, making decisions based on conditions in the data. While simple on their own, they become much more powerful when combined in ensemble methods like random forest and gradient boosting. These techniques combine multiple decision trees to improve accuracy and reduce errors. You can check out UMBC's Supervised Learning course on edX. Here, every topic is explained with clear visuals and simple language, making even the hardest ideas easy to grasp. Step 5. Understand unsupervised learning. Unlike supervised learning, where models learn from labeled data, unsupervised learning is all about finding hidden patterns in unlabeled data. This means the model tries to make sense of the data without being told what the correct output should be. It's useful for tasks like clustering, customer segmentation, and simplifying large datasets. A good place to start is with clustering algorithms. Begin with k-means clustering, which groups similar data points together based on their features. Then explore hierarchical clustering, which builds clusters step by step, either by merging or splitting groups based on how close they are to each other. After clustering, move on to dimensionality reduction techniques. These methods help you reduce the number of features in your data while keeping the most important information. Start with principal component analysis or PCA and factor analysis, both of which are commonly used to simplify complex datasets and improve model performance. You'll also come across more advanced tools like Gaussian mixture models, GMM, and the expectation maximization algorithm. These are useful when you want your model to work with probabilities and uncertainty. To dive into these topics, you can check out Stanford's CS229 lecture series, or if you liked UMBC's course on supervised learning, they also have a similarly structured course on unsupervised learning. Step 6. Dive into neural networks and deep learning. This is where machine learning gets really exciting. Neural networks are the backbone of modern AI, and deep learning models are capable of solving problems that were impossible just a few years ago. Start by learning how basic neural networks work, understand perceptrons, activation functions, and the backpropagation algorithm. Once you're confident, move into deep learning concepts like CNNs for image tasks and RNNs for sequence-based data. You can also explore autoencoders for representation learning and more advanced models like retrieval augmented generation or RAG, which are used in modern language models. Some amazing resources here include IBM's Deep Learning with TensorFlow and Keras course. There's also a free book called Deep Learning with PyTorch if you want a more technical deep dive. Step 7. Explore advanced topics in AI. At this stage, you can branch out into specialized domains within AI. If you enjoy working with language, natural language processing might be the perfect fit. You learn about tokenization, sequence modeling, and state-of-the-art models like BERT and transformers. If you're interested in decision making and robotics, reinforcement learning is another exciting area. You'll explore Markov decision processes, Q-learning, and policy gradients, basically teaching agents how to learn through experience. You can also look into learning theory to understand what makes models generalize well. And finally, it's important to learn about AI ethics, how to build responsible models that are fair, interpretable, and aligned with human values. Stanford's CS224N for NLP, David Silver's reinforcement learning lectures on YouTube, and Mozilla's ethics in AI initiatives are all great free resources to guide you here. Step 8. Work on real projects. The best way to learn is by building. Start with simple regression and classification projects using open datasets from platforms like Kaggle or the UCI Machine Learning Repository. As your confidence grows, start working on more complex projects like image classifiers, sentiment analysis tools, or even reinforcement learning agents that can play games. Document everything on GitHub, share your work on LinkedIn, and maybe even write blogs about what you've learned. This not only solidifies your understanding, but it also helps you stand out when applying for jobs.
So what we are going to do is we are going to start with machine learning using Python. All right, let's start. Okay, so what is machine learning? Let's start by saying that, machine learning is all around you. When I say why it's all around you, you are already seeing machine learning here and there around you. Let me give you one example. So we have this, everyone must have bought from Amazon or Flipkart or any e-commerce website, right? So we would have bought from there. So how does Amazon implements machine learning? So imagine if I am going today and trying to buy, a phone there. Let's say I'm a big fan of OnePlus and also Apple. So what I'm trying to do is I'm trying to buy a phone. Okay. So what do? I go to Amazon, I search different variants, I search different things, and then I'm like, okay, I am going to purchase this 64 GB, this, and this is in my budget. This is my phone. What does, when you go to the, when you're looking at the product page, don't you see a small thing there saying that, there is, what do you say? There is something that you would like to buy, a phone cover, charger, probably some accessory that comes with mobile, right? Do you see that? Let me try and show you that. Let's go to Amazon. So when okay, I'll have to log in. I don't want to log in. Let's say if I search for phones. Okay, let it load. Okay, let's say this, if I go and click on one, okay, they'll come and tell you, see more products details here, and you'll also have frequently bought together, right? This is around you. What are they saying? You are purchasing a phone, you would also like to purchase a cover, would you? Right? And then they are also recommending that related products with this. Everything. So you see how Amazon is recommending. This is machine learning. This is machine learning. Let me close this. So when Amazon tells you that, you are purchasing a phone, you would also need a cover. Then once you put the cover there, the next thing what they are going to tell that you would need a screen guard, right? That's what. So that is a type of machine learning that is around you. Okay. That is a type of machine learning that almost everyone must have experienced here and there. And in some e-commerce website, be it Amazon, be it anywhere else, you must have definitely seen this. Okay. And then let me give you another example. How you guys are already implementing also uh, this machine learning. Okay. Let me come down. Okay. Let's try with this. Okay. So let's say you are what do you say? A player. Do you like sports? So let's say you are watching football. You're watching a football match. And what is the goal? The goal is that you need to put something into the net. This is the ball, and this is you. Trust me, I am a, you know, I born pretty late. Otherwise, I would have given competition to MF Hussain and, people like Da Vinci. So trust me, my drawing is absolutely best. So the thing is that we need to, what do you want to do? You want to hit the goal, right? This is where it belongs. But what happens? You've just started, playing football. What you do is you first try to hit it here and the ball goes here. That's your first aim. Okay. Now, what do you contemplate? What do you see? Okay, I have, pushed something to very right. I need to put it somewhere here. This is the gap that I see. I need to put the ball somewhere here so that it goes inside the goal. Then this is what you try. This is the second attempt. And you score a goal. You score a goal. So what happens is, what is this that you have seen? What is this? This is nothing but this is what you have learned. You have learned this. This is your assessment that, you need to be this much closer to the goal. Your ball should hit not outside the goalpost. You need to put it towards the left so that it goes inside the goal. So what you're doing here is essentially you're learning. This is how machine learning also works. So rather than you learning, this is how you're implementing machine learning in your real life right now. Not even playing, not even while playing. we also watch matches. So a cricket match, there was a World Cup right now, right? So we were all guessing, yaar, kisko denge, we need to take, wicket of Klassen so that we win the World Cup. And everyone was like sitting there and saying that, we were waiting anxiously that, when Klassen goes out, people, they're putting the ball really in front so that he's hitting sixes and fours. Why are you giving bowling to, spinner? He's hitting them really well. ऐसा आ रहा था ना feeling. So that is where we are judging and we are learning from our mistakes that the last ball he hit was a six and it was right in front for there to be hit. So the bowler also learns. We are also saying that it shouldn't be there. And how are we learning? We are learning from our mistakes. That's key part here. We are learning from our mistakes. Okay. So when we are learning from our mistakes, what are we learning? We are learning the delta. We are learning that we have made a mistake and we have not reached the right task in goal also. And when we were getting belted by Class N and everyone from the South African team in the final, we were also missing that, right? So the key thing is that we are learning from mistakes. We are learning from our past experiences. Okay. So that's how we were learning. Now, the other thing that keep this in mind, okay? Keep this in mind that how are we learning? The other example is Alexa. So have you seen Alexa or have you ever seen Siri or Cortana from Microsoft? What do they do? When a person speaks, Alexa automatically, yeah, exactly, Anil. It follows our instructions, right? It follows our instructions. I say, Alexa, wake me up at 7 a.m. tomorrow. It will immediately go there and, put an alarm of 7 o'clock. And at the morning, 7 o'clock, वो रुकती नहीं है जब तक I don't get up. It will not stop till you say that, okay, I am up or stop or shut up. So this is how Alexa, it's learning from you, it is around you. And also a very simple example, even before Alexa and everything came, how I don't know if people use it quite popularly today, but there is an option in your keyboard. You can press the mic and speak and it will write the message for you, right? So why machine learning is here is because it is understanding from people voices. There are so many people who have different voices, who have different tones. Okay, they have different what do you say, textures in the voice. A female voice and a male voice, it would be like, hey, how are you doing? Or a female would be, hey, how are you doing? So all those things are there. There's pitch, there is also the shrillness in the voice. So Alexa is able to understand everything. And we are Indians, Alexa is being used out as well, right? So someone from Britain would say, hey mate, can you show me a beautiful place to go? And someone from the other side, or a Japanese or a Chinese, they'll have a different accent. So Alexa is able to recognize all these accents. They are able to nullify all the pitches, male, female, different languages, different cultures, different accent, and still able to understand what you're saying. Correct? So Alexa is having that voice recognition. That's why it is able to do that. Okay. We put this on the side. And then, yes, what else? We have Netflix. This is my favorite. So, how many of you have Netflix accounts or have, interacted with Netflix? We have gone to Netflix, and do you know what it does? As soon as you log in, as soon as you log in, as soon as you log in, it will ask you what is your genre, what are your favorite things that you like, right? It will ask, do you like comedy? Do you like thrillers? Do you like English movies, Hindi movies? Do you like romantic movies? All those things it will ask. It will just ask for four things. And as soon as you watch a movie, one or two or three, I think the cutoff is four. Once you see four or three movies, it will automatically start, recommending you the movies that you would like Have you seen that? How is it able to do that in the background? So this is also a case of machine learning. This is called recommendation system. Movie recommendation. It is recommending you the movies. You have not even gone there and rated the movie that yes, this is 5 star, this is 1 star, this is 4 stars. But based on that, it is still able to, tell you that what you might like in the future. So how do they do this? What they implement something is called as, let's say there is Anil. Okay, he watches Netflix. He goes and watches 4 movies. Okay, and what are the characteristics of Anil when he logged in, when he took the account of Netflix? They say that, okay, Anil, tell me what's your age, man. He's 42 years old, and Netflix also knows he is a male, right? And also, which part in India do you live? Delhi. Okay. So these are these different things that they know. You have already given to Netflix for free. As soon as you log in, as soon as you create your card and everything, your account there, you've already given that knowledge to Netflix for free. Okay. So what Netflix does is Netflix will try to look at all the people within Delhi. Okay. All the people who are, male, and all the people who are in a certain range, let's say 30 to 50 range. Okay. It will try to see what all movies these people are watching. What movies or TV shows these people in Delhi or NCR are watching? What movies are all the males watching? What movies is this group watching? And there is also one peculiar thing. That's when become a data scientist eventually. You'll try to understand. This is very simple. The other very peculiar thing is your watch time. Your watch time. So are you watching in the evening? Are you watching at night? Okay. Are you watching in the afternoon? This they will automatically get from their platform from Netflix itself. They don't need to come to you. So what they are going to do is they are going to look at all the other people also which watch in this in evening, at night and afternoon. Whenever they watch, what are they looking at? And they also have preferences. Anil has also told, I like comedy movies. Okay. They are going to do this matching based on all these characteristics. And they are going to say that these are the 4 movies that people in this area, people in with this traits are watching. So what are they going to do? They are going to go and recommend all these movies to Anil. Okay. So this is very peculiar, and this is a type of uh, machine learning as well, which is called recommender system. We call them in industry, we call them in short, Rexes, recommender systems. Okay. All right. This is one very peculiar example and very popular one. Trust me, guys. I have taken interviews and I have also gone to so many interviews. People will ask you, how does Netflix, recommends movies? This is a quick, from my experience, I'm telling you, you can note this down. You need to have at least this basic understanding. Even if you are not applying for any role that requires recommender systems, you need to know how it works. It is very important from the interview side. Okay. I will mark a star here so that all of you know that this is something that you should at least know at this level. Whenever you're sitting for interviews, whenever you're going for, a role that you're applying, be it data scientist, machine learning, and anyone, that you should know at least what is recommender system and how does at least Netflix works. And once you know this, the the beauty is that you also know how Spotify works, how Spotify works, how Amazon works, right? And there are so many places. YouTube works, Instagram works. All these e-commerce sites, they are recommending you something or the other, right? You watch one reel, which is, related to, let's say, dance, and then the next following reel is also around that. Is it a coincidence? No. They know that you would like this. Whenever you see a video on YouTube, you're looking something, that how to do this in Excel, how to do this in Power BI. Next, on the right hand side, you will see some of the videos related to Power BI, because you know that you're looking at this, you might need this. They are recommending you. Okay. These are subscription based, these are free based. Your YouTube and your IG, they have a slight difference, but mostly it's around the same concept. Okay, we'll go into the detail, what happens in detail, but it is around the same. Okay, perfect. So we know recommender system, and Netflix, you won't believe, was one of the first companies who started doing this. I'll tell you, if you want some background around this, I'll tell you what machine this Netflix used to do. Netflix was a company who used to sell CDs. Go and look at the internet. They used to sell CDs, and then they used to keep the data of who's buying this CD, who's buying this CD, and even then they used to recommend CDs to them, that you have seen this, you might like this as well. So they were one of the first companies who implemented this. They bet a lot on data science, on recommender systems. One of the first companies. Okay, cool. Let's see, what do we have the next example. Google Maps. Now tell me, everyone would have used Google Maps here and there. I live in Bangalore, and trust me, my life is hell without this Google traffic prediction. Okay, what does it tell you? As soon as you say that I want to go from here to here, right? They are going to tell you that this is the time that it is going to take. It is going to take 1 hour. It is going to take 30 minutes. It is going to take 15 minutes. And over there also, they'll tell you the route, which one is taking less time. They'll give you an alternate route. And also, it takes it next level. How does it take it next level? It tells you that if you travel between 9 to 11, it is highly congested. It is the most time taking route. If you want to save your time, travel between 7 to 8. It will tell you this is the traffic prediction what Google is doing. Okay. This is also around you. Next. Okay. Let's start machine learning. Let's get into it. So machine learning, now I will do one thing. I want to start with a few things that are not in the PPT and not this thing, but is coming straight from my experience. And trust me, I need your 100% attendance. 100% attention here. If you're looking at a phone, if you're distracted by someone, trust me, if you learn this in the next half an hour, what I'm trying to explain, you will get the entire cusp of machine learning. I will be able to cover this in future, but not in this detail. Okay, so please pay attention. Let's do. Okay, so machine learning, what is machine learning and how is it different from your programming? Has anyone made a program? Can you tell me that we can write a code, okay, to say that which number is even, which number is odd? Very simple, right? We know that all these things are odd, okay? And we also know all these are 2, 4, 6 are even. correct? So we do this very basically. So we can write a program say to identify this. Okay. Now tell me one thing. Let's look at another example. The other example would be email. Email spam. Okay. Now tell me one thing. You also have Gmails, any Outlook or any this email system you have. You have your account there. You might notice a folder called spam there. होता है कि नहीं होता है? होता है ना? Spam क्या करता है? It tells you that these are not required or unnecessary. Unnecessary. Okay, you need not pay any attention to this. So what happens there is, how do we do this? Tell me one thing. How do we do this? How is Google able to or Gmail able to? I'll take an example of Gmail because most of us might be using Gmail. How is it able to tell whether it's a spam or a non-spam? Imagine if you are, you don't need any coding for this. Just think with me logically. Let's say you have this data set like this. Where you have your emails. Okay. And we tell you whether the content of it, this is your content. And let's make one other column, whether it is spam or no. Okay. This is your email one. This is your content one. And this is spam. This is your email two, content two, and this is spam. This is email three, content three, and this is not spam, and so on. Okay. Let's say you have 100 emails and you have all the content with them, all 100 of them. And this is also non-spam, for example. How will you guess whether it is spam or not spam? If you are given this opportunity that you have to guess which one is spam, which one is not spam, how do you guess? Have you gotten any messages on your phones that you have won this lottery? KBC से phone आ रहा है, you won 1 crore and you need to deposit, right? KBC say you have won, you are the lucky customer and you won 1 crore rupees, deposit 2,000 rupees and crorepati ban jao bhaiya. Okay, all these messages are there, right? So these messages, what they do is they have, this is the keyword here. Let me close this for a moment. The keyword here is your keywords. You are able to tell with the presence of keywords whether this could be a spam or this could not be a spam. What are these keywords? What are these keywords? These keywords would be lottery, right? It could be prize. It could be lucky. Another thing would be win, right? All these are your keywords, which can help you identify whether a email is spam or not spam. So now, once you have understood this, now this is where we go into the difference between your classical learning as well as machine learning. How is machine learning different? So if there was a normal programming, okay, let's say this is classical programming approach. Classical programming approach. What they will do is they will have one program, okay, a software engineer or a developer. Let me say that this is a software developer engineer. Okay, what they will do is they will write a program, and that program will have what? it will have two things. It will have rules and it will have your input. Input is what? Input is email, right? And the output is going to be whether it is spam or not spam. Correct? But imagine how are these rules coming? ये rules आ कैसे रहे हैं? ये rules ऐसे आ रहे हैं, ये कीवर्ड से, इस कीवर्ड से rules आ रहे हैं. If you see a mail an email having these words lottery prize and बहुत सारे words होते हैं, ठीक है? If you see that and if you notice that email has close to 70% of these keywords, then you will say that it is a spam. नहीं तो not spam. Correct? कितने if else लगाने पड़ेंगे? There may be so many if else's. If else क्या होता है? If else is that you say if lottery present, then do this. Else, if it is not present, else मतलब do this. So they will have to look at each keyword in the email. Correct? It is so tiring. It is so tiring. It is so tiring. And this is not fruitful as well. This is not the right approach. You will not be able to capture all the keywords. And imagine उस code को run होने में कितना time लगेगा. So that's where ML comes in. That's where ML comes in. ML approach. What is ML approach? We have this again, the same data set. Okay. These are your emails. This is your content. And this is your output. Okay. This is E1, E2, E3, and so on till E100. And similarly, and you say this is spam, this is not spam, this is spam, and this is not spam, something like that. What does ML approach says? ML approach says, भैया दिया तो हुआ है. एक एक को कोड नहीं करना. We don't have to find the keyword. What we will do is we will ask our ML to recognize the pattern. To do what? Recognize the pattern. Machine learning is only this. You have to, I will write this again. You have to recognize the patterns in data. Okay, this is ML. What is the ML approach now? We will not write, those programs where you have rules, you have inputs, and then, it will have an output. What ML will do is ML will take this data, okay, and it will pass it to what do you say as a function. This is an ML algo. Okay. This is an ML algorithm. It could be naive Bayes. It could be a classification base. It could be random forest. It could be anything. It could be logistic regression. You might have heard these words. We are going to cover it in this module itself. And trust me, be with me. We are going to do it from scratch. Like absolutely no iota of doubt should be there in your minds. What is ML algorithm? We have these emails. Okay. It will be passed into this ML algorithm. ML algorithm will do what? ML algorithm will make a function. This function is also sometimes called a hypothesis function. Okay. And what's the job of this function? Hypothesis function. It will find patterns. it is going to find patterns for you. And it is going to say, based on the data that I have, this is my input. Okay. This is my input and this is my output or my target variable. What is this called? Target variable, and is also called label. Okay. So what it is going to do is it is going to learn from this data. How it's going to learn? There is a concept of training and testing. Okay. So what happens is it will divide all these 100 emails into train and test and test. How it is going to do? So the popular approach in the industry is, what even I personally use is 70-30. I use 70-30. What do you mean by 70-30? The other approach is also 80-20. How do we do that? So I have these 100 emails. Okay. I will create one data set which is called train. Okay. And I'm going to use the 70-30 split. It is going to keep out of those 100 emails, it is going to keep 70 emails here. And is going to say that, this is my training data set. This is 70 and you're going to keep another test on this, which is going to be 30 emails. Okay. Now, why do we do this? What the ML algorithm is going to do, how it is going to find the patterns, it is going to look at this train and is going to look at the content of all of these emails. And rather than noticing those each keyword and putting if else's, it is going to say that, okay, I have learned that whatever you have spam and non-spam, I'm looking at both the options, right? It is also looking at an email which is spam. It is also looking as an email which is not spam. Correct? So it will understand, it will find that pattern कि यार जो spam mail होती है उसके अंदर क्या pattern है. It might be keywords, it might be the language, it might be something else, it might be the timing of it, it might be the urgency. Click on this button. Else, there's only 2 hours of time to do this. There's only 10 minutes of time to purchase this. You have won this lottery. All these things are fed into this machine learning in the training data set. Based on these concepts, it is going to learn that. It is going to automatically learn that, and that is when your model is created. Okay. This is what your ML model. So what is the test for? Why test? Model is created and model has identified the patterns. Then why do we need test? Okay. Model is trained, but we need to know whether the model that we have trained is working correctly or not working correctly. Is it saying that spam mails are spam only, or is it saying non-spam mails also as spam? Is it putting everything in spam or is it putting everything in non-spam? Correct? That is why you need test. And an analogy for this is you need test because you need to meet the requirements. Validate your results coming from model. Correct? This is why you need test. And analogy is, all of us have gone through colleges and even the what do you say, the schools. We used to study everything from the book, but then we had exams, right? We had exams. What was the motive of the exam? The motive of the exam was that we need to test whatever we have learned, whatever we have read. Do we understand it properly or no? Correct? That is how you are understanding, you are testing your model on this 30% and saying, okay, I've given you most of the data that I have. I have given you most of this data to learn, to find the pattern. Have you done a good job to find the pattern? I need to validate my model. That is why you need test. This is the basic concept that going forward, each of the algorithms will use. So what happens is, let's take the same example of email and spam. Okay. Now you have 100 emails. Okay. You have 100 emails. Each one of this email has been given into your model. Okay. You have first split it into train and test. You are given 100. Okay. You are Anju and you are given the responsibility to tell whether an email is spam or not spam. Spam meaning, is it harmful or unnecessary? Non-spam means it is a general email and we can read it and there is no suspicious links in that so that you can get fraud or something like that. So you are given these 100 emails. One way is that you would read all these emails and find that, okay, these keywords are present in my spam and non-spam. How am I able to tell, okay, this is spam or not spam? You are able to identify those keywords, correct? This is the original way or a brute force way. But since we are data scientists, we are aiming and learning machine learning, we'll do things thoda smartly. We are going to do things smartly. How? We are going to leverage machine learning, correct? We are going to leverage machine learning. So machine learning says that you have been given these 100 emails. You will divide these 100 emails into a train set and a test set. You will break these 100 emails into these two parts. One is train and the other is test part. In the train part, you will randomly select 70 emails, not top, not bottom, randomly. Okay. You will randomly select these 70 emails and say that, okay, these are my emails. You will pass those contents to your ML algorithm. You will pass those emails to this ML algorithm, which will try to find the patterns, which will try to find the patterns in the contents automatically. It will try to find the patterns automatically. There are many algorithms for this purpose. These are called classification problems. Okay, we will learn, and one most important algorithm or the basic algorithm in classification is logistic regression. Okay, so that is going to find the patterns and is going to give you probability, whether the probability of this mail of being a spam is 70%, 80%, or not spam is 70% or 80%. So we have that threshold. It gives a probability. It will not say 1 or 0 until and unless you code it that way. You provide that instruction that way, that anything above 50% or 70%, say it is a spam. It is learning from here. Okay. And once you have learned your model, you have to test it whether it has learned properly ke nahi. Has it learned it properly or no? You need to test it, right? You cannot say, okay, I looked at these 100 emails and I split them into 70 and I trained it on all 70. Then I'm good to go. I can put it in Gmail and Gmail can start using it. No, 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 no. You cannot do this mistake. Correct? You can never do this mistake until and unless you have validated your results. So how will you validate? You have these 30 emails. You have these 30 emails. Okay. Now what you're going to do? You will validate it. All these 30. Correct? This is spam. This is actual. And this is your prediction. You have said this is spam. This is spam. You have said this is spam. This is not spam, but you have said spam. This is also not spam, but your model has said spam. So you need to validate. If it is saying everything as spam, is this a good model? It has not learned anything. It's just saying that everything is spam. It has not learned anything. So that is why you need to split the data into train and test it on the test set whether your model has learned it properly or no. If it has learned it properly, there are certain metrics that we look at. Okay. There are certain metrics that we look at, but that is in other sessions we'll be covering what metrics are looked at. All right, let's move forward. So once you have done this, once you have created train and test, then you have your model. Now, one important thing is, when was the model created? Was it created on 100 emails or was it created on trained data set? Did we also use the test data set for creating our model? Creating model, did we use 100? Did we use 70 or did we use 30? This is train plus test. This is your train data and this is your test data. So we only trained our model on this. That is why the name training. Okay. Now, quick definitions or terminologies that you need to know whenever you're sitting into interviews or whenever you're talking to anyone. You are going to become future data scientist, you're going to become future machine learning engineer, you're going to become AI engineer. You need to know certain terminologies. So this train and test are called train data set. Okay, this is training data set, is the same data set, but you're dividing into training and testing. So this is your test data set. I am putting 70 here and 30 here. What is 100? This is your complete data set. Correct? Okay. And this thing dividing into train and test is popularly known as train test split. Train test split. I will write industry here. Okay. These are good jargons when you're talking in your interviews, when you're speaking in your interviews. You need to say training data set, test data set, complete data set. And the concept of dividing this is called test train split or train test split anyways. Okay, doesn't matter. And the other important thing is thumb rule. Thumb rule is either you divide it into 70-30. Okay, either you divide it into 80-20. How do we decide? It is decided based on data. The crux is the crux is that we need to follow. We need have one rule for this thumb rule, that we need to provide as much data for training. Now, can you tell me why? Why do we have to give as much data as for training? It is because your model is being built on trained data. Correct? If you are going to pass less data for building your, this thing model, it is not going to learn all the patterns. In building your model or creating your model, you need to identify all the patterns. You need to give as much data as you can. It has to cover all the factors. It has to look at everything. right? And how is this 70-30 or 80-20 split done? It is done randomly. It is done randomly so that if there are a few, whenever you get data, it is recorded somewhere. So there is already a sense of, date wise, it is either date wise or it is sorted by, who has sent it or something or the other. So you want to do it randomly so that you cover all the factors or cover all patterns in your train data set. Does that make sense? Okay. So these are some key terminologies and key things that you need to remember whenever you are going for a job interview. And also keep this, coded in your mind, because this is going to be your bread and butter. This is going to be your bread and butter. Okay. All right. Now the thing is, now we have understood this basic concept. Okay. We've also understood how ML versus classical programming works. Then from there, we have also learned how ML works, train, finding patterns, then, testing it on test data set. This we have learned. Now, the other thing that we need to, look at it is types of ML, types of machine learning. Okay. There are majorly two. Okay. There are three, but for now, trust me, there are two. This is supervised and unsupervised. Guys, we are going to just cover supervised and unsupervised. And trust me, this is 100% question, 100% interview question. You need to know this. Even if it is not an interview, you need to know this no matter what. This is the basic. Okay. So what happens in supervised? And this is close to 90% of the problems that we see. I'm coming from industry. I've worked on so many projects in my life. Okay. In last 9.5 years, 90% of the task is supervised. 90% of the tasks that we get or ML algorithms that we build or projects that we do in the company, they are dealing with supervised type of machine learning. Okay. So in this, what happens? Okay, tell me the above example that we saw of email, spam, not spam. This is supervised. How is this supervised? What does supervised mean? Okay, let's start from understanding the word. What is supervised? There is a person who is supervising the ML model. We are looking at those inputs. We are looking at the ML when it was creating that email model to classify whether it is an spam or not spam. We chose the training data set. We tested it on 30 emails. Okay. So that in future, we have the model built. In future, if any number of emails come, there are another 100 of them coming. You already have the model and it is a good model out, testing it, and you have fine tuned the model. Any number of emails might come. You will just pass it into that ML algorithm and it will tell you whether this is spam or not spam. So you have to do that effort once of supervising the model, supervising the entire thing. So one key thing that it has is label. Correct? Our label here was spam or not spam. Correct? We had this data set. There were emails that we had, and this was our output. Whether this is spam or not spam, spam or not spam. This is your target, or it is also called label. So the data is labeled data. Whenever you are going into supervision or supervised type of models, you will always have labeled data. Always you will have 100%. You will have label, because if you don't have the label, you cannot learn. Correct? If you were not given spam and not spam, you will be looking at keywords only, no? And even looking at keywords, you will not be able to say, okay, I'm looking at keywords, but I have identified these two keywords, prize and lottery, but I don't know whether this email was spam or not spam. Correct? So you will be always given this label. And in unsupervised, what happens is you will never have this label data. This is going to have unlabeled data. Okay, it is going to be unlabeled data. Now you will say, you should tell me, if it is unlabeled, you just now said that how will it learn? Then how will it learn? Any example that you can think of where unlabeled data can be used by machine learning? Okay, I'll give you one example. All right. Now this example would be fruits. Correct? So you have an apple, you have an orange, and you have a banana. You can club all the apples together. Okay, you can club all the apples together. You can club all the oranges together. There's no orange. Okay, let me put it this way. You can club all the oranges together, and you can put all the bananas together. You can club them together. How will you club them? How are you going to club them? You are going to club them basis on color. So these are some vision models in machine learning, okay? And they can look at the color. Or you have been given a data set. Let me do this way. Let's not go into this. Let's say you've been given this data set. You are not told that whether it is apple or orange. You are given color, okay? And then you are given its shape. These two factors only. Let's consider only this. There could be other thing also like length and width, but let's consider only these two, color and shape. So anything that is red and is kind of, oval, and this orange would be what? Orange color. And it is what shape? Round. And banana would be yellow color. And it would be long. Correct? Like this, you are given 100 rows. You are given. By just looking at these two, color and shape, can you say this is apple, this is orange, and this is banana? How? How will machine know? Machine will know that, yeah, the color of this is different from this. Correct? The color of this is different from this, and the color of this is different from this. Then I have another, red color. I have another yellow color. I have another orange color. And the shape of this is different from this. Whenever I see red color, I see oval in the shape. Whenever I see orange, I see round. Whenever I see yellow, I see long. So what it is doing, the keyword that I'm looking for, what is it doing to club them together? Features, yes. But what is it looking at? What does machine learning do? I told you in the beginning, it is looking at patterns. It is looking at patterns. It is saying that whenever it is red, I have oval. And then there is a different type. Whenever I see orange, there is round. Then a third type, which is yellow and long. Then all the rows out of these 100 rows, they are being, having these three combination only. Red and oval, orange and round, yellow and long. Then I see red and oval, orange and round. So I can divide them into three categories. I can divide them into three categories. This is where the concept of clustering comes in. Okay. So without looking at the data, without even looking at the labeled data, have I told you this is Apple? Have I told you here? No, right? Even if this was label, I don't have the label. I don't have the label. But still, just looking at the patterns, you can say the red, orange, yellow, red, orange, yellow, red, orange, yellow, oval, round, long, oval, round, long. There is a pattern. I can divide these, I can pick these three, correct? This is your type of ML. This is an another type of ML. Okay. Okay. So let's make it small so that it's easier to explain. Okay. So we have two types of ML majorly. Okay. We have two types of ML. One is supervised, the other is unsupervised. Okay. Here in this example, you know what is apple, what is orange, what is banana. But imagine a project where you're told that, okay, you remember the initial, what do you say? Um, the initial example of Netflix, where we took Anil's example. You don't know when you're saying that, everyone in Delhi, everyone in, in the age group of 30 to 50, everyone, watching in the evening or at night, they are related to each other or no? You don't know. You are just blindly following this model and saying that, okay, it is good at, identifying the patterns. So it would have done the right thing. So clustering is really important. It is used where? It is used in customer segmentation. When you have to segment your customers, right? You have to do fruits like this example. I'll explain you with another example. Okay. Let's say, you are given some photos. Okay. You are given some photos. I'm not saying what, but this is one photo. This is another one. I told you guys, I'm a competitor for MF Hussain. So if you're not able to understand what is this, it is not my fault, huh? This is not my fault. Okay. And then we have this. Can you identify? Let me make this change so that it is easily distinguishable given my. So you have this. Hmm. Trust me, these are dogs. And these are cats. Okay. Trust me when I say you're not able to understand my drawing, but this is what they are. How would you identify? Once I've told you this is cats and dogs, are you able to say that all the cats are having these whiskers, this mustache, and the dogs they are not having that? Correct? So even model your ML algorithm will, out of all the photos that you have, is going to identify the patterns. Is going to say, I have one set of photos which doesn't have this hairs on the face, and I have one set of photos which have this hairs on the face. Correct? The other example. Okay, tell me one thing. Do you do you guys have your accounts on Facebook or Instagram where photos are shared? Do you have it? So do you remember that initially when Facebook rolled this data out, right? When Facebook uh, was rolling this feature out where it could automatically tell that, you and your friend, let's say Tulsi and Saranya, you are together in that photo. It would ask you first, initially, it would ask you to tap it. That where is Saranya? Where is that? Where is that? It will automatically identify your mother and father in a photograph. So it is trying to club those clusters. Okay. It is trying to identify that, okay, you are always with them, you're always with them. But since it is a more, advanced kind of algorithm where ML, where you are using vision, you're using photos, correct? So in that case, you will have to give it some kind of, input. But here in these simple examples like fruit, like, when the data is tabular, keyword is tabular data. Keyword is tabular data. This is your tabular data. When the features are given to you in terms of tabular data, you can implement clustering. Okay. And whenever you are given features in tabular data, it will say, what will it say? Here the data would be like this. Here the data would be whiskers. Okay. Um, and here would be sample, uh, let me say serial number, because you don't know. I'm just giving you an example with one feature. In the end, there are multiple features that goes in, but let's say these are 1, 2, 3, 4. We have 4 examples. Then you have whiskers, yes, you have no, you have yes, and you have no. So are you able to, looking at this, you can say there are only two outputs here, whether whiskers are available, the facial hairs are available or no. Based on that, you can club these 1 and 3 together, and you can club what 2 and 4 together. Can you or can you not? Just looking at the data, you don't know what it is. This side of the picture, you don't know. Correct? So that is what these are, your clustering algorithms. It will automatically do that, looking at the data. Okay, perfect. So now we have covered supervised and unsupervised. Okay, so we have already learned about clustering, correct? And the example that we saw for clustering was, it was fruits. And then the other example was dog, cat, correct? This is clustering and it is unsupervised. This is unsupervised and the data is unlabeled. This is what we saw. Okay, 2 examples. Then we learned something. Now I'm giving a formal name to it. It is called classification. Classification. For classification, what example did we saw? We saw email, spam and not spam. Okay. This is what type? This is supervised. And it is on labeled data. Okay. Now, the thing is, guys, if you look at it, I did this purposely. If you look at the output of the ML model, is it not yes or no? Or it is not, can we not say it is 1, 2, or 3, like in our fruits example? Three categories we were able to create, right? In dog and cat, it was 2, correct? So we are having in both these, we are having the output of the ML model is like what? Is integer, correct? Or discrete. Now, this is the term that you should refer. This is what industry follows. Discrete. Okay. Meaning that you will either have a specific number of categories or a specific number of outcomes. It cannot be 1.2. Correct? It cannot be continuous. So the opposite of discrete is what? Is continuous. And to understand, only for our understanding, we don't have to tell this to anyone. It is only for our understanding. These are the outcomes are real numbers. Okay. You understand what are real numbers? It could be 1.5, 2.3, 4.8, 100.8. Okay. Floating. It could be floating. Let me put this as float. Okay. Let me put this as float here. Okay, I'm just telling these two, you don't have to tell to anyone. It is only for our understanding so that you can understand. This is the one that you need to speak. Continuous, and here it's the discrete. This is only for our understanding so that we are able to understand the concept. Okay, so nothing wrong in it. It's just that if you will say continuous or discrete outcomes or continuous outcomes, then it is, people will know, okay, he or she knows what they're talking about. Correct with me? Just telling you out of experience. Follow this. Trust me. You'll not face any problems. In fact, you'll have a good impression on the person in front of you. Okay. Be it your colleague, be it your interviewer, be it your boss, anyone. Okay. So there are two examples of the continuous outcomes that I want to discuss. One is regression. Okay. Have you heard about regression? This is generally the first topic that everyone teaches. So regression is nothing but when you are predicting continuous numbers. Continuous numbers or values. Now, what could be the example? Example could be predicting salary, right? So if you want to predict the salary of someone, saying that, okay, this is the amount of years of experience he or she is having, these are the skills that they work in, this is the field that they work in, then we can predict the salary. And salary could be any number, right? Could be any number, even the price. It is not fixed that salary will be only 1,000 or 2,000. It cannot be, 40,000 or 50,000. It can also be 52,000. It could also be 52,050 rupees. It can take any value. Any value is possible. Okay. We try to round it up in 500s or 100, but in logic, it can take any value. Correct? Then the other also example is predicting house price. So if you are trying to sell or buy, okay, a house, that is also a regression. How will that regression happen now? In this example, again, it is supervised. It is supervised. It will have labeled data. How will the data look like in this case? Just giving an example. So let's say the price is this, okay, and you will have area. Correct? What is the area of the house? Number of bathrooms. And let's add a few more. So the other one would be locality. Correct? So this is how things will look like. And you will say, okay, this is, 20 lakhs, this is 30 lakhs, this is whatever number of bathrooms, 3, 4, 5, something like that. Correct? So this value can take anything. So again, the concept here would be same as we learned in classification. This is supervised. So whenever there is supervised learning, you will have to split the data. Correct? Because you want to learn the patterns, and then you also want to test your model. So this will again have that train, test, split. Everyone with me? Okay? Train, test, split. Amenities. Oh, obviously, how many features does this thing have? If you're selling a flat, whether in that society, how many things are there? Is there a swimming pool available? Is there, let's say, a children area available? And if it is not in an apartment, it is an independent house. Is it facing towards the park? How far is the park? A place where people play, a garden, something like that, right? Amenities. Okay. So all these things you will learn from these patterns, and you will say, this is what I have. You will train, test, and then you will create a final model. So what will happen if we till now we have this understanding that whenever there is a supervised problem in front of us, no matter whichever type it is, whether it is, classification or regression, unsupervised hai, label is present, we have to split it in train and test. With me? Now, in that, once you have done that split, you have to train the model on train. That's why the name as training data set. And then you have to test the data set on the test split. Now you have found that after testing it, the model is not right. Whatever actual values that you see, let's say this was your train data set, okay? And this is your test data set, okay? Let's say whatever features that we had on top, we are having here also. This is your test, for example. Now this is your actual value. You're saying the actual value is 30 lakhs and the actual value is 40 lakhs. But your model is predicting this is 100 lakhs. Okay. And it is saying this is 200 lakhs. It is very bad, right? It is very bad. So what will you do in that case? You tested it for some reason. You know it is not working good. Will you go and tell it to, 99 acres, for example, that take this model, you'll be able to, do well with it, or you will give it to yourself or your friend, saying that I have built this ML model. It was trained on 70% of the data or 80% of the data. It is predicting what should be the price of the house. If you're looking for property, use my model. Is it useful if you're getting these predictions? No. No, right? No, you cannot use it. If your house price in actual was 30 and you're predicting 100, okay, you'll be at loss. And people who are using your model will be at loss. The only person who would be laughing or would be, saying is good is the one who's selling the house, not the people who are buying it. People who are selling it, they'll be like, "Arey, this model, that this guy has made is really well. It's giving me profits, profits. It's raining money here and there." Okay. So whenever you test your model, you have to improve it. You have to improve it, improve it. And when I say improve it, what do you do? In industry or in everyone in the field in data science and machine learning, they call it as fine tuning. Okay, they call it as fine tuning. So keep this word in mind, that till now, take my word for it, we will go into fine tuning, how it is done, what are the different techniques. There are hundred of techniques for each of these type of MLs also. We will cover each one of them. I will leave no stone unturned, that you don't get 100% of this, not 100%, 200% out of this module. But for the time being, till we go there, just trust me, this is the process, that you train the model, you test the model, you on testing, if it is good, you pass the model, you give it that it can be used in real world. If your model is not good, you have to fine tune it. And when I fine tune it, imagine it this way or understand it this way, that you are going back to your training data set and trying to make some changes so that your ML model is a new version of the model and is an improved version. Okay. And then you test it again. Then you say, okay, this is better than the previous one or worse than the previous one. If it is better, then you try it again. So it is a cycle. It is an iterative process. Correct? Okay. How we do fine tuning? What are the techniques? There is feature engineering, there's feature selection, all those things are there. We'll cover it one time at a time at the right place. Okay. So here, keep this in mind till then, that we fine tune the model. Okay. And regression is continuous based. Okay. Predicting your salary, predicting the house price, everything that is related to real numbers is this thing. Then there is a different case. Okay. People very often, I've seen many people, they get confused with this, and that is forecasting. What is that? Forecasting. Why they get confused and what do they get confused with? Guys, I need your 100% attendance and attention. This is a key concept, which is, you know, people, it is very close. There is a thin line, and people get confused in this a lot. And this is what, people are looking at to reject you. Okay, they don't know this only. Okay, so please play 100% attendance here and attention. So forecasting is also continuous. Okay, and is also prediction, is also done on labeled data, which in turn means it is supervised. How is it different from regression then? My pen is not working properly. How is it different from regression? there is one very key aspect, which is why this forecasting is different from regression. This is the key thing. Anyone asks you, this is the first thing that you should tell. It is having a component of time, component. This is the key. This is the main thing. How forecasting is different from regression. Okay. Now tell me one thing. What are the examples? I'll say the examples and you'll get to know. What are the examples for forecasting? Forecasting example is weather forecast. Have you ever heard anyone saying weather prediction? Correct? It is weather forecast always, because there is a time component to it. That what was yesterday and what is today, what was 10 days back, what has been happening every day or every month based on what kind of forecasting you're doing. Is it weekly forecast? Is it a weekly weather forecast? Is it a monthly forecast? Is it a daily forecast, or it is a hourly forecast? Okay, so this is third, and the key component is time. Here, how would the data look like? Forecasting can be done only with the label also. You know why? You know why? So if I tell you that this is your data set, the let's say temperature, okay? Temperatures are pretty high right now, but I'll try to be lenient. 30 degrees, 32 degrees, 33 degrees, okay, and so on. You can put in anything. 40 degrees, 50 degrees. This is given for one location, let's say. Okay, this is what your label or your target variable. You don't need anything to forecast this. All you need is, if you tell me when this occurred, I can tell you when it is going to occur in future. Let's say this is date. This is date. This is day one. This is day two. This is day three, day four, day five. Okay. So we can do anything. If I tell you these were the 5 days and these were the temperatures, I can get it now. I can tell you that this was the forecast, this was the temperature in last 3 days or 4 days. Even you think of this very logically. If you know that winters are coming, how do you know winters are coming? Because you keep it in mind that whenever November or December it starts, winter are going to start. It's time based, right? Whenever you feel that the temperature is going up, you have that in your mind that okay, it is only during these part of days or this part of years where temperatures are high, which is called this thing, summer. So the only thing, we'll cover this in detail, but I wanted to show this to you that there are different types of ML, okay, and different uh, implementations. So it is very seasonal. This season is what? Time based. So this is the key thing. Time based. Okay. Never be confused. For now, just say that it is time based, and we do a prediction or forecast of a continuous variable. Okay. Cool. The fifth thing. Okay. We've already covered it. What was that? Rexis or recommender systems. What was the example that we discussed? We discussed about Netflix, and then we discussed about Spotify. It suggests you the music based on your taste, correct? Okay. So these are the five types. These are majorly five types. And there is one more thing, which is, I told you in the beginning that majorly it is supervised learning and unsupervised learning, correct? It is supervised or unsupervised, but there is another thing called as reinforcement learning. Okay. There's another thing called as reinforcement learning. We'll look at some examples. I think with the examples, it will be very clear how, they have. Let's move in. Guys, this is very, very important. Let's get to it. So we had left the PPT here on introduction to machine learning. I think what machine learning is, it's a subset of artificial intelligence. This is all, a formal definitions, but main for your understanding is machine learning learns patterns based on data. Okay. Then we test it so that we test its performance. Okay. But formal definition is that it is a subset of artificial intelligence. Artificial intelligence is a huge field. There are so many things into it, like robotics, like you have, machine learning. There's so many things into it, RPA. All those things are also, anything that helps, a program or a robot or anything to do something that has some artificial intelligence to it, and intelligence into that system is there. That is artificial intelligence. Okay. Machine learning is a special field inside artificial intelligence, okay, which has been gaining great traction these time. And trust me, there are so many jobs, and it's really an exciting field to be in. Uh, Data is the key and learning algorithm. Okay, so that's we've already understood. Then we also understood what is machine learning, and yes, this is one thing. That what is machine learning. So there is a meme on this, that a teacher is there is a class of robots and everyone is doing their job, and there's one person or one robot in this case who is misbehaving. So the teacher says that, Robbie, stop misbehaving, else I will send you to data cleaning. And the class that they are going through is machine learning. Okay, so the pun here or the joke here is that as a data scientist, okay, or as a data analyst, or even, you know, anyone in this field, machine learning engineer, the most of the tasks that you'll be doing, the life cycle looks like this in machine learning. So you have data, correct? You will first get the data. That's your first step. Get data, or it's also sometimes called load data from somewhere, wherever it is available, from the client, from, someone needs to build an app. So anything on the internet, you need to get the data first. Then the other thing is we need to transform it. We need to, do multiple things so that it is fit for machine learning. So I will go into in details what is the difference between transformation, loading, extraction, ETL jobs, all those things. Data engineers are the ones who do that. Okay. This is more of a, I'm clubbing everything together. This is ETL. Okay. And majorly is the data engineers who do that. Okay. Majorly. It's not that data scientists cannot do that or an ML engineer shouldn't do that. They do it. It depends from company to company, the size of the company. Okay, I'll come to that. The other thing is data processing. So this is where, 80% of the task is done. 80% data processing or cleaning, I will say. So whenever you get a data in real life, imagine I was showing you email one, content one, email two, content two, and I was showing you the data for house prices, right? Amenities and all that. in real life, it is not so clean, right? People who are noting down that data will make mistakes in noting down. People who are capturing the data, they will not listen to one thing and they will type in some other thing. There are always anomalies into the data. There are always some things that you need to clean in order for it to fit for machine learning, for the model. Once you have, once you get the data, you clean the data so that you've removed all the values that are missing, all the values that are suspicious. You've removed them, you've cleaned them. Then is when you can work on the ML part of it, dividing it into train and test, split based on whether it is supervised tasks or perform unsupervised tasks like of clustering. This comes only after doing data processing and cleaning. This is 80% of the job, and trust me, this is is very consuming, tedious, and people don't like to do this job. And I generally call this as grunt work. Grunt work. What do you grunt means something you don't like doing. Okay. So it is the major part of machine learning life cycle. Then third is your ML, model building. Now in model building, there are many things like there are EDA. Once you have cleaned the data, okay, EDA can be done while doing processing also, okay, so that you understand the data. EDA, what do I mean by EDA? It is exploratory data analysis. Exploratory data analysis. What do I mean by this? You are exploring the data, okay? You are exploring the data and saying that, okay, after exploring the data, I found these relationships. First, you will explore the data, then only you can ask the model or decide which model to put, right? You cannot close your eyes and just say that, okay, this is, I have the label, I need to do this. Once you have the label, you need to know now whether you want to do classification or regression or forecasting. So, and which are the fields that are important. Okay. We should remove the outliers. Outliers are also called anomalies. If you have a data set which is of all the cars which are being sold in cars 24 or spinny for that matter, if all the cars 99.9% of the cars are between the range of 3 lakhs to 20 lakhs, if in the data set when you receive it, you see one car for 100 crores, 100 crores, or other way around, 1 rupee. What is that? That is anomaly. Someone has made a mistake, be it a human. Most of the cases, it is a human who makes that mistake while noting down that data, while collecting that data. Sometimes it could happen due to some software issues also. Correct? So all this thing comes into data processing and cleaning. That is really important, but is also not a fun task to do. It is, very difficult part, but very essential part. Okay. That's where the meme is coming from. Okay. That if you misbehave in the machine learning class, I'll send you to the data cleaning class. Okay. Cool. Let's go ahead. And then, how does machine learn? We've learned it. It learns through patterns. This is what this slide is also talking about. So it is a really good example, and even to eyes, it looks very disturbing. So this is a breed of dogs which is Chihuahua, okay, and this is a muffin. So if some even your brain and eyes get puzzled, especially looking at a few of them, right? Like this one looks like almost like a dog, but it's a muffin, correct? And even this one, this example. So there is this doodle, Labradoodle breed, but you might get confused with a chicken, like this one. It's a chicken. This is a chicken. This is a dog. So at the end of the day, things could be very messy. It could be very confusing. In real life, things are not as simple as black and white. There might be a gray area. Okay? It's not white and black ever. There's a gray area. And that's where machine learning works on the concept of probabilities. It will say that there's 100% probability or there's a 70% probability that this is a dog and 30% probability that this is a muffin. That is a wrong model. You need to train it again, fine tune a few things so that it improves. Yes, that's the entire process. You need to be able to fine tune our model and it will always give you a probability. It will say this, I am 99% sure this is dog. I am 20% sure this is dog. So it is always one minus one game in machine learning, especially in classification. Just note this is it is always one minus one. Meaning, if you say that there is a 20% possibility that this particular thing is a dog, okay, then 80% of it is muffin. Correct? It is always one minus one game in machine learning. But the underlying concept is probability. It will never say, I am 100% sure. For anything and everything, it will always give you probabilities whenever you have these tasks as classification. Okay, cool. Let's go ahead. Yeah, this is another example of classification only. So now a curious or an interesting thing about this is that you see captcha, right? Whenever you try to go and log into some, a secured website or a portal, you get this captcha. They want to identify whether you are a human or you are this thing, a robot who's trying to, get to that data and try to, hack or scrape things. So you are labeling it as what is the fire hydrant. So you are labeling the data for them. Labeling of the data is the tedious task. People need labeled data so they can make these models. 90% of the things are supervised. But if there is no one who is labeling it, there's no use of supervised learning, right? It is as good as your labeled data. So whenever you go to the website next time, think it this way, you're not telling the website or you're not saying that, I am a human, let me enter. It is in fact you're doing labeling for them for free. You're doing labeling for Google for free. Okay, cool. All right, there are a few myths that we'd like to address. Now this I broadly touched upon that, artificial intelligence is a whole umbrella under which we have machine learning, and even niche of machine learning, a subset of machine learning is deep learning. Okay, so here you would say there are things like robotics, and in machine learning there are a few things that you can do with machine learning only, and there are a few things that you can use machine learning and deep learning both, but there are cases or instances where only machine learning will do better. You have a gut feeling based on experience. You learn over time, and you know for a fact that deep learning will do better here rather than machine learning. Okay. So an idea to that is, as and when you get huge data, as and when your data grows, okay, that's where deep learning is really powerful. It's really powerful and really better than machine learning. When your data is absolutely huge, humongous, then deep learning is what has the most chances of working better than machine learning. You can still do the same task with machine learning, but you'll get okayish results. Your model will be okayish. But deep learning, when the data is really huge, it will do wonders for you. Your boss and everyone will be very happy if you implement deep learning model, and perfect. Okay. So we'll touch on this one by one. So artificial intelligence is basically, I told you, no, just imparting a way of intelligence into a machine as a whole is a huge field. It's artificial intelligence. Okay. And then machine learning, which is a subset of artificial intelligence, is the ability to, train a machine to perform and learn without explicitly coding it. Remember, we talk about classical programming versus the ML approach, the email spam. If I have to do this in classical programming, if I have to write a code for it, program for it, I'll have to look for keywords in each mail and say that, okay, this is what it is. I am writing a code. It is really difficult to do that. And how many combinations will you keep at the end of the day? Correct? So that's where machine learning, you're giving the data, you're saying this is your label, and this is where you need to learn from it. And then once you are trained, once you are working good on my test data, now you're ready to go into the world and tell the world that this is spam and this is not spam. Perfect. Okay. Deep learning. Now, deep learning is slightly different than machine learning. Okay. Now, in machine learning, there are very little nuances that you have to take care of. Like when we were talking about the house prediction case. Okay. There are certain features. When I say feature, there are columns or information that are important for your model to predict. But there are some things that are not really important for deciding the price of the house. Number of bathrooms? Yes. Okay. Number of floors? Yes. Size of the house? Yes. It will tell you higher the size, higher the cost, obviously, right? Or not obviously, I don't know, depending on the locality. So you cannot say only one factor, but other factors also. Okay. If I tell you with all the house prices, if I tell you which agent is selling it, agent as in which broker is selling it, will that be of any value? Will it be useful in predicting the house? If I say person A is selling house A and person B is selling house B, will you be able to say that, okay, the person selling A house will be less price and B will be high price, or vice versa? Will you be able to tell? No. Why? Because that variable or that information is absolutely of no value for your model. If you put that variable into your model in training data set, your model is only looking at noise and is going to become corrupt. Okay, it will try to find some patterns unnecessarily. Deep learning, on the other hand, so in machine learning, you have to decide which variable, which information I need to put in my training. But in deep learning, in the other sense, is very smart. Why it is very smart? It works like a human brain. There are small neurons. These neurons are nothing but one simple nodes that are a part of an algorithm. It will process all the data that you have and it will automatically decide that you don't need person A, person B, agent data, agent information, or a broker information for house prediction. It will automatically do that. So this thing is selection of features and passing which feature or variable or information, which information is necessary for the model, which information is not necessary for the model, is called feature engineering or feature selection in machine learning. But that kind of concept is not required in deep learning. Okay? That kind of concept is not required in deep learning. So that is deep learning. It works like human intelligence. You have neurons which learn from each other. That is why for it to automatically tell that this information is not useful and this information is useful, for that to happen, you need to have huge data. You need to have huge data. That is why now you understand why deep learning is better for data where it is, really large, and ML could work on data which is even small or medium, say. I don't say that, deep learning cannot be implemented on medium data set. It can be implemented, but the effort and the the kind of results that you'll be getting between machine learning and deep learning are not going to be very different. Okay, you can make distinction between deep learning and machine learning. Okay, cool. Now the other myth: do you feel your job is under threat because of AI? Yeah, so this is a myth, guys. Trust me, this is a myth. I've been working on models like GPT. Okay, me myself have trained many models like Chat GPT. Okay, if you guys don't know Chat GPT, you should definitely know about it. Go back after this class, experiment with Chat GPT. But for those who know it, it is a kind of generative AI. Okay, it is dumb. There's no other way I can put it. It is dumb. It needs a human for it to tell this is right, this is wrong, this is where you're doing wrong, this is where you're right. Whatever you see right now is, if I have to give you an example, Chat GPT like models, right? If it breaks this myth, I would like to share this data with you guys. Chat GPT, I don't remember the exact count, but it was trained on data worth 2 lakh years. Imagine this. Imagine this. The data that a person, we don't live even for 2 lakh years. It was trained on a data which is worth of, 2 lakh years of data. If I start collating the data now or start reading or understanding the data now, it will take me 2 lakh years. Will I be even there till 2 lakh years? Humans are way more, understandable and way more intelligent. A kid of 12 years old, 10 years old starts to learn that, this is right, this is wrong. Only in 12 years, 10 years, 8 years. And after feeding in this 2 lakh years of data also to Chat GPT and other, Anthropic and Llama, all those things, they are still dumb. So trust me, guys, this is an absolute myth. Don't be worried. You need, you are required for AI to grow, not the other way around. Okay? You are never going to lose your job at least for another 100 years. I can give that in writing. But there's one condition to it. You need to be very, what do you say? You need to know how to use AI. That is one different thing. Okay? So you need to know how to leverage this versus, or use this versus worrying that, it is going to take my job. It is, I'm going to be replaced. No, that's not going to happen. I can give you in writing. Okay? That's not going to happen. It is not in the current state. It is not in that league. Automation is replaced. That's what. Automation is what? It's a robotic process, right? So all the grunt work, all the things that are repetitive in nature, it can be replaced. But you still, at the end of the day, you still need a person to look at it. You cannot blindly trust AI, right? So you need to know how to use AI, how to fine tune. You need to be expert in your field and you need to know AI. It's not that you can blindly give this thing. Okay, tell me one thing that if you're going into an operation theater, will you be comfortable a robot doing your surgery rather than a doctor? Correct? It has no emotions. It will do something, some stitches somewhere it has to put, and it will put somewhere. And it is emotionless. It will not be very soft or gentle, a robot. And things can go haywire. So we are really at a stage which is very far, okay, from us being replaced. Okay, all right. So we covered types of machine learning, supervised, unsupervised. Okay. Now, The other thing is, before we move on to other things, I want to capture a few examples that are in the PPT. Okay. And yes, this is something that I would like to touch more in detail, which is AI versus machine learning and deep learning. You know what? Let's do this. Let's do this. Then I think uh, we have everything that is there in PPT. Okay. Now, what is the concept? This is your AI. Okay. This is your ML, and this is your deep learning. Okay. Now, artificial intelligence also has a field of robotics, correct? Any slight intelligence that you put in is called artificial intelligence. Okay. Whereas machine learning could be unsupervised learning, could be supervised learning, and the third type that we have to discuss in detail is reinforcement learning. Correct? Okay. Now, deep learning is also same, but it has a few additional things like NLP, like video, Gen AI. Okay, so let's try to divide. AI is a broader field within which ML is a subset, and deep learning is even a subset, a very special case of machine learning. Okay, let's discuss what is the difference. So if I say I have ML here, okay, and I have deep learning here, okay, before we go into that, what all type of data can we have? What data do you see around you? I'll give you one example. Text data. Okay. Let me write this. We are going to be data scientists, machine learning, data engineers. So, okay, let me write a few examples so that you get to know. I have text data. Okay. I can have video data. I can have image, audio. Perfect. Image, audio. You have done clustering or classification here. Rather, you have done classification here. Why? Because there is no other type of data that you can get. Think, each and every type of data can be classified into one of these categories. Either it could be textual data. Okay. When I say text, number, and all those things. Okay. Or either it could be video data, because video is slightly different, image data, and audio data. Audio is kind of your signals, frequencies. Okay. Now, there is another nuance to it. Okay. The other nuance is, though we know this data, there are two types. It could be structured, okay, or it could be unstructured. When I say structured, what is that? It is a tabular data. Okay, whatever you get in a table format is tabular data. It is structured. It doesn't mean that you can skip data cleaning. You can skip any part of it. You can skip outlier treatment or missing value treatment. We'll touch upon that, but you still have the data in a format that is structured. But is there any structure in video? Is there any structure? Image, right? Audio, and a special category of text, which is natural language. If it is written, if it is spoken, whatever, any case of textual data which is in the format of natural language, how we speak, how we interpret things, is unstructured. Everyone, this is really important for us to understand deep learning and machine learning. We understood AI is a huge field. Okay. Within that, there is a small part which is ML. Okay. Which is this. And then within that, we have a few things like we have AI, we have ML. Okay. ML has unsupervised learning, supervised learning, and reinforcement learning. And then we have deep learning, which is working on NLP, generative AI, some of the features or some of the implementations I'm talking about. Okay, like image processing, identifying which image it is, digit recognition, whether it is one or two, okay, five or a four, all those things. That is under deep learning. So at the end of the day, everything is about pattern, finding patterns. Okay. Now, I asked you here, what are the different types of data that we get in our real world? Okay. Not data types of a variable. Okay. But the kind of data that we can get. Okay. If this is confusing, let me change it to kind of data available. Okay. In the world, what is the kind of data that we have? It is either structured, correct? It is either structured or it is unstructured. When we say unstructured, it is when we say structured, it is tabular data. Okay. And unstructured would be that, there are so many things which a computer cannot understand or your software cannot understand, but we as humans can interpret it. You're watching this video, right? You can interpret this. But how will your system, how will a machine understand this? How you are able to understand is through your brain, through your neurons. But your system doesn't understand what is a video. The way the machines talk or they understand things is in terms of binary, in bits, in zeros and ones, in numbers. They don't know what is K, what is A. Here with me at a very grassroots level. So unstructured data is that data which we can understand, but is not in a tabular format for or for the machine to understand. Okay, it is unstructured. It has to be structurized. So that is video, image, audio, and natural language. Give me an example of natural languages. The thing that I'm talking now. Okay, if it is okay, a better example would be you go to doctors, they write prescription, right? Whatever that you have, does it have any format? Is it in a table? Can you directly pass it into a software or into a machine and say that, okay, tell me what all, this was my, when you go to doctor, on top they write, okay, this is what the complaints are, and at the bottom they write, this is my medicines. It could be one medicine, it could be 10. Correct, there is no structure. Can you directly pass this language to your system, to your machine, and say that, okay, tell me for these complaints, 100 patients, I'll give you data for these complaints, can you tell me which medicine should I take? No, right? Machine cannot interpret it as as we can interpret it. We have to do some things. That is natural language. Okay. So now the other question is, now this is kind of data that you have. The differential between ML and deep learning is really easy. Very easy. Okay. I told you one thing, that ML works good on small data, right? Or medium. But deep learning can work on medium data also. But the effort that you have to put, the price that you have to put for a deep learning model on a medium data will not be worth it. You might get a 0.001% improvement, or even 0.1% or 1%, 2%, depending on what your domain is, right? You might get that much of improvement, or you might get deterioration, or it might be exactly the same. But the amount of money that you'll be spending on putting deep learning there, because deep learning runs on GPUs, it needs additional processing. So that's why we prefer this on more data or large data, huge, humongous data. Whenever it is there, deep learning Close your eyes, go to deep learning. Okay. The other thing, why, what is the difference between ML and deep learning? It is feature engineering. Or before that, now tell me, since we've studied this already, I'll tell you, and then we'll talk about feature engineering as well. So here, uh, you can work on structured data and you can work on unstructured. Understood? That is why I wanted to clear this thing. What is your unstructured data? What is your structured data? You cannot use video as it is for your machine learning. Deep learning is a better bet for image processing, for audio processing. Deep learning is better. Machine learning will only understand numbers. There are no features for you to play around with. Deep learning is your bet. This is one of the reasons why deep learning is gaining traction in the market, because machine learning can work only on tabular data. Most of the companies, they have tabular data only. They have records, they have, sales, they have stocks, all those things. But as and when we are now producing so much of data, people are producing so much of data, data is now being accumulated in unstructured data as well. We are having videos, we are having images, we are having audio, right? And also earlier we used to not have those capacity of running. We did not have GPUs. We did not have, these big databases, data warehouses to store the data. Now we have them. That's why your deep learning is gaining traction. And very clear distinction. Now you can confidently go and say that, okay, this is where I will apply deep learning. This is where I will apply machine learning. It is very clear now. Okay. Whenever the data is unstructured, whenever the data is large, deep learning. Whenever the data is small or medium, but has a structure to it, prefer ML. Okay. Okay. Now let me touch upon feature engineering. Okay. And with that, the other difference is the third difference, which is feature engineering is required in machine learning. Okay. And feature engineering is not required in deep learning. This is the third example. We'll touch this in detail now, but keep this in mind. Feature engineering is required. You have to do it in machine learning. In deep learning, there's no need. It will do it on its own, and you'll understand why it does it on its own. We'll connect everything. I will connect everything for you. Okay, cool. Now let's talk about feature engineering. So this is feature engineering. Okay, what is feature engineering? Let's try to understand our data set better. Okay, no one will tell you. So guys, this is something that is very standard in the industry, but no one teaches it. No one teaches it. And you understand it, but your understanding is kind of convoluted between these other things. Okay, so understand this with absolute attention. Okay, move away your phones and move away from the reels that you're watching. Okay, cool. Now for understanding the data, this is how you get the data. Correct? You have many columns, and there is one target variable. Okay, this is your target. Mostly this is how you get it. Okay, so how do we define this? Now this is your output. Okay, or label. This is called label, or it is also called target. Okay, this is called your features. This is called your features. or your variables. Okay, all the information that you want to do is called that. Let me try to explain this with an example now. Okay, our house prediction only. This is your price. Okay, this is your area of the house. This is your number of bathrooms. This is your locality. Okay, this is number of floors. Okay, and what all other things. Okay, so these are your features, everything in the blue, and red is your target variable or your label. Okay, and now pay attention, guys. Pay attention to this. This is xi. Okay, this is one instance. What is this? This is one instance. It is also called a data point. Okay, everything in your features, in your variables, one single row xi is, and all the features in coding and everything, a standard practice is you represent your features with x. Okay, and your target variable is y. Okay, this is a standard nomenclature that everyone follows. So whenever you go ahead and even read some of these PPTs, and also if you're reading on the internet or looking at someone codes, this is very standard. Okay, that's why I'm trying to clear this standard. Okay, cool. And this is yi. For ith row, this is the actual output or actual value. Okay, for ith row, I'll write this ith row. Keep this in mind. These are very small things. No one teaches it, but they're really important for you to understand all the following, concepts. And even when you're looking at some of the formulas and everything, it will be very clear. Okay. Now there are other, terminologies or some this nomenclature or as well. So whenever you have yi, okay, it is actual value of ith row or ith data point. I hope that is clear. Okay. And this is how they say you put this, cap on top of it. You must have understood this in maths, somewhere. If not, but trust me, you don't need more than that of maths. This is y cap. That's how they call it. And this is so that you can distinguish between actual values and predicted values. This is your predicted value. Okay, of ith row. Okay. Now, feature engineering is what? Feature engineering is what? Now, let's say one of the feature that was given to you was broker name. Broker name. Who is showing you that house? Okay. Where, or is the broker, if you're selling a house, a broker is a person who is middleman, who takes commission from both the sides. If no one knows that, okay, he is responsible for selling it. Now tell me one thing. Do you need the broker name? Will it have any information or will tell you to decide the price, to predict the price of the house? Does it have any value? If you pass this to model, let's say Amar is selling one, Akbar is selling one, Anthony is selling one. Does it tell you anything? No, right? It is a useless feature. So the act of you deciding that this feature will not go in the model, this feature will not go in the model is feature engineering. The act of deciding which feature to pass to model, okay, is called feature engineering. Okay, there is another thing to this, which is you can create additional models also, additional features, sorry, creating additional features. How is that? Let me give you an example which everyone can understand. Okay, let's say you have this thing where you have to predict the age, right? Age. Now you are given this problem statement that predict age. Okay, so you are given what? You are given height of the person and you're given the weight of this person. Based on that, you can guess the age. Okay, simple, very simple. But what you can do, there is something called as BMI, body mass index, correct? It is some combination of, if someone can tell me, it is something, height over weight square or something like that. There is some formula for this. So it is a calculated field, calculated field, which takes calculated field, which takes both height and weight inside it, correct? Okay, so this is your calculated field. So this is a new column that you're creating. Okay, so you have, either you can pass both of them, or you can pass all three of them, or you can pass only BMI to predict the age. That process of modifying your features, adding, creating, deleting, all that thing is called feature engineering. Okay, and now we can also understand this point again. So in machine learning, you have to do this. In deep learning, it will automatically do that. If you have 30 features, 30 columns, 30 variables, and only 5 of them are important, you have to do that selection in machine learning from 30 to 5 based on certain techniques. You need to come from 30 to 5. We'll talk about those techniques, what it is, but logically understand this. In machine learning, you have to come from 30 to 5. In deep learning, it will automatically come from 30 to 5. So feature engineering is required in machine learning. In deep learning, it's not required. All right, cool. Then let me take this question. What is categorical and numerical? Okay. So now you know that in this format that I told you in the above, okay, this is one of your feature. This is one of your feature. We've understood this. It is also called a variable, right? It is also called a variable. Now, these are its type. One feature ka category or numerical. That feature is either numerical or categorical. When I say categorical, it will have discrete values. Okay. It will, example would be if you have a column saying gender, okay, male or female, correct? Right or wrong? If you have a feature called fruit, It could be, in our example, apple, orange, or banana. Just be careful here, guys. Here we are passing this as a feature. We are not categorizing it. Whenever you have categories, right? That variable, when it is in feature, is called categorical feature. When that same categories go into your label, you have to do classification. Understood the concept? Why it was necessary to distinguish between this and this, right? When you have categories in your label, you have to do certain tasks like classification. You have to say, okay, this is yes or no. It is email is a spam or non-spam. Correct? We looked at that example. That becomes your, that will give you a hint of what type of model you have to put, what type of learning you have to do. But when it is on the other side, when it is in your features that you have to use, you have to handle it differently for your model and data cleaning. Okay. Okay. Cool. And this numerical is any continuous variable. Okay. Any continuous variable. Now, our example here was area of the house. Okay. Area of the house. Then what else? In our above example, it was weight. Okay. And when this continuous variable comes into your red part, which is your label, when it becomes label, it becomes what kind of problem? That will give you an idea what kind of problem you have to do. You have to do either regression or you have to do forecasting. Forecasting you will do only when it is time based. You can apply forecasting there. Okay. I hope this is clear. So what I'm saying is we understood here that this is the terminology that we understood here, right? Everything on the left is your features. Okay. And this one is your label. Okay. And then that's the only thing that you need to remember as of now. Now, there are types of variables. Okay. Types of variables, or they are also called data types. But I would like you to understand it type of variables. Okay. Now, variables are what? Everything that is on the left side, which is in this blue line. Okay. These are variables. And for one column only, we are talking about this. If this column, which is your variable, is categorical, meaning it has only few entries in the row. Example, it could be the owner is male or female. It is a gender kind of a feature or a variable. Okay. Number of bathroom could be categorical, right? In our previous example, number of this thing, bathroom could be categorical. You could have 1, 2, 3, 4, 5, 6, right? Here with me? Locality also could be categorical, saying that locality is Adarsh Nagar, locality is Yalanka, model town, only 3, 4 or more than that. You can count it. It is discrete value. Okay. But whereas continuous variables or numerical variables have continuous value. It is continuing 1, 2, 3, 4, 5, 6, 7, 8. There's no end. So your area could keep on increasing. It could keep on reducing. Okay. Weight could keep on increasing. Height could keep on increasing. It can take any value. It is not that it will take only, integer value or only limited number of values. Okay. Continuously changing as in it could take additional value. Any other value. There's no limit range that it will take only 1 or 2. All right. So I think we've covered this. Now, ML, we know, is of 3 types. We've understood supervised learning in detail, correct? We've understood unsupervised learning in detail, right? There's one thing that I told you that we will touch in detail is reinforcement learning. ML has three parts: SL, UL, RL. SL stands for supervised learning. We've looked at it in detail. UL is unsupervised learning, looked at it detail. RL is reinforcement learning, which we will look at now. Okay. Now, reinforcement learning, I will first explain it from the PPT, okay, which I feel has a good example, really good example. Let me show that. So we've covered this AI versus ML versus deep learning. AI is not taking your job. I told you yesterday also, it is really dumb. It is trained on 2 lakh years of data. Human people, small kids with only 12 years of data, 10 years of data, they know what is right and wrong. Okay. Is not going to take your job. Supervised learning, we looked at it. Unsupervised learning, we looked at it. Now let me go back to these are examples, okay? Apple, banana, email spam, and clustering of these. We've covered all this. Voice-based assistance, Netflix recommendation. This is where I want to talk now. Okay, reinforcement learning. So reinforcement learning, in fact, is better to be explained with this. So if you have seen a dog being trained or a cat being trained, whenever there is two things: before conditioning and during conditioning and after conditioning. Okay, stick to this word. Conditioning is meaning that you are in the process of doing something. Okay, you are changing something. That learning in machine learning, that learning is conditioning. Imagine it this way, understand it with this way. So before learning, okay, what used to happen is when you put a food in front of dog, the saliva will start coming in. It's a response to stimuli. This is his response by looking at food. It feels hungry. Okay. And whenever you press a bell, you say that, okay, bell is ringing. It has no response. It has no absolute no response. The dog will feel like, why are they ringing bells? Are they gone mad? Okay. But during conditioning, meaning during learning, when the dog is being trained, what trainers do or what people do, okay, when they condition a dog, they say that whenever I ring a bell and I will give you a food. They do this 10 days, 12 days, 13 days, 100 days, whatever. Dogs are very smart. They learn it very quickly. But what they're trying to do is in the learning, they're trying to associate the ringing of bell with the food. That's what they're trying to teach the dog. Okay. They will, every time they bring the food, they will also ring the bell. Every time. This will happen for a few days. Then after, that is conditioning. That is conditioning. After conditioning, what happens is whenever you ring a bell in front of the dog, you will get the same response of saliva coming out. Meaning it thinks that for the last 10 days, 12 days, or whatever X number of days, whenever the bell used to ring, I used to be served food. So it will have the same response by listening at the bell as it used to have for looking at the food. Okay. So this is after conditioning. You are reinforcing something in the learning. Okay. You are reinforcing that ringing of the bell is associated with food for the dog. Okay. The other thing, let me now go back and explain you next example and we'll connect. Imagine you have a maze. Okay. And your goal is you have a toy car. Start to end is what you want to go. Okay. That is your goal. This is the start and this is the end. Okay. And let us make us more interesting. So if Lena and Anvesh are friends, okay, and Lena says, I am building a toy car, okay, that can run on its own, that can drive on its own. And Anvesh is Leena's friend and says that, okay, how can I help you? So Leena says, build me a maze on which I can train my car. Okay. So Leena says, build me a maze on which I can train my car. So Anvesh, being a good friend, he builds a maze. Okay. I hope you guys know what maze is. Okay. Something or the other. Let me show you what a maze is. Maze image. This is a maze, sorry. Okay. You start from here and you get to some other place. You start from here and your goal is to go here. Okay. So what happens is this is an absolute gem of a maze that Anvesh has built. Now what happens is Leena says that, okay, I will not look at the maze because I want my car to learn autonomous driving, to automatically reach from start to end. Okay. Let's open the space here. I've made a closed maze. So when the car goes here, okay, this is the car. When the cars go here, since there is no remote control, nothing, it will first crash here, right? And then it will try to go here. And then again, it will crash here. Then again here. And ultimately, it will try to go out of here. Correct? You are with me that it will first crash. It will not go on its own. Correct? Perfect. Now, reinforcement learning is this concept that listen to this very carefully, guys. If you're able to understand this one example, life is set. Reinforcement learning is done. Okay. So, what Lena has done is she has given points to its car, or rather, Anvesh and Lena, they are tracking whether the car is good or wrong. They have given 100 points to the car. Every time it crashes, it is given a penalty of minus 10 points. And every time it takes right turn, right as in correct, it could be right or left, correct turn, it is given plus 10 points. Okay. Now the model is such that it will try to optimize this number. It will never try to reduce this number. So it will try to avoid crashes, correct? And try to gain as much as points that it can. If it crashes also, it will try to gain 10 points by making a right turn or correct turn. Okay. Is that clear? Similar to the dog example, similar to kids example, you're given toffees, chocolates for good things, cold drinks for bad things. Similarly, this is reinforcement learning. Okay. And there are certain terminologies to this. Let me put that in perspective as well. There are certain terminologies. Now, this yellow maze is called environment. Okay. This entire maze on which it is learning is called environment. Okay. And this car which is learning is called agent. Agent Vinod nahi. Not agent Vinod. That's not the agent that I'm referring. Is the agent. In this case, it is car. Okay. To whom we are asking to learn. Okay. Then we also have goal. This goal I have already told you. This is the goal. Move from start to end. Okay. This is what this slide talks about. Okay. This is your agent and the environment. In our case, the maze was the environment. What it does, it observe. If it crashes, it gives you 50 points. Okay. And this is your reward and penalty, plus 10 and minus 10. Action is basically whatever happens, if it crashes, you have to update the policy. In that case, they are calling it policy. So this is your action policy, meaning you decided it will be plus 10 or minus 10. Plus 10 for correct turn, minus 10 for crash. That is your selection of using policy. Okay. Then action, meaning actually whenever it crashes, minus 10 and takes the correct turn, plus 10. That is your action. And after every action, you update the policy based on reward or penalty, meaning 100 become 90 or 90 becomes 100. Okay, based on crash or turn. Perfect. And iterate on this entire process. Now, once Lina and Anvesh has successfully made this car or agent learned, it can now go and do the same thing for any number of mazes in the world. And they have made an autonomous driving toy car. You train it only once or twice on the environment, depending on the case. This is the concept that your autonomous driving class cars are also following, or in other words, it's also called driverless cars, right? This is the concept behind that. Okay. The other thing is that reinforcement learning, guys, is very research oriented. Okay. In my experience, if your company is into research and development, or if you're looking for PhD, this is important. Okay. Otherwise, if you do supervised learning and you do unsupervised learning, meaning coming from machine learning or deep learning, this is what your jobs will require you to do. 99% of the jobs will be this. Okay. So understanding reinforcement learning at a high level and understanding what is happening is important. That can be asked. But on the jobs, I'm coming from experience, I'm talking from experience. There's hardly any use case that you'll be working on. Yes, if you work for a company who's working on autonomous cars, driverless cars, then you would need reinforcement learning there. Okay. Now, what we're going to do is a really cool stuff. We're going to do something really cool. What is that? Yeah, this we have done. Okay, so let me just close this introduction thing. So if anyone asks you these kind of questions, can you clearly and confidently say it is a machine learning problem? One, and what type of machine learning problem? Okay, that's that. And then, yeah, these are some examples. I think we've covered most of it. Okay, we've covered more. Anomaly detection is nothing but fraud in transactions, anomaly that is out of the order. Okay, enough of this thing. Let's get to something that is interesting. Okay, now there's also one um, assignment that I would like to give you, a homework, which is you need to go to the internet, okay, and tell me what is semi-supervised learning. Okay, now we are going to do something which is called linear regression. Okay, so this is where everyone starts teaching or starts learning. This is the basic thing in machine learning that you need to know linear regression. And trust me, guys, I will teach you in first. This is how we are going to do. We will look at some of the theoretical concepts. Okay. We'll be doing that. And then we'll be going into practical or hands on approach. This is how we are going to learn every concept. Okay. Why theory? See, to be honest, all of us, we don't we don't like theory that much. Practical is where everything happens, and our brains open. We have a minute to minute understanding of things. But trust me, the theory that I'll teach will be in really interesting format. Okay. You'll not feel like you're learning theory. Okay. And we'll only see what is important, what is required, and whatever I can cover with the practical hands on knowledge, I will do that without compromising on the quality. Okay. You have to trust me on that. Okay. You have to trust me on that. All right. This is how we'll do it. Okay. And trust me, I am going to teach this in a manner that you will not feel like you have, done something a lot. You'll feel like, yeah, this is so easy. This is so easy. Okay. We'll do it that way. Done. Okay. So now, before we go into linear regression, okay, we briefly touched upon what is regression, right? We know what is regression, house prices, prediction of that. Okay. Then your salary prediction, meaning it is continuous variable, or your output or your target variable is continuous. Okay. Output is continuous. And then we need label, of course. In label, here we call it as target or label. Okay. This is regression. Now, essentially, regression is nothing but it essentially what it does is, how are we predicting these? How are we predicting these? It is trying to find relationship. The word that I told you to keep in mind for machine learning was finding patterns. Okay. Regression is, in those patterns, you're finding relationships. Okay. You're finding relationships. This is the keyword. What are you finding relationship between? You're finding relationship between your target and your features. Now, when I write features, everyone is clear what I mean by features and target here, correct? You are trying to find relationships between your target variable and your features. Okay, cool. Keep that in mind. That is that method, that type of learning where you're finding relationships is called regression. Now, regression could be of two types. Okay. Topic is linear regression. Okay. Linear regression. Okay. But there could be something called as non-linear regression as well. Okay. Based on this relationship word that I told you, what is linear and non-linear? Okay. All right. Let me say. Okay. So whenever, if you replace this regression with relationships, it means linear relationships and non-linear relationships. Instead of regression, if you choose this word that I'm telling you, that you trust me, say that regression is relationships only. Okay. For our understanding, this is not the formal definition, but for our understanding, we need to be first clear, then we can, pick up all the formal jargons and everything. So when linear regression means, it is a linear relationship. When we say a linear relationship, it is this. Okay. So as and when this is your age, sorry, this is your salary, right? Okay. And this is what you are predicting here. Okay. And you have only one feature. You have only one feature here, and that is experience. Okay. What do you feel will happen? As your experience increases, your salary increases. Is that a fair relationship to keep in mind? As experience increases, your salary also increases. Is that fair to assume? So the relationship here is linear. Okay. It is linear. So what I'm trying to do here is I'm trying to plot all the people here. What is this yellow point here? It is people in data set, in our data set. Okay. And what does it explain? This tells me the experience of this person. Okay. This person's experience, this x-axis tells me, and the y-axis will tell me this is the salary of this person. Correct? Everyone with me? This basic we know about the graphs. Okay, cool. All right. So now when we have linear regression, okay, when we have linear regression, you see this is a linear relationship. I can fit a line here, which is straight line. Okay. I can fit a line which is straight line. This is your linear regression. Okay. Whenever there is a linear, a line type, focus on this word. In linear regression is only telling you it is a line type. And regression, I have solved it for you. Regression means relationship. So when there is a line type relationship, linear relationship is called linear regression. Okay, perfect. Now, now with this, what is nonlinear relationship or nonlinear regression? Okay, whenever your data is like this, okay, there is no pattern here. It is not something that is, you can say that it is linear. It is all over the place. Correct? Let's say this is y, this is x. Can I fit line like this? No, right? So the best fit would be something like this. Okay? This is non-linear relationship. Okay? So what we are going to study and what everyone studies is linear regression. And this is what is the basic of machine learning. This is the utmost minimum you should know. Okay. Now let's get into the details and see what actually is linear relationship or linear regression. Okay. What is there in linear regression? Now let's take an example. I told you this is theory, but we will try to do it with examples. Okay. Now the problem statement is that you have to predict the price of the second hand car. It could be, something like Cars 24. Everyone knows what is Cars 24, Spinny, etc. There is a person, okay, or there are so many people who want to sell their car, okay, but Cars 24, okay, Cars 24 and Spinny, they are those companies which buy these cars from the people in the second hand market. So let's, for example, I have one car. Okay. I want to sell it for some reason. I don't know where I can sell it to some person, right? Who I know, who contacts me. But a good chance in today's world, in today's India, what is happening is companies like Cars 24 and Spinny, they have opened their shop and I can straight away go there without, waiting for a response on OLX or eBay, something like that. Or if there is no one in my relation who wants to buy my car, I can directly go to Cars 24 showroom, Spinny showroom, and say that, guys, this is my car. I want to sell it. Will you purchase it? Now, let me create a data set. Okay. This is the data set that we'll be using to understand the entire concept of linear regression. Okay. Now, let's say this is the data that I have. So what all we have? We have mileage, right? We'll have mileage. We'll have the age of the car. Age of the car. When was it bought? Correct. We will have the manufacturer of the car. Correct. Mileage is nothing but average. ठीक है? We Indians, we love average. Maximum average car is the best car. But there are a few who like Ferraris. They don't absolutely care about average. Okay, it's 0 or 1. Either we will want the one with best mileage, or we would want one that zoops goes 0 to 100 in split seconds. Cool. And the other would be engine. Correct. And let me put this in a different color. Let this be the price. Okay. Now we know what is this. This is your features. Okay. And okay, let me first clarify this. And this is what? This is your target. Okay. In linear regression, okay, this is also formally defined as something else. All the features are called independent. Independent. This is also called variables, right? And this is also called target variable. They are independent. And this one is called dependent. Why is that? Now you're finding a relationship. Okay. You have to find a relationship between dependent, one who depends on something, and independent, meaning your target variable with your features. In other words, if something is dependent on some other thing, then only you can find the relationship. No, if they're independent of each other, what will be their relationship? Correct? Everyone with me? Everyone understands this? Features are also called independent variables. Target variable is also called dependent variable. Okay. I'm keeping it this for now. Okay. I'm keeping only this. You can add in as many features as you want. Now, let's say the mileage is 20. Okay. Age is meaning the car is already 8 years old. And manufacturer is, let's say, Maruti. Engine is 1000 cc. Okay. And prices, let's say 5 lakhs. Okay. Whatever. Then 5 lakhs seems to be too much, but okay. This is example for an 8-year-old car, which is 1000 cc only. And okay, the average is 12, age is 7. Okay. And it is, let's say, Hyundai. and it is 1200 cc. This is, let's say, 4.5 lakhs. Okay. Then we have another, which is, let's say, the mileage is 9 and the years is, it is only 3 years old. This is, let's say, Kia. This is 1500 and this is around 10 lakhs. Okay. And so on. I just wanted to give you a glimpse of the data. Okay. This is how it is. Now, if we have to understand linear regression, okay, now if you look at it, your task is to consider all these columns 1, 2, 3, 4, okay, to predict your price. You're given four variables, four independent variables to predict one dependent variable, which is target variable. Okay. Now it is your choice to either take one of them or take two of them or three of them or four of them. Your choice, but your choice will be driven by some mathematical functions. Okay. Some mathematical concepts, but at the end, it is your choice. And that choice, that, act of deciding which feature to put in, which feature to not put in, to create a new feature, that is called feature engineering. Correct? We just studied it. It is feature engineering. Perfect. So now I will start very simply with one feature as of now. Okay. I will write also. Considering only one feature. Okay. Or let me say one independent variable. Okay. We are going to look at only one feature now. And I am choosing it to be age, since it is very easy to understand. Because as and when the car gets older, the price goes down. Okay, everyone understands. As and when your car gets older, it is supposed to it is supposed to have low price. Okay. Now the other funda in this, the other thing while plotting this, we would have studied this earlier also in school, that whenever we are plotting, okay, we have independent variable as x-axis. Okay. And we have dependent variable on y-axis. Okay. Keep this in mind. So whenever you're creating a graph, this is a very novice mistake that some people make on the job and also during interviews. So always keep it in your mind that independent feature, independent variable will always come on x-axis and your dependent variable will always be on y-axis. It's not something that is told, but it is something, which is intuitive to humans. We can understand a line flying. We, with respect to y-axis, when you have a graph like this, with respect to y-axis, it is visually, or to the eyes, it is easy to understand. Okay. That's why we put it like that, and that's why we are even taught in our schools also like that. Okay. That's the logic. You can do ulta also. There's nothing wrong in that, but this is how I would prefer you guys to do it. Okay. And that's how even people in the industry prefer it. So now, if we have to create a real, let's plot the data. Considering only one variable, and I will consider age. Okay. I will consider age. So now in my data, I will have only one, which is age, and I will have price. Okay. So the first example was 20 and this is 5. This I am putting in years. This I am putting in lakhs. Okay. So I am removing this L here. Okay. Cool. And the other one was, okay, 8, 7, 3. I'm just trying to copy 8, 7, 3, and this was 4.5, and this was, I think, 10. Yeah. And there are few more. Okay. There are few more. It is 4, and this is around 3, and it is, 5, it is around 6. Okay. Now there are a few exceptions here, right? There are a few exceptions here, right? This one. It is only 3 years and it is 10 years, 10 lakhs, correct? Because others are in the range of 4, 5, 7, 8. Okay. But anyhow, we will still consider it. You are not going to do anything with it since this is a dummy example. Okay. Now, when I try to plot this, don't you think I'm not considering the numbers, but you get the idea of it? Don't you think this will be your age and this will be your price? Okay. This will be your price. Lower the age, higher the price, correct? Then lower the age, higher the price, lower the age, higher the price. Then as and when your age increases, okay, the price will keep on coming down, correct? There might be some outliers as well, correct? Is that fine? As age increases of your car, the price will come down, correct? So this will have a relationship like this. Is that fair to understand? Okay. Now, instead of age, I take average or mileage. Let me do that here as well. I am doing this for mileage. This one was for age. Okay. This is your mileage. And this is your price. Now, what will this relationship look like? Same as age, correct? Okay. So now these type of relationships, okay, where it is, age is increasing. This in terms of line, this is having a negative slope, correct? It is moving like this. It is a negative slope, correct? If you have a graph like this, where a line goes like this, it will have a positive slope, correct? So this is negative slope and this is positive slope. Everyone understands this? Okay. So now why I spoke about slope? Do you know why? Do you know why? We have linear relationship and it is a form of a line, correct? And the way how you can define a line is nothing but y is equals to mx plus c. Okay, this is your slope. This is your intercept. Okay, this is your independent variable. You see how y is dependent on x. That is why it is your independent variable. Okay, and this is your dependent variable. Okay, how y is dependent? Okay, look at this. Now y is being defined. You can get the value of y if you put some value of x here. M and c are going to be constants, correct? For a line, this is some slope of it. Let me explain it separately. For a line, okay, this is the slope of it. It is going to have some fixed value. It is going to be fixed, correct? And this is the intercept. This is the c value. This is also fixed. Okay. Now to get any y value, on the y-axis, if you keep replacing some value of x here, you will get the corresponding y value. Correct? Similarly here, if let's say this x is equals to 5 and you plot it here and then you project it on y-axis, you will get the value of y. Correct? Y is defined like y is equals to mx plus c. In other words, if you have to, understand it this way, these are mathematical functions. We always say y is equals to f of x. Correct? It means y can be explained or defined as a function of x. Okay? There is some function, you put some value of x here and you will get value of y. Okay? So this is also nothing but a function of x, or function of x which defines y. That is why it is dependent. It is depending on your x. And didn't I tell you that in industry we keep all the features as x and all the target variables as y, right? What is intercept? Wherever your x value is 0, x is equals to 0, and wherever it crosses your y, that is your intercept. Without any value of x, you will have minimum this much of amount. In our car example, okay, no matter what, you will at least have to pay 1 lakh rupees. This is your intercept. Okay, at least you'll have to pay. If even if it doesn't have any engine, it doesn't have any manufacturer, it doesn't have any mileage, and you have to sell it, and cars 24 are bounded by purchasing it, they will still purchase it. If 1 lakh seems to be higher, let it be 50K. I'm just, for simplicity, for calculation, I'm saying 1 lakhs. It is the cost of scrap that you'll be getting. I'm just relating it with the example, but it's like if there is nothing, at least we will see this value of the target variable or dependent variable. Okay. Okay. So this is Desmos. Okay. Now here, let me add a few values here. Okay. Let's say we had 4 and 5, 8 and 10, 6 and 12, and this is 5 and 13. This is 1, 3. Okay. These are your data points. These are your data points. Okay. Now, linear regression is what? I want to put more examples. Let me, at least we will have something to talk about. Okay. So let's say this is what we have as an example. Okay. I'm not telling you any linear regression concept. I'm just telling you an example of this thing, line, how lines look like. Mx plus c. Okay, why is it going there? This is the equation of the line, correct? This is the equation of the line. Okay. Now we have a basic thing set up, correct? So now let me play with this. Let me try to see changing c. You see it is negative. What happens when it is negative? It touches your line, or it cuts your line when x is equal to 0 at a value which is negative. Okay. We still have the slope as positive. Positive mean 1. Correct? So we understood that the positive will look like this and negative will look like this. Correct? So if I keep on decreasing it, you see how if I keep on changing the value of c, is the direction of the line changing? It's just that where it is moving on y-axis is changing. Correct? Correct? Okay. Now let's see. Let us put it to 0. Now this 0 meaning it is still it could still have a linear relationship. Ignore the points here, but if there is a linear relationship, it could still have that linear relationship, but when x is equal to 0, y is also equal to 0. Okay, that is when c is 0. Now, if I change my m, if I change my slope, how do you think the line will react? Let me make it more positive. You see, is it ever crossing this line? It is still in this. It is moving, like it is rotating. It is but never coming like this. Okay, this is for all the values of m. And if I make it negative, you see how the rotation has changed. When I am at m is equal to 0, it overlaps your x-axis. Nothing but m is 0 means there is no slope. So it is x-axis, correct? Now if I make it negative, you see how it is changing. Now it has become this, correct? So lines can take any value. Lines can take any value on that plane. You can keep on changing your c, you can keep on changing your y, and you can have any combination of this. So m and c can take any values depending on the relationship. Is that clear, guys? C is the intercept where it touches y, or the value of y when x is equal to 0. Okay, that is the definition of C, or intercept. M, which is slope, is nothing but it is the slope at which the line is. Formally, it is the change in y divided by the change in x. If you see this, okay, if you see this triangle, this is the change. If I have to get the slope, I will see that the change is this much and the change on x-axis is this much. It is the slope. Okay. So basically what happens is, in linear regression, your motive is you need to find values of m and c such that you get the best line. Okay, keep this in mind. We will come back to this. We need few more other concepts to understand this, and this is best line. Best line is one that will perfectly fit your data. Keep this in mind. Okay, for now keep this in mind, that best line is that will fit your data to the best of its ability. Okay, now we will go into what is this best line. What is this? Okay, now what happens is, let's take this example again. Let's take this example. We have all these points. Okay, we have all these points and you are trying to fit a line, correct? Why not this line? How do you say which is better? Okay, what about this line? Okay, now I'm telling you, you have these options. This is line number 1. Okay, and this is your line number 2. This is line number 2, and this is your line number 3. Tell me which is the best line, which identifies the relationship between your data sets really well. So there is some confusion between 1 and 2. Some confusion between 1 and 2, right? But there is absolutely no confusion about 3. This is worst. Correct? Everyone understands this? This is the worst line. ये तो हो ही नहीं सकता. It cannot happen. Everyone with me? but we are confused between 1 and 2. 1 or 2. We don't know. How will we know? How will we know? We'll know about it by checking the errors. Okay? By checking the errors. Now, when I say error, what do I mean by error? Okay, let me take another example to explain this first clearly. Okay, let's say this is your data set. Okay, now I'm doing this with a positive correlation, or sorry, positive slope, so that it is easier to explain. Okay, the same thing applies for the negative slope also. Okay, now this is my line, for example. This is the value of, this is one line that I feel can fit my data really well. I don't know yet. I don't know yet. Okay. Now what happens is, what I say, that every point on this line is the prediction, because my function is mx plus c, correct? Whatever value I put in x, I will get the value of y. Okay. Let's say this is 1, 2, 3, 4, 5, 6, 8. Okay. 1, 2. Okay. This is the graph. Now, for this point, the one that I'm highlighting. Okay. Do you see that it is far from this line? Correct. And this one is also far from the line. This one is also far from the line. But this one is, the red line here is really small. The red line here is small. Here probably there is no red line only. And there are a few points which are on my line which are 0. The red line is not present only for them. Correct? What are these red lines? These red lines are nothing but your errors. Why? Why are they errors? Because if you notice it correctly, yellow point is your actual value. Yellow is your actual value. And all the points that are on line, because you're saying that this is your, function or expression of the line, you're saying all the ones that are on this line. Line is a combination of multiple points together. So all these lines are your predicted values. Correct? Every point you are saying, for this value of x, this should have been the y value. This is your predicted value and y cap. Okay. But in reality, this is the point related to this. This is the point which is your actual value. So this becomes your actual value. Your actual value is this. This is your y. And the difference which is coming from this, which will come from this, is nothing but error. Does that make sense? Does that make sense? So error is nothing but your actual minus predicted. Correct? Red line is not standard deviation. Red line is how far is your actual value from the predicted value. How far is your actual value from predicted value? So you have predicted this value. Okay. For x, that is this. Okay. But in reality, the actual value is this. Correct? So you have predicted it to be this value. Okay. But in reality, it is this value. This is some value of, let's say 8. And you have predicted 6.5, for example. Then 8 minus 6.5 is what? 1.5 is the error. You are off by the actual value. Your prediction is off from the actual value by 1.5. Correct? Okay. Now, there's one little thing I want to just highlight. One thing that you need to make sure. So, your motive is that you have to get the lowest error. The line which has lowest error is your best line. Is that clear? If your predictions are very close to your actuals, don't you feel your error will be the lowest? And if the error is lowest, that's your best line. That's the line. So here, between 1 and 2, the one which has the lowest error, we don't know. We have to calculate it. We don't know. The line which gives the lowest error is the best line and is the regression line. Everyone clear with this? Intuition should be good. Visually, what is happening, we'll go into the practical example, we'll type it out. Running linear regression is only 3 lines job in code. It's only 3 lines, not these lines, but 3 coding lines. But understanding what it is doing internally is really important. Okay. All right. All right. Everyone, I hope this understanding, this intuition, if it is clear, no, for linear regression, I promise you it is going to be a cakewalk. I promise you. Go back. Okay. I need only 2 things from you. One, trust. The other, consistency. Go back, refer these notes, refer the original notes, okay, the PPTs, refer the internet, come back with more clarity, come back, ask me more questions, and that's how we are going to learn together. Okay. So imagine we have this graph again. Okay. I will plot some lines with other color. Okay. And now let's say my predicted line is this. Okay. My predicted line is this. Now, what does this say? This says that for this is my x-axis. Let's assume this is your age only. But age will, now I have created the other thing. Let's take it as mileage. Because it has positive slope, it is having an increasing relationship. So I'm not putting my x-axis as age. Okay, perfect. And this is your price. Okay, so now what does this say? Now, this is your actual value. Correct? This is one of your actual values. Now, what is your prediction? Your prediction is this. So for this data point, for when your mileage is, let's pick one. So when your mileage is, let's say this is 100 here. 100 is too much. Let's take 10. Okay. When your mileage is 10, your actual value says this, correct? If I plot it here, this is your Y. We looked at the, certain things that we need to keep in mind. Y tells me actual value. Okay. And Y cap tells me predicted value. Correct? You've covered this. You've covered this. But you have said this is your line. So given this value of X, This is what you're predicting, correct? And if you plot it here, you need to know the price of the car, right? You need to know the price of the car. So this is your y cap, okay? And this line, or in other words, here, this is your error. Everyone with me? So error is what? Error is actual minus predicted. I will write it here also. Actual minus predicted. Okay. Now, don't you think that this is one error? This is one error. Now, you might have this error also, this error also, this, and there are some errors on the opposite side as well. This, right? So you're making errors on each prediction, correct? You're making errors on each prediction. All the errors that are here will be positive, and all the errors here will be negative. Can you tell me why? If you look at the y-axis, for this one, the value, let's say, is 1000. Okay. I'm just saying 1000, and predicted would be 900 because this is y-axis, correct? And for another one, let's take this example. So your predicted was this. Oh, sorry. This is your actual, and your predicted would have been where it touches the line, your yellow line, and where it touches your. So let me put this as 2. Let me put this as 1 and 1. What would this value be? This is a higher value. Y cap is a higher value here. Let's say this is 50. This would be 40. Correct? And what is your error? Actual minus predicted. So in the first case, actual is 1000. I'm taking first example. Okay. Let me put it here. 1000 minus 900. This would be 100 of an error. Let's call this error 1. And this one, which is second, would be what? Would be 40 minus 50 minus 10. This is your error 2. You understand that we are getting positive and negative errors? This is key concept. Are you able to understand? We could get positive errors, we could get negative errors. Can you explain in short how can we get predicted value and the actual value? Please check my question above. Samarth says least square method. What is y cap? Okay. So we covered this, Samarth, but we didn't cover this huge, it's a small concept in notation, in whatever material you study outside, even if you have to refer technical documents or notebooks or different books by different authors, this is the notation followed. Anything which is y is your actual value. Anything which is, this y cap, this, on the top, there's a cap, a hat. It's also called y hat. And we used to study this in our schools. That is referred as predicted value. Okay. That's what I'm mentioning here. Okay. Let's say there is one equation. Okay. This is the equation y mx plus c. This is the line. Internally, that is what we are doing. We need to know m and c. Correct. That's the whole purpose. What we are doing is we are trying our best to understand internally under the hood how is the algorithm working, how it is able to calculate m and c. Okay. So given you are able to identify m and c, let's say m is 2 and c is 10, for example. Okay. Now for whatever value that you put in x, you will get one value of y. Correct. You will get one value of y. So your equation would be this. Now here it will become prediction. That's why y cap. So it will be 2 times x plus 10. If this is your mileage, for example. Okay. This is your mileage. Now, if you say your mileage is what? 10. So 2 into 10 plus 10, meaning what? 30. So you're saying 30 lakhs would be your prediction. In actual, you don't know what is the actual value. Probably the actual price, which is Y, actual price of the car with, mileage of 10 would be 25 lakhs. So this is your actual value. This is your predicted value. All your predictions will be on this line. All your predictions will be on this yellow line. These are all your predictions. Every point corresponding to an x axis lies on this line. To know its value, its price, you need to project it here. You need to project it on the y-axis. That's how you will know the price, right? We have price here. Okay, cool. So now we know that we might have positive errors, we might have negative errors. Now, don't you think we know that your best line is the one which is going to have lowest error? Correct? Best line is the one which is going to have the lowest error. Yes or no? So that lowest error, why? So that if my line is able to overlap all the actual values, let's say if your actual value was like this, if you had data like this, like this is your actual value. And if your line perfectly crossed all of them, will the error not be zero? It will be zero, right? And that will be the perfect line, that all your actual values lie on this line. Correct? But in reality, that doesn't happen. In reality, it's absolutely, difficult to find such a beautiful data that everything is, overlapping with the line. So that's why you will always have some error. So that is why the whole idea is that we reduce the error. The whole idea is that we reduce the error. Okay. Lowest the error, that is your best line. Okay. Now, don't you think if there are some positive errors, there are some negative errors, they will cancel each other out? Yes or no? If there are positive errors and negative errors, will they not cancel each other out? Correct. So that is why what can you do as a solution? What can you do? You need to understand why we took root mean square error. Why? There is a why to it. Once you understand the why, then remembering that thing is going to be piece of cake. So there are two things that I'll tell you that comes to my mind when you haven't read this at your end. One way is take absolute. Correct. Take the absolute value. Take absolute value of y and take the absolute value of this thing. Or in other words, let me write it this way. Take absolute value of actual minus predicted. Correct. Now this is for one value. This is for one. If you do a sum of it, it will be for all the values, all the data sets. Let's say all the data points, sorry. Let's say you have how many points? You have I is equal to 0 to n, 1 to n. Correct. One error is this. One error is this. The other error is this. The third error is this. You have to calculate the best line based on the entire data set. Correct. So the errors have to be summed, and there have to be a concept of averaging it out. So what you're doing here, you will divide it by total number of values that you have. Okay. What is this called? This is your mean. This is your absolute, correct? Mean, absolute. And what is this inside? This is error. So this is mean absolute error. Okay. Okay. This is your mean absolute error. Now, what do you think will be mean squared error? It's very easy. Now, if you understand, you're able to identify all three types of errors very easily. Now, the other option was instead of absolute, you take square. That's what Lakshmi also said. So instead of this absolute, what will happen? It will become 1 over n summation. Why are we doing summation? For all the data points, and we will do actual minus predicted square. This is what? This is your MSE. Mean squared error. What's the difference? Absolute, square. Instead of absolute, if you take square, you'll get mean squared error. Okay. Everyone with me? The third one, which is very popular and mostly that's what in the industry people use, is RMSE. Now you already know MSC part in this RMSE, correct? So what are we going to do? First, we are going to calculate the mean squared error, actual minus predicted square, and then take its root. What is this? Now, will you ever forget absolute error, mean squared error, RMSE? Will you ever forget? No, right? It is very intuitive. People who have made this, they also thought like us. It's just that no one tells us that what they were thinking when they devised this. Error could cancel each other out. So there are only two ways. Either take, either you take, absolute, or you take the squared error. Okay. So the story starts from here. Now, what could happen is based on whether the x point, the actual value is above the line or below the line, you could have positive error or negative error. Correct? This is what we looked at. This is what we looked at. This is the second data point. This is the second data point, and this is your first data point. So the first one is going to have positive error. Why? Because we are assuming that the actual value was 1000 and the predicted value was 900. How we say y was higher than y cap or y hat is because it is looking like this only, right? When you project this point on y-axis and the point on line on y-axis, you will get these values. ये zero से शुरू हो रहा है ना, and it is increasing. And similarly, for the second point, which is here, this point, if you plot, the actual value is lower than the predicted value. Correct? So you'll get a negative error. Now the reason behind summing it is, now you're looking at the errors one by one. Error 1, error 2, error 3, error 4, error 5, error 6, error n. And how do you know what is the value of n? The number of data points. Each row, each observation is your row and is your data point. So as you need to find the overall error of the data set, not only for one observation. Correct? So you need to find the error of all the observations. So you need to take a sum. And with the idea of taking that sum for one value, then second value, third value, fourth value, there is a chance that these errors will cancel each other out. So your idea of finding the best line will be flawed. Why? You will get zero error. This is the line that you're looking for. Correct? This is your best line. But if you don't take the positive errors, if the things will cancel each other out, what will happen is this data set and this line, this will be your baseline. Or in other words, if I have to give you an example of the slope, if this is your data set and this is how it is looking like, this will be your baseline, because the distance here and the distance here is exactly the same. It will cancel each other out. This is not your baseline, because you're predicting every time less or high. Correct? So this is the flaw. That's why you have to take sum, and you have to nullify this cancellation. You have to nullify this cancellation by, you can either take the absolute value of the error, that's what we've done here, or you can take the square. Okay, actual minus predicted square, it will not be negative. Can square be a negative value? No, right? And then in industry we use RMSE. What is the why we have put this root? You need to understand. No, we understood absolute why it is there, squared may why square is there. Now we need to understand why was, if you already had this MSE, why did you wanted to put this root on top of that? So the idea was, when you take squares, no, the error is so high, and a value which is really par, let's say your value is here, and if you take the error, right, it contributes really high when you're finding that value, when your line is trying to adjust. What it will do is, it will try to fit a line like this so that the error on this item is really less, but that does not necessarily give you the right line. That is an outlier. Okay, so to adjust all those values, you are taking a RMSE so that it is comparable. Okay, perfect. So now we have understood the errors. Now we have understood the errors, and the whole idea is that we need to minimize our error of the line, and we have to tilt it this way. So we had looked at this, right? So this is your line. If you change M, it rotates, correct? It rotates. And if you change C, it moves up and down. And when you change M, it rotates. So the whole idea is that you need to rotate, or that rotation and that cutting of y-axis should be in such a way that you minimize the errors. Okay, so that we don't give so much value to some values. So the entire mean squared error will be really high because of only one observation, for example. So you need to find a way to nullify that error coming from a really one value. To nullify that, you're doing root. Okay, perfect. And M here is slope, and this is what it does. Let me change this value so that it is in the window, and this is your M. Okay, now I'll tell you, if you look at this, no, you'll be like, yeah, linear regression to yahi to hai. So simple. Linear regression, GIF. See, are you able to see this? What is it doing? It is changing the C and it is changing the M based on these distances. Correct? Let me try to zoom in so that everyone is able to see this properly. Okay. See, this is the iteration it is doing. Based on your data set, it will rotate and it will fix at that value where the error is minimum. This distance is D1, D2, D3. We were marking it as what? Error 1, error 2, right? Let's look at the other one. Is there a GIF here? See, it is looking at the mean squared error. This is a better example though. You see the linear relationship. The line will start from there. You see the mean squared error is going down, right? Then when it reaches its minimum, now at this point, crosses, if it crosses there, the slope changes more, the error will start increasing. Okay, everyone with me? Now you understand with one variable only how you will find the M and how you will find the C. Correct? With one variable. Is the intuition of linear regression clear? That's how you're going to do linear regression. That's how all these packages inside the algorithm, that's how they work. Computer has power. So you can say that this is my data set. Now fit me a line. It will fit that line in such a way that you get the best M and best C. And when I say best M and best C, it means those values of slope and intercept when your error is minimum. There could be multiple lines. We looked at line 1 and 2. Now you know how to decide which one is better looking at these metrics. Okay. So look at this. I think it is easier and understandable from here. Now let's say the error is reducing, right? When this line is going. Now this is your final error. It will stop somewhere where the error has reduced. Correct? Now if this red line tries to go somewhere here, okay, it is moving like this. When it starts moving like this, the error on this bottom part will increase. Let me try and explain it here. So let's say this is your graph, okay, and all the points are like this. Okay, when this is your line, let's say this is the line, best line. Okay, now if this is 1 here, this was your second line. The error here would be more. This one, this one, this one, this one would be more, correct? With 2. Now, if the line moves here, if this red line moves here, what will happen? It will look like something like this. It will look something like this. Correct? Now the error will still start increasing. It will increase. So in both the directions, there will be some errors. You need to find this red line where you minimize the error. All right. Okay. So now we know how to find the best line with one variable. Okay. Now I'll tell you one story. All the statisticians and all these people, they have one thing in common. Can you imagine a 4D graph or a 5D graph, 10D graph, 10 dimension, 7 dimensions? No, right? The max that we can visualize is 3-dimensional. Correct? So now let me explain you this with 2 features. Now this is going to have your dependent variable price, okay, and this is going to be your age, independent variable, and this is going to be your mileage. Now in 2D we were fitting a line, correct? Now the values could be somewhere here. Correct? Now instead of fitting a line, you will be fitting a plane. Now you cannot fit a line. You'll have to fit a plane, right? In 3D, where all these points lie and the error is really less. It could be any plane. In 3 dimensions, it is going to be a plane. If you go to more dimensions, the shape of that, you know, line or plane is going to change. So we say that it is hyperplane. We don't know it is a 3 dimensional, 4 dimensional, 5 dimensional. And how do you decide these dimensions? Based on your input features or your independent features. If you have 10 independent features and one target variable is going to be only one. Okay. If you have 10 features, you have to minimize the error in 10 dimensions. One is age, the other is mileage, other is engine, then manufacturer, then some other value, kilometers driven, someone was saying. Imagine, can you even visualize? No, right? No. So that's why people call it as hyperplane. It is more than 3D. 3D tak you can say yeah 3D plane hai, yeah, this is cuboid or cube somewhere. But above that, it is a hyperplane. Okay, everyone says it as hyperplane. Now tell me one thing. Since this is not a line, now your y cap, which is your prediction, will be what? So now there comes a concept of weights. This is beta 1 x1. I'm saying beta, you can assume it b also. This is beta 2 x2 plus beta naught. This is nothing but your intercept. Assume it that it is intercept, but this is something that without any input, any value of x, this what is x? X1 is age, x2 is mileage, and there is some weight of the age, and there is some weight of the mileage, which is beta 1 and beta 2. Okay. You need to now find the value of beta 1, beta 2, and beta 3 so that you have the best plane. And how do you find it? Concept is same. Error. Reduce the error. Minimize the error. Sometime in text, they also refer to this as weights. So you might also see some text, some posts or blogs saying this as weight 1 x1 plus weight 2 x2 plus weight 0. Okay, this is with two independent features. And when this is n, there are n features in your data set, n independent variables, then this line will become what? X2 plus X3 plus Wn xn plus W naught. Both these notations work, either beta. So I will write it here. Beta, W or B. All of these are nothing but weights. And in other words, technically they are called coefficients. Whenever you go into the interview, you can either say weights, but it is good if you say coefficients. Okay. All right. So coefficient or weight tells what is the contribution of that feature. Okay. Let's take a hypothetical equation. Let's take hypothetical equation, which is, this is your prediction. This is your prediction, and I'm assuming only two features. Okay. two features. One is age and the other is mileage. अरे rhyme हो गया है तो. Okay. One is age, the other is mileage. And this, when I say two features, it is independent. Okay. Two independent. Now, let's say this is W1 into age, okay, times age plus W2 times mileage plus W0. If you have to understand it very intuitively, hear to me what I'm going to say next. Okay, this is not that important, but it will help you in understanding to derive when you're in the projects to explain your concepts to a person who doesn't know linear regression. That is part of the job. Trust me, that is part of the job. If you are going to explain this to someone, this is going to help you and is going to help you leaps and bounds. Listen to this with undivided attention. Okay, undivided attention, 100% focus here. Let's say W1 is 100, W2 is 200, okay, and W0 is 50. Okay, it's 50. Now your equation will look like this: 100 times age plus 200 times mileage plus 50. Correct? Now, if you change your value, you keep everything constant. You change only the value of age. Change only age. Keep everything constant. What is going to happen? Your y new will increase by a factor of 100, is directly proportional to 100 times age. Correct? I'll give you an example. If your age was 2 years, okay, this should have been negative. To make it sense, I'm changing it negative. Okay, to make more sense, I'm changing it. You will understand why I'm changing this to negative. If your age is 2 and if your age, you increase the age by 1, here I'm keeping everything constant. Here y would have been 200 minus 200, and here it would have been minus 300. Correct? So the increase in age, we know the slope is going to be negative, right? And this is going to be positive. This is where the sign is coming in. If you increase the age from 2 years to 3 years, the price, the impact of that increase on the price is going to be a factor of 100. It is going to have an impact on your prediction or the price of the car by 100. Okay. If it was, let's say 500 at 2 years of price, 1 year down the line, 3 years, it is going to become 400, assuming everything is constant. Understood? How do you decide the coefficient is 100 or 200? Is the slope, right? Is the slope. So if the relationship is negative, here, let me draw it. So this, as and when your age increases, your price is going to go down. As age increases in your second hand market, as and when your car gets older, the price of it is going to go down. Correct? So the relationship is negative and the slope is negative, relationship is negative. And if your mileage increases, if your car has a higher mileage, the price is going to be more. So the relationship is positive. Here it is going to be negative. That is why these values. Positive for mileage, negative for age. Okay. So independent variable is, in our case, independent variable is your target variable. It is, sorry, it is your dependent variable. I'll repeat that. Dependent variable is your target variable. It depends on certain other features. So your price of the car depends on some other features like age of the car, manufacturer, kilometers driven, engine it has, the mileage it gives. Okay. So mileage, according to your problem now, is independent for prediction of price. So you can predict the price of the car given you have mileage. You can predict the price of the car given you have age. Okay. All these are called independent variables, and your target variable is called dependent. Okay. How can we reduce error? In whatever happens in the system, right, in algorithm, generally it follows brute force. Generally it follows brute force. Brute force as in, it will try to do all the iterations and then it will find the absolute value or the correct value. But since we are doing machine learning, we are smarter than, executing all the iterations, all the 100,000 of them, and doing it once. In machine learning, that concept of finding the best error is gradient descent algorithm. In small number of steps or in an efficient way, you can find that error, the minima or the maxima of the curve. Okay. That is gradient descent. Gradient descent is something that helps internally underlying everything, that this is how, you can find the next error. It is basically differentiation. Okay. So these things you can go and explore, and I will definitely recommend that go and explore. The more you read, the benefit it is going to have on you, and your learning is going to be really good. My job here is to give you the easiest explanation so that you understand the concept. Once you understand the concept, you've taken, you've created a base. Now you want to create a 4-story building or 5-story building or a single story building. That is up to you. Okay. You want to create an antilla, go read, explore, burn your curiosity. Okay. So, mm, this will confuse a lot of people who don't have maths background. Okay. So gradient descent, basically, I am touching upon some mathematics. So guys, if you're not clear with this is not required. Okay. This is not required. I am highlighting it. If you're not able to understand this, don't worry. So in general, what happens is, this is how the errors look like. Okay. In any graph, even forget about error. Okay. In reality, all the graphs look like this. This is your maxima. Maxima meaning max value. This is your minima. This is again a maxima. In this region, in its locality, it is maxima. Correct. Even though it is lower than this. Okay. That's why we call it as local maxima. In its locality, it is maxima. In its locality, it is minima. In its locality, it is minima, and so on. This is local minima. This is local maxima. Now this since in its locality and overall also, this is maximum value. So this is called global maximum. Okay. And this value here is the minimum value, is the minimum value. This is called global minimum. Okay. Now the idea is, for algorithm, the idea is that you need to reach here. You need to reach here. If you're trying to reduce the error, if your problem is like that you need to reduce the error, you are looking for global minima. If your problem is that you're trying to maximize it, like for example, you are trying to maximize your car price when you're selling it, correct? Your motive is to maximize it. When you're trying to increase your profits, it is you're trying to find the maximum, correct? That is global maxima. But when you're trying to reduce your expenses, your expenditure, you're trying to find this global minima. Okay, this is clear. Now let's zoom in only at this part. Let's zoom in only on this part. Okay, I am pointing it here that we are zooming in. Okay, how will this look like? If you zoom in, you're going to look at this like this. This is how it looks like. Correct. You are now in pursuit of this local minima. So what happens is you start arbitrarily from here. You start from here. You set the values in the gradient descent. You set the values of your learning rate in such a way that after one iteration, this is one iteration, second iteration, third iteration, fourth iteration, third, fourth, fifth, sixth, you try to reach here. When you have done this, when you have done this, you have achieved your motive. Okay. This is in short that I can explain. You can imagine it this way also, that imagine you are coming from a hill down. Okay. On the top, when the steep is really sharp, the mountain is really steep, your small steps, you know that you are going down, so your steps are going to be really huge, because this is the change in error. This is the error that you're looking at. This is your error. Okay, so the idea is that you need to find this, and that's how you do it. How you do it? This is the gradient descent algorithm. It has two parts. One is the direction, where it should go. The other is steps. Step meaning it should be long steps or it should be small steps. Okay. The direction is you need to go here or you need to go here. Depends on that. Okay. Steps is also sometimes called learning rate. The idea is that you need to find the global, but in real world, what happens is you are not able to find the global minima or maxima every time. Most of the time, you'll be stuck in some locality. You'll be stuck in here or here. Okay. So you try to find the local maxima or the local minimum. Okay. And that's the beauty of maths, and that's the beauty of the data, that even if you find this, the effort that you have to do from reaching this local minima to this global minima is going to deteriorate or is not going to be that much of effort, then you're going to get the benefit out of it. Okay, so everyone is happy with this. This might give you 90% accuracy, this might give you 90.002% accuracy, and the effort that you have to do from reaching to here is really a challenge. I'm not saying it is not doable, it is doable, but in reality, uh, it is, kind of overfitting. So in future, if your data changes, this will do a better job rather than this. Okay. No more going into deep. This is pure mathematics. That's the best that I could explain in short. Okay. I will write it here so that no one confuses when you're looking at this GDA. This is not required. Okay. Okay. You can understand it logically, but if you need to go in detail, you need to cover the mathematics around it. Perfect. All right, guys. So this is what this is linear regression and so on. Okay. Perfect. All right. So I have uploaded my data set here. Now let me. So what do we do? First thing, comments, make it on the go while you're typing in, because no one comes back. You might think that, I'll put in the comments, no one comes back and it becomes difficult. In industry, follow it. I also follow it as and when I'm writing, at least for my clarity. I forget a lot. So I write the comment as it is on the go, importing dependencies. So what do we import generally? Pandas as PD. And I typically import these three without any this thing, without even thinking about it. Matplotlib dot pyplot as PLT. Okay. I end up using these three every time. So I, load it on the top. And for this session, at least since we are going, bit by bit, I will try to import the dependencies where they're required. I try to then, once I do that, I try to keep everything together. I'll show you how I do this. It's a good practice to follow, at least for myself. That's how I follow it. Everything that I'm loading is in one place, and everything that I'm exploring is in one place. So let me start with this first. Okay. Now, since we have this already, let me put in a few cells. ठीक है. Now, what are we going to do? We are going to first read the data. Where is your data? Your data is this, correct? So pd dot my keyboard is giving me a problem. Question 1 is the name, CSV. Then I try to do as soon as I read it to make sure that I have read it. We need to run this first and then this first. Okay. So now this is your data set. I'm just making sure everyone is on, not having this thing. Yeah, virtual will take some more time. Data imported and visible. Perfect. So now let's understand what this data set is. Okay. This data set is basically, the problem is, let me try to give you the idea of the problem. Okay. So the problem is we have to predict the, our favorite problem, house price. Now this house price, what we had looked at during our examples was, for explanation, it was an easy to understand data set. This is a real life data set. Okay. So this is being maintained by US. It is the actual data that they have covered and recorded for their purposes, and even for these purposes. So they've kept it online. Let me show you what is this. So Boston data set wiki is what we are looking at. This will also work. And before you start any problem, okay, look at this. This is Boston. This is a region in United States, Massachusetts. Okay, so there are multiple towns inside this Boston. This is how it looks. Okay, and this is your Charles River. This is the river that flows through it, and it is the Charles River. This one. Okay, such a beautiful city, right? Now, now since you've done that, it's always good to have that external factor. Machine learning machine will also do, but have that idea as a human, what are you doing? Okay, and this is a real data set. Okay, that's that. Now let's look at these columns. Now I've gone through the description of this data set. Okay, this is where you can look at the data set. What is it doing? Okay, now this crime is telling you the crime rate of the Boston area. Okay, now imagine when we were looking at the prices, we were finding number of bathrooms, area size. Yes, they are there, but in reality, there are so many things. Correct? You need to know the crime rate. It might affect the price, right? Don't you think? An area which is having high crime rate, people will not buy there. Probably the price will be less. Okay. Then this is another proportion of the zonal, the lands which are above 25,000 in the zone, the number of those lands which are owned by people which are above 25,000 square feet. This is industry telling that, how proportion of non-retail business per acre town. Okay. So what is the proportion of the industry? Think it that way in the town. Then you have CHAS. It is a simple column, 0 or 1, okay, which is telling you that is it close to the Charles River? I showed you the Charles River here, right? Okay. So I showed you the Boston. Anything that is closer is on the area which is on the banks of the Charles River is your 1, else it is 0. Okay. That's how it is. And let me, this one, any area which is closer to that is 1, and this area which is not closer to it is 0. Okay. Then we go into NOx. Now this is a proportion of nitrogen oxide in the atmosphere that is harmful. So they are noticing this is 53%, 46%, and so on. Okay. Then RM, what is RM? RM is the number of rooms. We had also considered this. Yes. Age, age of the house. Then this is distance. Okay. This is the distance from the 5 employment regions in the Boston. What is its weighted distance? Weighted as in what is it's a weighted average distance. Okay. That's that. And then this is radial distance, the tax that is paid. Then P ratio is basically, PT ratio is basically per people, how many teachers are there? What is the ratio? Okay, 15 is to 1. So every 15 people, 15.3 people, one teacher is there. And this, now this data has been recorded way long, and they used to keep this track number of black population or black people in a specific area. Okay, that's the count. And this LSTAT is let me refer, what is this LSTAT? Okay, so people with lower income, they are calling it as LSTAT. Okay, and MEDV, this is your target variable. It says median value of owner occupied homes. Okay, what is the median value of houses owned by people? Okay, Now this is in $1,000. So 24 here means 24,000. Okay, cool. Everyone understands the data set, and this is our variable, target variable, medv, and all these are our independent features. And medv is our dependent feature or target variable. Correct? Now, good thing to do every time you load in the data is first understand the explanation of each column, because that might be helpful, not only from the mathematical sense that this is categorical or this is continuous, not in that sense, but also kind of you know uh, business wise, what would be more important, what would be not more important. Okay, it is always to have that. It is not necessary to do that, but I like to do that, so I would like if you also follow that. Okay, just have a human, from a human perspective, try to understand the practicality of the data set. Okay, cool. Now we see this is 0 or 1, kind of a flag or a categorical variable. This is also an index. I think radial is not distance, as I said, is the index. Okay, so index of accessibility, meaning it would be like the one. If it has value 1, it is really accessible. If it has 2, it is somewhat accessible. 5 would mean really not accessible, something like that. It is an index. Okay, imagine it to be something like high, low, medium kind of a thing. Okay, then rest others, I think we have ratios, we have counts, and all. It's a mix of a data set. So what I try to do generally is I try to look at the head we've already done. I like to do this. Describe. So what it does is it, in a nutshell, gives me a lot of information about the data set. Okay. Now this tells me 506, 506. Everything is having 506. Correct? This tells me the count of uh, values that this has, or the rows that that column has. Crime has 506. What is the mean value? It is 3.6. Okay. What is the standard deviation? 8.6. Minimum value is this 25 percentile, 50 percentile, 75 maximum value. Okay. So in a nutshell, it tells you a lot of things about the data set. Okay. What I can quickly gauge out of this is that mean is around 3. So on an average, the crime rate is around 3.6. Okay. And there are a few, let's say 50% of the houses, 50 percentile means 50 percentile or 50% of the houses in this data set are in a locality which has really low crime rate, really low, 0.25. Average is 3.6. Okay. So it tells me that 50% of them are having really low crime and 50% of them are having really high crime. Okay. Above 75%, meaning close to the maximum value is this 88.9. This is 77, 75 percentile. It means the third quartile. You must have learned it in your statistic classes. 75% of the values in the data set are below 3.67. Okay. 50 percentile tells me 50% of the values are lower than 0.25. Okay. Perfect. And if I look at my target variable, the average price is around 22.5 in 2000. Okay. And the maximum value that it can take is 25 or 50. This is the maximum value. 75% of the houses are having what? Price lower than or equal to 25. Okay. So this gives a lot of information about the data set. And even prior to this, people also tend to do this data dot shape to find how many rows and columns are there. It tells 506 and 14 columns are there. Okay. Now, what I do is I look at this. So I get an idea that, okay, 506 are there and I can count everything here. But it will tell you only the value of continuous variables. You notice that you don't have the variable Charles here, correct? You notice it is not here because it cannot calculate the average value of 0 and 1. No, it cannot tell 50%, 25% tail, all standard deviations, all those things it cannot tell. So that's why you don't have that. Even if it has, it is not making any sense here. Okay. So when even if it is there, don't look at it with real value. You're not going to get much value out of it. So this is what we do. Shape 506 rows, 14 columns. Okay. This is how the data set looks like. This is you print to see that, okay, first 5 rows head, on by default gives you 10 or 5. You can also do this. Let me run it on a separate cell so that I don't read it again. So if you want to look at 10 rows, you can do this and it will give you 10 rows. Okay. If you want to look at from the bottom, if your data is having a time aspect to it and it is sorted, you can either sort it or you can simply print the tail. Okay. Cool. This is the summary. And the other thing that I also try to do, not every time, but is a good practice is, doing an information. So what it tells is, it tells me each column, okay, how many non-null values are there. So looking at this, you'll find if there are any missing values. Okay. It also tells, since I deal with really huge data sets, I also need to know this. What is the memory usage? What is the, if it is really huge data, if I'm working with image data, it's typically in GBs. So this helps me to whether I need to parallelize my things, I need to, work on the cloud, or will this it work, or do I need to, put in the GPU or something like that. All those things it will tell. For each column, it will print out its data type, whether it is a float, integer, object, whatnot. It will also tell whether how many none values are there. Now you know that there are 506 entries. Okay. If any column says 500, so 6 of them are missing values. They're blanks. Okay. They're null values. That's one. And then this also tells me a summary that out of 14, 11 of them are float type and 3 of them are integer type. Okay. Very in one line, you get a lot of information about the data set. Okay. All right. Cool. Now, once you have the data set ready and you've loaded it in, what do you want to do next? Now we are here to do what? We are here to do linear regression, right? So the other thing that you can do is, the first thing is that you need to know the dependent and independent variables. We know, right? Data cleaning is not required here. Okay. And we are going to do simple linear regression first so that we cover linear regression also, understand it. I want to do two things. The way I explained you, with one feature and then with multiple features. Okay. In industry, this is called linear regression, and multi features is called multiple linear regression. Okay. Keep that in mind. Very intuitive, but just in case. Okay. Cool. So now what I will do is I will try to create my data sets. I will do data. I want to keep only two variables as of now. One is I will keep lstat. This I've done. And so what we are doing is linear regression with one variable. One variable is what? Independent feature is equal to lstat. Okay. And dependent feature is, dependent variable is median value. Okay. Cool. So this is what I'm doing. I am, let me change this to, okay. So now you have this, you have one variable and one target variable, correct? We are trying to understand linear regression with one feature first, and then we are going to do with all the features, okay? So that you are doing this for the first time, right? We learned linear regression how? With one line, single line, correct? And then we replicated it for all the features, planes, hyperplanes. So for you to digest it better, I'm first doing it with one feature so that I can show you some graphs and also explain you how things are looking like. Okay. Okay, perfect. Now the other thing is, once we've done this, we should also plot it. Let's see. We were always plotting everything. Let's also plot this. Okay. So what we'll do is, now we have already plotted the matplotlib. Now we are going to plot the relationship between LSTAT and median value, medv. Okay, cool. So it is, what do we have in x-axis? LSTAT, correct? Dependent variable on y-axis. So we will have medv. Okay. And then I want to do what? I want to plot the x label. X label is, I'll start, and then plt dot. We are giving the labels. Okay. This is the median value of house. And then we have plt dot show. Okay. So this is how it is looking like. It shouldn't be looking like this. Yeah. Okay. So this is how it looks like. Scatter plot. Yes. Okay. Cool. So let me close this. If this guys is not visible to you, let me close this. So you see how it is changing, correct? If the percentage of people with lower status, percentage of people with lower status is high, the price is really less. And if the percentage of people with lower status or lower income, in that manner, if you want to understand it, the price is really high. Okay. All right. That's, you see the clear, division. You see the relationship. Now the best line would be somewhere here, correct? Let's try to find it. So now you have this data set. What do you want to do next? So we will separate out our dependent variables and independent variables. Okay. Segregate the dependent and independent variables. Okay. By, by notation, anything which is x is your dependent variable. So what we are going to do is, we are going to create this data frame where your, what value is your dependent variable? Your independent variable, sorry. X is independent, y is dependent. So x is L stat here, right? X is L stat, correct? So let's put in the L stat here. So what was the name? It was df underscore one feature. Yeah. So we are going to pass here lstat, and in y we are going to pass what? We are going to pass our target variable, which is nothing but medv. Okay, now we have that. Now the next step is, now you have your dependent and independent features separate out. What did we learn in supervised learning? What do we have to do? Now the next step is to create the model. To create the model, what do we want to do? So this is what we have done right now. Now imagine, what did we do? Divide the data set into, you have to build your model. What do you have to do? Divide it into train and split. Correct? You have 500 rows. You have to split it into train and test. Divide it into train and test. Now you have divided the columns first into dependent and independent. Now you need to divide your rows, one on the training, the other on the test, so that once you create your model on the training, you need to, you need to test it on your validation or test data set, how your thing is working, how your model is working. Okay, perfect. So for that, what happens is we have to import from sklearn dot model underscore selection. Now sklearn and scikit-learn are the same thing. When I started learning, first of all, when I started learning, Python wasn't there in the picture for machine learning. It was R language, but now Python has taken over. So what happened is, I started looking at what is sklearn, what is sklearn, what is sklearn, and in the internet I used to get scikit-learn, scikit-learn, scikit-learn. So both the things are same. Okay, it's just how people are calling it. So I need model selection from it, and from a model selection I am going to import my train and test split. Okay, this function is going to help me divide my data set into train and test. Okay, guys, perfect with me? Done. Okay, now what it does is it will give me these four things. This is the train array, train test split, and what it takes as an input. This is the output that it gives, right? From Python, you know, packing and unpacking, right? Whatever this gives as an output, it has four outputs, and you are giving each value to this: x train, x test, y train, y test. Okay, whatever value comes from this. Okay, now what it takes is, what it takes inside it is, it takes inside the x value dependent features, it takes your independent features. Okay, and then you can also look at it, this definition, you can look at it. Okay, train size, then you have the random state, and you also have other values in this, whether you want to shuffle or not shuffle, how do you want to select things. Okay, do you want to stratify? Stratify is meaning if you have three classes, apple, banana, and orange, and you want to take in the same ratio, let's say 50% of banana is there, 20% is apple, something like that, then you'll take it in the same ratio. Okay, and divide it into 70% or 80%. So what we did was, this is that, and then the split. So I will do 80% here. So this test size, what is the test size I am passing here? Random state. Okay. All right. So what happened here? You're passing all your x here, and you're passing all your y's here. Okay. You're saying my test size should be 0.2, meaning 20% in the test, 80% in your train. And this random state is telling me what? Is telling me so that I can repeat this. So some things happen randomly, right? I'm trying to take randomly 20% out as a test and 80% as train, so that you guys also are able to repeat this as your at your end. Every time randomness is constant. So if I provide this random state, it will, you know, repeat the same set of results for everyone. Okay, cool. Now let's print it here. How are my things looking like? How are my X train, X test, all those things are looking like? So I am going to do this. I hope everyone knows f strings. X train shape is this, and I will repeat it for, let me put it this way. Let's do Y train so that you know how Y train is looking like. Then we for everyone. And then I want to also look at my test set. So I am going to put here test, and here instead of test, it is going to be, or train, instead of train, it is going to be test. Okay. So now what we have done, we have in my train, X train, we have 404 values. And similarly, I have 404 actual values, the label. Y is label. And your test is 20% of 506. Okay, it is 102. 502 in your dependent variable and 102 in your Y test. Okay, cool. So now you have the train and test. What is the next step? Okay, we will now create the model. Okay, and which model we are going to create? We are going to create linear regression. So linear regression comes from your linear models. Okay, and it is again from sklearn model, not linear. It gives suggestions when it wants. Okay, Are? Let me write this properly. From this, import what? Import which algorithm are we going to do? Linear regression. Okay. So we are going to import linear regression from here. Now what I do is we have to first instantiate. We have to first instantiate this linear regression model. Correct. And then what we are going to do is we are going to fit, or let me do one thing first. What did I do? I instantiated this linear regression into model. Now my model, when I print model, I will get this. It is a linear regression type. It is an instance of linear regression. Okay. Everything of linear regression is now held in model. Now what you do is now you fit the model. Fit the model. Here our model is what? Our model is linear regression. Now what I will do is I will model.fit. It needs to fit on what? It needs to fit on X and Y. But X and Y are on train. Okay. and I will save this as, it will be saved where? In model. So all the learning that it is doing will be saved in model. Now till here, model is only linear regression. Here it is going to fit. It is, when I say fit, fit on my X train and Y train and find the patterns. This is what is happening internally. Okay. Once you find the patterns, I am going to test you on this. When I say patterns, it is fitting a line there. Linear regression, this thing has that concept already built in, that it will find the best one. Okay, cool. So now let me run this. Okay, model.fit happens, and then what we have also seen, that we have model dot. Now if you do this, you will see all these things that are inside this model or inside this linear regression. Okay, we want to see the coefficient. Coefficient was what? M or W or beta. So for L stat, this is the value. And you notice the negative value here. You notice the negative value. Why negative value? Negative slope. That's why negative value. Magnitude tells you how big an impact, and positive or negative tells you whether it will reduce your prediction or increase the value of your target variable. Okay. Then there is other thing also, which is inside model. What do we have? The other thing, intercept. This is your intercept value. Okay. So this linear regression will help us find what? M and C with one feature. M is your coefficient. Okay. And C is your intercept. And you see the values for it. Okay. Cool. Now you see the value for it. Now what's the next turn? Predictions. Correct. Now you know the line. You have weights, you have the betas, you have the coefficient, you have the intercept, you have a W naught or beta naught, whatever name you want to call it with. You have it. Now predict, get the Y cap, get the predictions, and then compare predictions with your tests. So simple. Okay. That's how you will know your model is good or bad. Correct. So what we are going to do is we are going to make predictions, and predictions will be done with model dot predict function. And yes, in the predict function, what are you going to pass? You are going to pass only test. You are not going to pass Y test, because if you will give the Y test to it, you are giving already the actual values. You need to test, right? So this is what we are doing with YPred. I am now also creating, for it to be visible clearly, I'm creating it into a data frame. Okay. And let me give the value of the columns to be its value as predicted. Okay. YPred dot 102 predictions. Let me also do this. Let me show you what you have predicted. You have predicted this for 102 values, because your test had 102 values. Correct? Now, how do you know whether your model is good or bad? How do you know whether your model is good or bad? We learned about 3 errors. Which were they? Mean absolute error, mean squared error, and root mean square error. Correct? Let's do that. Now for that also, you don't have to memorize all the formulas and everything. You already have it. Okay. So this is your prediction. This is your test values. Let me show you. So in reality, it is 28.2. But what you have predicted is 27.37. Okay. This is 27.69 that you have predicted. In reality, it is 23.9. So you see, there are some errors. You can already see there are some errors. 16.9 and 16.6. So now what we are going to do is we are going to find those errors. Okay. And those errors are in another sklearn dot metrics, and I am going to print it directly with the f string. Okay. This is which one is the first one? Mean absolute error. I will also need numpy. Since I have already imported it, I'm not doing it here. I'm saying MAE, mean absolute error, is what is metrics not mean. Python is such beautiful, you need to find mean absolute error, you provide only that name. Okay. And what did we metrics? Okay, it is saying a squiggly line because we have not run this till now. Let me run this. uh, from sklearn import metrics. Okay. From sklearn, we are importing metrics and we are putting this, and we need to pass the actual value and we need to pass the predicted value. This is mean absolute error. Similarly, MSE, and you change this value to mean squared error, and then RMSE is what? Is what, guys? Is just the root of what? Is just the root of your mean squared error. So what will I do? I will do np.sqrt. Is that clear, guys? So now you know mean absolute error, you know what is the mean squared error, and you know the root mean squared error. Okay. Now what I do generally is I keep everything that I have imported in one cell. This way I'm able to load everything in one. R square, we can do R square also. It's nothing but if you do, instead of here, if you do R2, I think it is R2 square score, unmatched unstring. It will tell you R square also. Okay. Now you have, I will cover R square later, but it's very simple. It is another metric only. Okay. Now we are going to go into multiple linear regression. So in single linear regression, what did we do? In single linear regression, we created a data set of only one dependent variable, and we had the one dependent variable and one independent variable. Okay. Now here what we are going to do is we are not going to do that. We are going to run it for all the features. So all my features are where? Are in data. Are in data. Okay. So what I'm going to do is I'm going to copy this, and now I am going to say dependent all features. I am going to say data all the columns dot iloc. Do you understand what I did? So from data, okay, let me print it out here. Data dot head. From my head, the last column is medv. So I'm saying all the rows start to end from start to -1, meaning the last one is never captured, right? In the list slicing. So I'm saying from start to -1, okay, take all the columns and put it in X, and in Y, take only the one -1, the last column. So that I have what? I have all my dependent features in X and all my independent features in X and dependent feature only in Y. Okay. Now, what was the next step we did? Next step was to split the data. We will do the same thing. Okay. We are going to do the same thing here. Again, it has run. Let us do the same thing. Whatever we did for one feature has to be done for every feature, right? The concept is same. So now we are going to do what? We are going to print our X test and Y test, X train and Y train. Now the only difference is the number of dependent features. Independent features. Why am I saying dependent? Independent features are 13. Earlier it was only 1, and your dependent feature is only 1, which is your target variable. Okay. Then what did we do next? What did we do next? We created the model. We created the model. We'll create the model. And then what did we do? We fit the model. We fitted the model. You see why I am doing this copy paste on purpose. We've already did it once, correct? We already did it once for one feature. Is there any change that I am doing except for just passing the features that I wanted to pass here? This is the only change. All the other steps are same. Train and test split. Finding the, X train and Y train, X test and Y test. Only the difference is number of features here. The model I created, it's the same model. It is telling you the same thing. I am fitting the model in the same manner. Correct? I am also predicting it in the same manner. Look at this. Okay, I will show you. This is kind of important. Okay. Now, earlier you had how many intercept? One intercept, right? Now also you're going to have one intercept. But this time you had how many coefficients? How many weights? You had how many coefficients? You had only one coefficient. Now how many are you going to have? You're going to have 13 of them. One coefficient, one beta value, one W value for each feature, each independent variable. Okay. And then what you do is you do the predictions. You do the predictions. Okay. This has your predictions. And then we are going to evaluate its performance. Guys, did I do anything different? Did I do anything different from one feature to multiple features? No, right? You can see the values have changed. It's in the understanding. Now, instead of one feature, you are having 13 features. The mean absolute error was 5 earlier. Now it is 3. This was around, I think, I don't know what the number was. Here it was 6. Here I think it was 26 or something. 46. Remember, see, you have done so much of improvement. And what did you do? With one feature to predict, it is difficult. With multiple features, it is easy to predict. Okay. So that's the whole idea. Let me save this. Okay. Cool. Okay. So with multiple features, it is basically a plane of the line, right? Cool. Now iLog part. So iLog is nothing but, okay, how do I explain this? Let me pick this here. Now, what is this doing? iLog is nothing but it tells a location for data to pick up the location. First, tell me this, guys. If I say A is equals to 1, 2, 3, 4, 5, 6, 7. Okay. Now, if I print A, you know it is printing this to this 1 to 7. Okay. Now, if I say 3, what does this thing say? This is a list. Okay. What is this going to print now? It is going to print only 1, 2, 3. Why? Or let me do this. 20. This is Python concept, guys. Revise it. I am explaining it, but revise it. You'll be much confident. Okay. So it is nothing but it is slicing. This is your starting part. This is your ending part. So it is saying the counting starts, the indices starts in Python from 0. So 0, 1, 2, 3. But the caveat is the starting part is included, ending part is not included. So it is going to print from 0 to 2. Index is 0 to 2, not 3. And 0, 1, 2. So that is why it is printing 0, 1, 2. If I say print till 5, if I say 0 to 5, this is nothing but a blank there means 0. Okay. This, let me explain this. I said this 0, 0 to 3, 0th element to third element, but third element is not included. So it will include till 2. It is going to give you the same result, 10, 20, 30. Okay. And here, if I do this 5, it is going to give me first 4. 5 is not included. So 0, 1, 2, 3, 4. This is what it is going to return. Okay. It returned till 50. Now, minus 1. If you say minus 1, what will it do? It will give me this number from the last. If this is 0, this is minus 1. Okay. It gave you the last value. Correct. Now this I'm explaining on list. If you do on data frame, so now you understand this is what I did basically. This to this minus 1. So now you understand this is columns and this is rows. Since I am now talking about data set, it has rows and columns. So this first part is telling you rows. This is blank, meaning all. Let me explain this here also. If I do A, and do not pass anything. It means pass me the entire list 1 to 70, 1 to 70, 100 to 70. Okay. So this part tells me all the rows, and this part tells me all the columns except -1. Okay. But in data frame, you need to put this when you're giving indices, you have to use this iloc, index location, so that data frame understands that it is the index location that I'm passing here. Okay.
Just a quick info, guys. Intellipaat offers an executive postgraduate certification in AI and machine learning in collaboration with iHub, IIT Roorkee, and Microsoft. This comprehensive course is designed to make you an expert in AI and ML in just 11 months by working on over 50 real-time projects and industry case studies. With this course, we have already helped thousands of professional and successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step towards career growth in the field of AI and ML.
Now the other thing is, now we know how linear regression works. Okay. We've also done the hands-on. There are certain things, two minute things, which are really important from your interview standpoint. Okay. Whatever I have explained you, if you understand that, okay, you know how linear regression works internally. Okay. Whenever an interviewer asks you a question, can you explain in linear regression? You can start from the scratch, from the start to the end. You can explain what linear regression is. Okay. Correct. And if they ask you, can you do a hands-on, can you implement linear regression here? You will be like, give me a data set, I'll do that. Okay, hands-on is clear. Now there are certain other variations. Even I, as a recruiter, go and try to ask this more from a overall understanding of the concept. Okay, so in the overall understanding of the concept, you need to know it's working. You need to do a hands-on on it. Then you need to also need to know certain theoretical aspects of it. Okay, now what are these theoretical aspects related to linear regression? So with respect to linear regression, there is this R squared. Okay, I will mark a star and I will say interview. Okay, what is R squared? 1. Then assumptions. For implementing linear regression, or people generally try to ask this as assumptions for linear regression. Okay, these two are really important. Apart from what I have already told you, the entire understanding, the intuition of the algorithm is really important than the hands-on part. Okay, now we'll cover R squared in a moment. Assumptions of linear regression are basically you as a data scientist, as a machine learning engineer, or data analyst, anyone in this industry, you need to know when to apply linear regression and when not to. That is really critical. It doesn't mean that you're given a data set and blindly you will say that I've learned linear regression, I will run linear regression. No, there are certain assumptions, meaning assumptions on the data that you're taking, that if the data follows these assumptions, I'm making these assumptions on the data set. If they are present, then linear regression will give me a good result, or it is something that I can implement. Code will still run. Your Python notebook, all those things will still run. It will still give you an error. But is that the right thing to do or not do? That is also a part of the job. Okay. That comes with experience, but assumptions are the first step that you need to look at. Okay. So we'll cover that. Now, what is R squared? Let's look at the first thing. Now, R squared has a really easy concept. This is the formula. What is this? This is nothing but this is sum of squared. Okay, let me also first explain this. Your errors that we looked at, okay, are also called residuals. That is left, right? So residual is something that is left. So the error is basically between your actual and predicted, right? That is something left. So residuals is another name given to errors. Okay. So this is something that you need to keep in mind. Now here you're telling the residuals, sum of squared errors of residuals and sum of squared errors of total. Okay. This is the formula. Now let's deep dive. How did they come into this formula? Okay. Why did they create this? Now tell me one thing. Tell me one thing. If you have a plot, okay, let's say you have a data set like this. Okay, you have a data set like this. What you are doing is you are finding the best line, correct? This is your best line. But how do you say this is your best line? You need to have some benchmark, right? Some comparison, correct? Till now we were looking at errors. Till now we were looking at errors. But there is another benchmark that you need to have that is, statistically also proven. Let's say I have this average line. Okay, what is this? This is average line. You need to compare your line with the average line. Okay, meaning if if I predict, let's say this value is 100. Okay, if no matter what your features are, you keep on predicting blindly the average value of the entire data set, of the entire pricing in our example, that median value. How good is your this regression line as compared to the average line? Okay, that is what R squared is. It is also called, R square is also called coefficient of determination. I will put it here. Coefficient of determination. You're determining whether this is your good line or bad line. Okay. And how are you determining? How good does your regression line is better when compared with the average line? You need some benchmark, right, to compare. So this is what it is doing. So you need to tell if your model is right or wrong compared to the average. And this is the formula for it. Here, what does this tell me? Numerator tells me my sum of squared errors of my regression line. Okay. And this is nothing but sum of squared errors of my average line. Everyone clear? Now you understand the formula, why it is that you're taking a ratio. You're saying how better is my regression line compared to the average line. Okay. Now what values can R square take? This is really important. What values can R square take? Okay. Now think it this way, guys. Look at this formula. If the error between your if the errors of your regression line let's say, is what? Let's say 100. Okay. If this is 100, let me put it here again. This is case one. If your SSRES is equal to 100 and your sum of squared for your regression line or average line is also 100, and you know the formula is 1 minus SSRES over sum of squared of the total, which is nothing but 1 minus 100 over 100. This will cancel out and this will come out to be 1 minus 1, 0. Right? When do you think your regression line and your average line will have the same errors? Only in one case, when they are overlapping each other. Correct? When they are overlapping each other. So this case one is that your model is average line only. If your best line or whatever line that you have, either through logic or anything, either by hand you've drawn, if they if it is exactly like average line, you're just predicting the average only on the data set, you will have r square as 0. Is that what we want to do? No, right? We want to do better than the average. Anyone can simply, why are we learning machine learning if all we want to do is look at all the prices and just say blindly this is the average? Whatever features you pass me, crime rate, lower status, okay, whether it is a sea facing, it is not sea facing, number of rooms, disregard all the features and blindly say this is the average price of the house. That is your average line, and this 0 is not good. We want to move away from 0. Okay, because 0 is average, anyone can do that. Now the second case. What is the second case? 1 minus SSRES SS total. You have some error. Okay, in average you have some error, let's say 100. Now we are saying SSRES is 0, is the best line, having 0 error. Okay, and your SS for the average line is still 100. Now what is this going to be? It is going to be 1 minus 0 over 100. 0 over 100 is what? 0. So this is going to take what value? 0. Correct? This is the perfect line. Okay. So the idea is you need to be closer to 1 and far from 0. Is this idea clear, guys? Correct? So R squared is clear. So with this, you can compare different lines. If your R square is 0.6 and your R square is 0.8, which is the one which is better? 0.6 or 0.8 R square, which is better? We need to be closer to 1. So closer to 1 is 0.8. So the line which is giving you R square of 0.8 is better. Okay, cool. Now you understand why it is also called coefficient of determination. See, my style is that you need to be able to know the entire story. Okay, you need to be able to connect the dots. To connect the dots, this in-depth knowledge is required. Why they are saying it as coefficient of determination? You're determining which is your best model with the help of R square. Okay. And how you're determining? You're determining comparison with the average. No matter what line you predict, no matter what line you fit, if you are able to look at the R square, you're able to say that, okay, this is better than average by 60%, 0.6 means 60% better, 0.8 means 80% better. Okay, perfect. Perfect. All right. Far from zero. Okay, cool. So this is R square. Now, what's the next thing? The next thing is assumptions. This is a very plain theory, guys. I could have, told you that you guys go and explore it at your end, but I think it's better at least we touch upon this. It's you can read about it. There are 5 assumptions, and they're very straightforward also. So I'll cover it in short so that if there are any queries around this, we clear the linear regression from the root from after we have completed it. What is the pattern that you would be following for your preparation of interviews? You have learned linear regression in the sessions. Okay. Go back, explore, do hands-on, and then what you do? You locate the interview questions. Complete the interview questions, then you're ready for linear regression. That's how you do it. You will not do it like, okay, I've learned linear regression, I will do logistic regression, I will do this, I will do that, and once the entire module is complete, I will look into the interview question. Nahi. Complete linear regression once and for all. Okay, cool. So what is the first? Very simple. Let me do it this. It should have linear relationship. It works on linearity, right? Linear regression. So it should have linear relationship. Your independent feature with your dependent feature should have linear relationship. Correct. Second, multicollinearity shouldn't be there. No multicollinearity. Okay. For the ones who are not from the maths background, and for the others who must have forgotten this, what is collinear? Collinear. If a point lies on the same line as that of the other, this is the line. Okay. These 2 points, are collinear. Okay. They're lying on the same line. So when I say multicollinearity, it shouldn't be present. Meaning, if you have feature 1, you have feature 2, you have feature 3, you have feature 4, and so on till feature n. They should not be giving the same information. Meaning, they shouldn't be collinear amongst themselves. You are predicting target 1 using feature 1 to feature 2, feature n. This is you're predicting target. The relationship between feature 1 and feature 2 shouldn't be linear. Okay. Meaning they shouldn't be on the same line. What is the example? In the car example that we were looking at, when you're trying to go and sell your second hand, you're trying to sell your car in the second hand market. If I say car's age, okay, and number of years since you bought the car, isn't they the same thing? Correct? They're telling you the same thing, right? If you purchased a car, purchased in what? 2020 was a really wild year to purchase a car since we were in COVID. But anyways, if someone did, okay, what would the age be? Age would be 4, and number of years since you bought would also be 4. Correct? So they're giving the same. It is basically just a different name, but they're giving the same information. to the model. No additional information is being given. Okay, cool. Then the third example is that your errors. Okay, I'm saying errors, but when you look at the literature, they will say residuals. And you know what errors and residuals are. They are one and the same thing. Residuals should be or should be forming a normal distribution. Okay. If you go and plot your errors, okay, they should follow this kind of a curve. Okay. They should be normal. Very simple, right? Cool. Then what is the fourth one? This is something that people ask. Okay. That's why I'm putting a star mark. Not because it is different, it is very easy. It's just that the name is really different. Okay. And they try to test whether the person has this knowledge or no. Okay. So it is what? That your error should be no heteroscedasticity. Okay. No heteroscedasticity in errors. Or in other words, it should be homoscedastic. You get the gist of it. Okay. Now, why they ask is because this heteroscedasticity and the homoscedasticity doesn't, really understand. People don't understand it really well. So what happens is you understand the word hetero and homo. Homo means same, hetero means different. Okay, homogeneous mixtures and heterogeneous mixtures. Now, your if you fit a line, okay, your variance should not be like this of your data set. This is your data set. Okay. Let me make it more clear. As and when this is increasing, okay, this is increasing. This is also increasing in different proportion. The variation is really different, right? This is not required. This shouldn't be the case. This should be the case. Okay. It should be equal on both the sides. Okay. This is heteroscedasticity and this is homoscedasticity. See, it's difficult to say also. This is what you're looking for. Okay. And the last one is autocorrelation. When I say autocorrelation, there shouldn't be any autocorrelation or no autocorrelation. This is mostly related to the time series kind of data because that tells you, that was, if you remember in the first session, I told you there is a difference between regression and time series, which is different and is very minute. You need to remember it. It is time based and it is not. Regression is not time based. Time series data is time based. Okay. Now here, what do I mean by autocorrelation? Correlation, you understand, there is some correlation. If you break the word, auto in this context means with itself. So previous values should not have relation with future ones. In other words, future values. This I'm talking about the target, okay? Target. Your future values of the target should not depend on previous values, previous or past values. Okay. With this, linear regression is complete. There is n number of, text or literature that you can refer. There are many different types of regressions as well. Linear regression itself, go and explore it. Okay. I highly recommend that you go out of your comfort zone, go and recommend it. You have the base now really strong. With these sessions, your base is really strong. The more you explore, the more it will become beautiful. Your knowledge will become beautiful, and the interview will be like, yeah, this guy knows basics so good. And then he knows all the varieties also. There are small minute changes, and they call it with a separate name. Internally, this is what is happening. Okay, perfect. So this was linear regression. Now we are going to start with logistic regression. Okay. Now, what is logistic regression? It is a classification type. It is classification type of an algorithm. Okay. Target variable is how? Target variable will have categories. Okay. It is either 0 or 1. Example would be spam or not spam. Okay. This is an example. Okay. Now let's look at some theory around it. Let me introduce you to this. Yeah. Now we looked at machine learning. We talked about the third also, which was what? Reinforcement learning, right? But I told you 90% of the times you'll be working on supervised. Okay. Now we looked at the supervised first, we looked at regression, and we looked at linear regression, right? Now we are looking at classification. In supervised, when I said supervised, it is based on, supervised is based on label data. Okay. It should have label. So in classification, there are two things. One is logistic regression, which is what we are going to study now. And there is another which is called SVM. SVM is nothing but very popular classification model and has been since for a long time. I have personally used it a lot, and it stands for support vector machines. Okay, really beautiful concept. If you go into the depth of it, really mind blowing. How these statisticians and these people who were doing research, they came up with these examples and these thought processes. It's easier to understand, but when you have a blank slate and you have to come up with this, it takes some courage. That's why they are there and we are not there. Okay. But we are learning from them. So logistic regression is a classification model based on statistics. Okay. Deals with categorical target variable or dependent variable. Okay. Could be binary or dichotomous. Now, binary, you understand binary. Dichotomous is same as binary. If you don't know the meaning of it, it comes from biology kind of, perspective, since they were researching it. So it's just stuck with this algorithm. Just keep that in mind. It works on dichotomous variables or target variables when the output is 0 or 1. When I say 0 or 1, not literally 0 or 1, it could be 1 or 2 also. Depends on how you're coding your target variable. Okay. But there should be only two categories. Okay. There should be only two categories. Multinomial, I'll touch on that, but just say that, it could follow anything. It could follow anything. There could be this thing, nominal and this thing. There could be many. Just ignore that point for now. We'll touch on that. Okay. Now takes both continuous and discrete input data, meaning your independent features can be either continuous or can be discrete. Okay. There wasn't any discrimination in linear regression also, correct? You could do anything. And here also there is nothing. In independent features, there are certain algorithms. Why it is necessary to put that out? There are certain algorithms that work on all these kind of things. They work on discrete also, but the way that you have to put that information inside the model needs some modification. Needs some, when I say modification, needs some encoding. Okay. Like for example, XGBoost. We are going to look at decision trees, random forest. Okay. Some of them, they need different kind of modification of the discrete type of values before we apply the model. That is why it is kept there. Okay. So regression is the one where you are predicting your uh, continuous variable. So regression, your target variable will be continuous. Meaning like predicting what? House price. It can take any value, no? 100,000, 10,000, 1 lakh, 20 lakhs, 20.22 lakhs, whatever. Predicting car price. Okay. And what was classification? You need to classify it, either this or that, or out of many things. So remember, we looked at these two examples. Your target variable is discrete. When I say discrete, it has one or the other, meaning you'll understand from the example. Spam and no spam. Either it is spam or not spam. Correct? The other example was where you guys looked at my beautiful drawing, fruit example. Now we looked at in the concept of clustering, unsupervised. But there are three: apple, banana, and orange. You have only what? Three categories. You're providing the features and you're also labeling. Given the label is there, then it becomes a classification problem. The other example, okay? The other example would be, now you have cars, correct? I'm relating it with this so that you're able to understand. You have cars. Here you're predicting the car price. But if you had to predict the type of the car, now the car can be what? Car can be an SUV, higher segment. Then it could be a sedan. Okay. It could be a hatchback. Correct. So these are different types. When you are given this data, car type, and let's say you are given engine, okay, what else? Seater, ground clearance, meaning how up it is, ground clearance, whatever, okay. And you are told this is an SUV, this is a sedan, this is a hatchback, and whatnot. This is your target variable. Okay. So your target could be, depending on all the features that you have, it could either be SUV or a sedan or a hatchback. You have only three options. Options is not the right word, but for understanding, I'm saying 3 options, but you should always say 3 categories. Okay. So now you understand what is classification, but your logistic regression works on only binary. Binary output. Only 2. Logistic regression will work when you have only 2 categories in your target variable. Okay, I'll have to slightly digress, but let me explain this. This is important for understanding. Now, tell me one thing. Tell me one thing. When you say hatchback or when you say SUV or when you say sedan and you pass it to your algorithm, which is on your laptop, okay, it will be like, what are you saying? Will it understand hatchback, SUV, sedan? No, right? What does computers and everything that you work on digital, they understand based on numbers, bits, binaries. That English is our language, Hindi is our language, this is our language. These things, they don't work on machines, they don't understand that. Okay, so what happens is, on the same data set, you are encoding it. Okay, I'm not putting in the additional columns, but you get the gist of it. Let's say this is car type. This is hatchback, then sedan, then this is SUV, then hatchback. Okay, what you are doing is you are saying, whenever I see a hatchback, I will put 0. Whenever I see a sedan, I will put 1. Whenever I see SUV, I will put 2. Okay, this concept is called what? Encoding. You are encoding it for the machine to understand it. It will not understand what is hatchback, SUV, or sedan. It will just say that all the zeros are separate, all the ones are separate, twos are separate. Okay, these are 3 categories. Now, when we do it on label, it is called label encoding. Okay, there are different types of encoding also. We'll cover it into the future, but there is something called as one hot encoding. Okay, then there is TF-IDF, term frequency and inverse document frequency. This is the concept of NLP. Let me relate this with a really good example, which everyone must be using. Okay, everyone has looked at ChatGPT or understands what ChatGPT does. Correct? You are typing in words. You are typing in words, but it doesn't understand the words. Internally, what it's doing is it is doing this encoding. It is doing this encoding. And over there, the concept is called embeddings. There is way further or of much detail, concepts there, which also say tokenization and embeddings. And there are many things, but did you understand? It is not non-numeric. Okay, it is not non-numeric. You are, no matter what you're getting, you are doing some kind of encoding for it to be understood to your machine. Okay, perfect. One hot encoding, it is this. One hot. This all concepts are coming from the English speaking community. So one is 1, hot is nothing but 0, 1 0. Okay, it is nothing but 1 0. This we'll learn in decision trees and random forest, but this is how you're encoding. Okay, perfect. So we just introduced logistic regression. Okay, it works on binary output. Then classify it is a classification type. Your target variables will have categories. Actually, in fact, these two should be same only, but I'm just connecting it here. Okay. And then this is your example. Okay. Then we looked into a difference between regression and classification. We covered it here. Then to answer a query around non-numeric data, to have that intuition and understanding correct, it is not only non-numeric, it is also, we pass all the non-numeric or anything textual thing by encoding it, because that's how the machines understand. Okay, cool. So here, some of the use cases. Let's look at some of the use cases. Okay, so now Olympics is going on, correct? Olympics is going on. So let's take an example from Olympics. Let's say Neeraj Chopra will win or no. I hope you know who Neeraj is. He's a guy, okay, with long hairs who throws javelin. Okay, this is my javelin and this is the field on which he throws. Okay, he's an athlete, Indian athlete. He won gold last time. So we are saying what? We are saying win or lose, right? This is what 0-1, correct? The other example, World Cup. Will India win? Yes or no? There is nothing in between, right? It's clear. Either we will win it or we'll lose it. We are not going into the rankings that they'll reach semi-final or no. Our motive is only to say whether we are going to win or lose, yes or a no. Okay. The other example, we have been looking at it. Email. Spam. We say it's spam, not spam. If you ask a question, is it spam or not spam? Again, the answer is yes or a no. Correct? Fourth, is the cat fat? Yes or a no? Outcomes in all these use cases, whenever your outcome is either this or that, binary output, binary output, that's when we use logistic. Okay. Now some of the real world examples. Imagine, okay, you are the owner of Geo Cinemas, for example. Okay, you're pretty rich, but still, you are the one who is responsible for getting the profits. Okay, now you need to know using machine learning. This is an actual real world example. Can you predict whether a customer is going to churn or not churn? Customer churn. So this is how churn means whether uh, they are your members. Okay, you've paid, you've taken the prescription subscription, sorry, of that, Geo Cinemas, Netflix, whatnot. Okay, are you going to churn? Meaning, will you leave? Will you stop your subscription? That is called churn. And when you do this for the customer, you mean to say whether you're going to churn or not churn. Okay. So this is for anything. Could be Netflix. Okay. Could be Geo, could be Hotstar, anything. Okay. This could also mean for a in US there are these Walmarts. Okay. Here we have D-Marts, Walmarts and D-Marts. You need to know if your customer is going to churn or not churn. Okay. You must be using some Wi-Fi's, whatever brand, let's say Airtel or Geo Fiber. What else? Who is there? Oh, Act, correct? All these folks, they need to know whether their customer is going to churn or not churn. Meaning, are they going to stop their services and not renew it? This is a big problem, guys. And if you are able to identify this with high level of accuracy, you can stop the customer from churning. You can give an additional discount, an additional something, okay, that will stop the customer from not renewing or going off your platform. The other example would be Swiggy or Zomato. So Swiggy would like to know whether a person who is ordering from me today, tomorrow, from next month onwards, okay, is he going to churn? Mean, is he going to stop ordering from me? Not completely. Probably the what do you have? That Swiggy Super is there, no? And Zomato Gold is there. So is he going to stop using that and switch to Zomato or not going to switch to Zomato? I don't care. All I care about is he or she going to stop my service or not? Is he going to churn? Is he going to switch? Why is this such a big problem? Because big problem because customer acquisition is really high. Customer acquisition cost is high. They want to, so to make you the customer for the first time, they have spent so much of money. They have given you marketing on the TVs, on your phones. Okay. They would have, have one person calling you, not directly for you, but they're spending on their ads, right? You must be seeing these people, they put really big banners on the roadside, correct? They also give some TV commercials, TV ads. Then they also sponsor some of the teams in tournaments, correct? So they're spending for what? So that people see that what is, if there is a person who doesn't know what is Swiggy, okay, and really likes food, if they know that there is, through these advertisements, they know that okay, there is something called a Swiggy. Out of curiosity, they'll be like, yeah, I'm seeing this everywhere, who is this Swiggy? If they search and they're like, Are, he's giving me free home delivery and all, I'm sitting at my home, he'll give me food that I've ordered and I have so many options. All these things are on convenience, right? It is for the customer's convenience. You're getting food at your home. You are able to order something which is 20 kilometers from your house, okay, without going there. And you're still getting that whenever you want, when you're ordering. So everything of this is on convenience. So if a new customer looks at it, they most probably will find it convenient and they will enroll into Swiggy. And then it is Swiggy's different game of marketing. First thing is to acquire the customer. And to acquire the customer, once it has become my customer, now there is a different game altogether. It is called CLTV, which is customer lifetime value. There is a journey that a customer takes in the business. Okay, read about it. It is an interesting concept. How people think about it. Read about it whenever you're free. Okay, so this customer churn is really important. So they need to find a way that I can predict which customer is going to churn. Is going to churn. And when you say churn, ML models, they don't work on 100% guarantee, right? Even with linear regression, we knew we are predicting and there could be some errors. So they work on what? Probability. This is in the first class I told you. It is 1 - 1 game. Correct? They tell you this is the probability of a customer to churn. Let's say if the probability is 0.8, meaning 80% it is going to churn. The not it that person is going to churn. Customer is going. Then can I also say 20% no churn? There's a 20% probability that it will not churn. Correct? It is 1 - 1 game. It works on probability. Okay. Now these are some examples that we looked at. Now in linear regression, what we were doing, we were fitting a line. Now, if you look at a data for classification, how will it look like? Okay, let's take an example of email, spam and not spam. Okay, because it is an easier example to understand, and same is, we can apply it to anything. The idea is to understand the concept. Okay, this I'm saying, I'm going to say that they are spam. And here on my y-axis, I have all the ones which are not spam here. Okay. And there are a few keywords. Remember, it is going to look at the patterns, and keywords would be what? Keywords, if in the mail content, these keywords come, you are able to say whether it is a spam or not spam. If it says lottery, correct? Win, prize, jackpot, if these keywords, these words are present in the content of your email, this means that it has a high possibility of being a spam. More these words, higher is the probability. If in an email I see there are, three of them coming, three of these keywords coming in one email, three keywords present versus another email in which one keyword is present, which has a higher possibility or a probability of becoming a spam or being a spam mail. Let me change this to 3 to 8. If 8 keywords are present versus one, right? The one which is having more number, correct? Everyone with me, right? So this is going to have higher probability. This is going to have a lower probability. This is going to have a higher and this is going to have a lower. Okay. Now, let's say here are your number of keywords, number of these keywords on your y-axis. Now let's say this is 1, 2, 3, 4, 5, 7. Okay. This is how it is. Let's say an email that has 4 or 5 keywords. Let's say 5. It has 5 keywords. Am I not going to say that it is a spam? Correct? The one with 6 can also be a spam. 7 will also be a spam. Okay. There could also be instances where when I see only one keyword and it is not a spam, 2 keywords, it is not a spam. Okay. Sometimes there might be 3 keywords and still it is not a spam. And vice versa can also happen. There are 2 keywords present there. Someone is really sharp. They've taken only 2 keywords, but still it is a spam. Okay. An example would be, hey, you have been shortlisted by KBC. You have won lottery of 10,000, 1 crore. I used what? One and lottery. But this is a typical spam email. WhatsApp pe now these days they send you a lot, but do you agree? There are some exceptions. Someone can be really sharp and just use only one word so that even they know that someone who's reading this content, the whole idea is that they should click. Once they click, enter their details, then gone. Money is gone. Your hard earned money is gone. So this thing can happen. Similarly, there could be, you know, a genuine email which has 5 keywords, but still is not spam. Your friend has sent you this email saying that, hey, what? Hey, Anil, I am really happy to say that, I have won a lottery and the prize money that I'm getting from it is, let's say 50 lakhs. I think I have hit a jackpot in life. I've used all the words. But this, your friend has sent you. He's not asking you to, you know, press on any link or anything. So it is a genuine email. So this case and this case, you understood, right? There are exceptions. Now, since we are able to do this, whether this is a 0 or 1, okay? Now let's say I am saying when it is a spam, understand the concept. I told you that when you have to encode it. I'm saying the spam is 1 and not spam is 0. Okay. All the spam in your y-axis, you have either 0 or 1. Earlier you were having what? Continuous variables, continuous values. Now you are having only 0 to 1. And there are only two values that it can take, either 0 or 1. That we know. For logistic regression, that is the case. Now, the concept is same. We have to fit the line. But can I fit this line? Can I fit this line? Or this line? No, right? I cannot. Which is the line that I need to fix? Okay. The line that I can fit could be something like this. Could be something like this. It looks like an S, correct? So that you're able to classify all these correctly. This one, this one, this one, and this one, this one, this one. You're able to classify it correctly. This one you were not able to, this one you were not able to. Here, the line is not going to be a straight line. It is going to be a curvy line. Okay. So now you have a data set. Now you have a data set. One email. This is one email. This is one email. This is one email. Okay. You are trying to fit the line on the entire data set. Over there in linear regression also, we were trying to fit the line in the entire data set. This is your entire data set. All the emails together. How many do I have? I have 8. Let's say you have 8 emails. Okay. The best line with which you can reasonably fit is that you can correctly identify 3 here and correctly identify 3 here. 3 in spam, 3 in not spam. But you're not able to identify this correctly, this correctly. Why? Why? Because same concept as that of your linear regression. Now, if I go, this is my line, this yellow is my line. Let me draw this properly. Okay, this is my line. Now, whenever you are trying to, in linear regression also, what we were doing, when I have to look at something which is at having two keywords, I used to plot it on my line here, and then look at its value on the y-axis. Correct? This is what we used to do, right? Here, this value is telling me that it is closer to not spam. So I'm going to say that it is not spam. But this, in reality, this is the one, and this is the actual. So this is an error. Or here the errors are called misclassification. Everyone with me, do you understand misclassification? This one and this one are your misclassifications, correct? And this one and this one, all these are correctly classified. What we are trying to achieve here is we are trying to fit a line such that our misclassification is less. Okay. In this case, when there is a 0 and a 1 output, you cannot fit a straight line. It has to be a curvy line. Now the curvy line is this type of a line that we are able to fit, which is S shape. Okay. This is what? S shape. Okay. And the motive is similar to linear regression, that your error should be minimum. Here in this case, the misclassification should be minimum. Okay, cool. The other example, the other idea is that here on the y-axis, you have 0 to 1. Okay, doesn't it tell me that it is the probability? Somewhere in between, this is 0.5. If there is a value that is coming here from out of this one, anything greater than 0.5 is going to be spam, and less than 0.5 is going to be not spam. Correct? Based on this curve, based on whatever plot you do here, anything, if I plot it on my y-axis, if it is greater than 0.5, it is going to be spam because it is closer to spam. And anything which is less than 0.5 is going to be not spam. The chance of it being a not spam is more because it is closer to the one where it is not spam. Okay. Now this 0.5 is also called a threshold or a criteria. This you have in your hands. Depending on use case to use case, you can either take it as 0.5 or 0.7 or 0.4 or 0.6. I don't care. Depends on the use case. You have this in your hand, looking at the data. Okay. And all the values here in between 0 to 1 can take any value. Now you understand, since this is 0.5, it can take even 0.0002. It can also be 0.112. It can also be 0.234. It can also be 0.67. This is nothing but this is probability. This y-axis is a probability. You have this data. You have this data. Okay. Okay. Now you have this data set with you. Is the same thing, correct? Let me clean it a bit. It is the same thing that we plotted above. Now tell me one thing. Are you able to see that in this yellow line, this is not present, and in this yellow line, this is not present? If you try to plot, let's say I have 7 here, I had 7 here, right? If I plot the number of keywords in an email, if 7 are present, if I try to plot it here, will I not touch the line here? So what does this value have here? It has what? It has 1, which is nothing but spam. Okay. So now here, when you are at 2, you are trying to touch the line, your line that you have fit. And when you try to plot it on the y-axis, it is what? It is, let's say, 0.01. Here is your 0, and here is your 0. And this is what? This is not spam. Correct? And you're going to say this is 0.5. Your criteria is any probability in this line. If it falls anything between this, I'm going to say it is spam. Meaning anything, if the probability is greater than 0.5, it is going to be spam. And if it falls in this region, which is less than 0.5, it is going to be not spam. So this one, rather than calling it as an error, you are not able to classify it correctly, na? It is spam, but you are still saying that anything which has 2 keywords is going to be not spam. But this is spam in reality. This is your error. And error in classification is called misclassification. Okay. So in general, since this is probability, in general, threshold as a thumb rule is chosen to be 0.5, 50% here, 50% there. But depending on your use case, you can change that value. It is in your hands. It is in your hands, depending on what you're seeing in the data. Let me give you another example. So that you understand this threshold thing. Okay. Now, imagine another use case. You are working with HDFC. Okay. And I come to you and I say that, can you give me a loan? So what do? What is your problem? Understand this. Your task is, should I be given? Okay. Since you are going to read it at your end, should you give loan? That is your problem. Correct? That is your use case. That's the you want the solution for this. You mean the other way to look at it is, if I am coming to you, okay, let's say this is who is asking for loan. Okay, asking for loan. You need to say whether he or she is a fraud or no. This is what? Another example of 0, 1. Yes or no? Correct. So here again, logistic regression will come. But tell me one thing. Out of, let's say you receive 100 applications. You receive 100 applications. How many of them are fraud? Only 1%? Or in, imagine we are living in a really bad country. Even then, this would not be more than 5%. Terms and conditions applied on the country, as in, depending on the country, it might be 10% also. But in my experience, this is really huge. Even 1% is really huge. Okay. Now, this is also called as imbalanced dataset. Imbalanced dataset. Here, out of the 100, 95, 95 are not fraud. Okay. And only 5 of them are fraud. Now, in this case, do you think 0.5 will be a good choice? No, right? No, right? Now you understand how you need to put it really tight. That threshold should be really tight, meaning that 95% of the times I don't get a fraud application. There's only 5% chance. So this line here, this threshold here will not be 50%, correct? It will be somewhere here. Okay. So that's how you change your threshold. And that's why you have it in your hands. And that's how it depends from use case to use case. Understood? Is that clear? All right. Okay. Now you know this. And now you know that it is an S shape. Now, did anyone tell you, or do you know why S shape? Why only S shape? Why cannot I put a Z shape? Why cannot I put a C shape or an invert C shape? Right? All these are possibilities, right? If I put a graph here, all these are possibilities. Why S curve? Isn't this something like a parabola? If I just twist it, parabola is like this, right? If I just change it, will this not be expressed in mathematical concepts, mathematical equation? It will be, right? So all the statisticians in the world, all the data scientists, machine learners, machine learning engineers, research scientists, they looked at all these curves. You and me, we don't have to. They looked at all the possibilities in the world and they said this S shape curve is the only way that we can solve this problem. Imagine we looked at the curve, right? We looked at how we interpret it. So imagine this is your keyword at 2. Okay. And this is at 3, 4. Now at 4, if you try to plot it on your curve, will it not give 3 values? Will it not give you 3 values here? Correct? This is spam. This is not spam. So for one input, you're getting 3 output. You're saying there is a possibility of this being not spam, and this is the possibility of being spam. This is the possibility of being spam. Only in one input. Will that solve our problem? No, right? For each observation, I need to tell whether it is spam or not spam. For each email, I cannot say that, there is this possibility, and this possibility. Then what is the use of machine learning? Here also, you'll get 2 points. Correct? So the idea was all these people, all these research scientists, they looked at everything and they found S curve to be the best. S curve to be the best, which could help us solve this problem. Or S shaped. And could easily be converted to mathematical explanation. Okay, cool. All right. So now you know why. Okay. And you know how we are fitting a S shape. S shape. 0 to 1 probabilities. Now, I need to take you through one really important concept inside this for you to have further understanding in the logistic regression, okay? Which is called odds, okay? And how it is different from probability. Okay, this is a good concept. Now the idea is, let's say you have 5 red balls, okay, and you have 3, everyone from the non maths and non-tech background. We are revising a concept. I'll take you from the basic to explain you this odds concept, which is not really easy to understand. Okay, so pay 100% attention here, everyone. Okay, this is a really good concept and really a base concept for you to understand logistic regression. Okay, now when we used to understand our what probabilities, correct? So probability was what? The definition of probability was number of events when it was successful, when success you have, okay, based on what you have, over total number of events. Correct? This was the definition. Now you have to give me an answer. Out of this, you have to tell me what is the probability of picking a red ball. Tell me. Look at this. This is the definition. 5 by 8. Correct? 5 by 8. How did we reach to 5? This is the formula for probability, number of events when success. So you'll be successful when one of these balls are in your hand, which is one of the 5. So you can be successful out of 5 in 5 events, correct? Out of total number of events. Total is what? 5 here and 3 here. So 5 plus 3, 8. This is the probability, correct? Now, odds. Odds is slightly different. Okay. What is odds? Odds tells you the likelihood of success with respect to failure. Okay, this is the very crude and very simple definition of odds. It is the likelihood of success with respect to failure, not with respect to total events. Understanding? Okay, so in the same example, okay, if I say what are the odds of picking a red ball? What are the So in this there is another concept of favorable and unfavorable. I am just saying whatever I am saying, it is favorable. Okay, what are the odds of picking a red ball? 5 by 3. Why? Imagine this to be success, number of success events and number of failure events. This is your odds. Meaning in this case, it would be 5 and you could fail in 3 of them when you pick one of the yellow balls. So this is your odds. Okay. So what you're doing is you're doing 8. 8 is total events. You only need to count failures. You're saying how likely am I to be successful compared to my failure, not probability of me becoming successful. There's a very slight difference But once you go through this concept now, once again, revise it, you'll be able to understand it. Okay. It's slightly mathematical. I've tried to, simplify it to the core of it. Okay. Perfect. Cool. Now you know what is odds and what is probability. To concrete this concept further, let us understand a few more examples. This, okay, is fine. We've already looked at it. Where is logs? Huh. Okay. So this is one concept. Let's say this guy went for fishing 5 times in a week. He caught a fish on 2 times and he failed 3 times. Okay. So the probability is what? Probability is chances where he was successful over total chances. Okay. So he was successful in catching the fish twice. Out of how many times did he go? 5 times. So 2 by 5 is the probability. But odds, what is the odds? Odds is number of times when he was successful to catch the fish and number of times when he was not able to. He failed to catch a fish. Okay. So these are your odds. Another example, ignore this log it and everything. Another example is so this is the predictions, okay, of a rainy day and a sunny day. Okay. Now the odds of catching a sunny day is green means yes, red means no. Okay. The odds of catching a sunny day is 2 by 3, 2 over 3. Okay. And the odds of catching a rainy day is 3 by 2. Red is yes, green is no. Okay. 3 by 2. There was rain on 3 times and it didn't rain on 2 days. So 3 by 2. Now you could also take a ratio of these. 2 by 3 divided by, this is what they are doing here. Okay. You could also take a ratio of this. Now this ratio is called odds ratio. This ratio is called odds ratio. Okay. Let's do one thing. Why am I teaching you this odds concept? What is the reason behind this? The reason behind this is that whenever you are doing logistic regression, then when we were doing here, okay, we understood the curve has to be fit in an S shape. But at the end of the day, I am comparing my spam with not spam, right? I need to know an email is spam, how likely it is to be a spam, and how likely it is not a spam. They have to compete against each other, not out of how many I have spam. For one email, I have only two decisions to make, spam or not spam. So I have to compare these two. I need to compare the odds. I need to compare what is the likelihood. The keyword is likelihood of an email being a spam and a not spam. That doesn't come from probability. It comes from odds. Okay. That's why it is very similar to probability. So it is easy to get confused, but that's the minute difference. I am deciding for an email or a 0 1, okay, win or a loss, fraud or not fraud, whatever example you take, I am competing with the other one. So I need to know my chances of success compared to my chances of failure. In other words, my chances or my likelihood of catching a fraud person versus my chances or likelihood of not catching a fraud person. Understood? Okay. Keyword is likelihood. So it's not plain probability, it is odds. Perfect. Now you know this. Now you already know this. Let's move into the logistic regression further down. Okay. Now look at this very clearly. Okay. Can I say odds is equal to probability over 1 minus probability? Can I say that? Let me give you an example. Why I can say that. So in the red marble and the yellow marble example that I gave you, okay, Over there, the probability was what? Probability of catching a red ball was 5 out of 8. Correct? And let me put this in this way. Red, it was catching a red ball was 5 out of 8. Okay. And catching a yellow ball was what? 3 by 8. Everyone with me. And what was the odds? Odds was 5 by 3. Now you understand where I'm going. Can't you say 5 by 8 over 3 by 8? This 8 and 8 will cancel. Will it not left? You will have 5 by 3, which is same as odds. Probability of getting a red ball over probability of not getting a red ball. Isn't that odds? If you're successful, that is probability. And over not or being failure, can I not say failure is probability of not being successful? Correct? Okay. So now let's derive a few things. Okay. This will be very, just follow me. We are not doing really high rocket maths. It's very simple. Okay. Two things I need my non-tech guys and also people from tech background and mathematics background to remember or revise this. When you have to take a log of A by B, what is this? This is nothing but log of A minus log of B. Correct? If you have not studied this, this is the property. Okay. This is the property of logarithm. I have not derived this. It is already there. Okay. Now we know odds is equals to probability over 1 minus probability. This is your first step. Second step, take log on both sides. What will happen? This will become log of odds is equals to log of P over 1 minus P. Correct? Okay. And I'll tell you what is the equation of sigmoid function. Sigmoid function is nothing but 1 over 1 minus e to the power minus x. This is your sigmoid function. Okay. Why I'm telling you this is because in linear regression, our equation was y is equals to mx plus c. Correct? In logistic regression, it is this. 1 y is equals to 1 over 1 minus e to the power minus x. Okay. That's why we are going to reach from here. From here, what we learned, odds to probability to this equation. How do we reach there? We're going to derive it. And trust me, this is the line that we'll be working with. This is the line that we have been working till now in linear regression. Okay. Now we already know it is an S shape. Don't take my word for it. It is the S shape that in logistic regression we have to use. And how do I say it is going to follow this? It is going to be this. How do I say this? Let's prove it. Okay. We'll go into mathematical derivation also, but I want to show you this as well. Okay. This is Desmos. It's nothing but a chart, right? Now, what happens is if I put an expression here, which is y is equals to 1 divided by e to the power minus x. Okay. Don't you see this is an S-shaped curve? This is the equation, guys. Y is equals to this. Okay. If I zoom in, whatever we have studied till now, it cuts exactly at 0.5, and it does not go, whatever the value of x is, it does not overlap 1. Basically, it is asymptotic to 1. And on the negative side, it is asymptotic to 0. What have we plotted here? We have plotted this. Okay. This is the best curve for us to say whether it is 0 or 1. Correct? S shape. And this is the equation. I'm proving it to you right now, showing you visually at least. Are you able to understand that this is the equation for us to get this kind of shape, an S shape? No matter, is it going above 1? No, right? It is not. Is it going below 0? No. Correct? Okay. This, let's say y is equals to e to the power x. Okay. This is the graph, and y is equals to log of x. This blue line is log of x. Okay. And this is your e to the power. Exponential, opposite of exponential is logarithm. Okay. So this is the graph of logarithm, and this is the graph of exponential. And I'll tell you why we need this. Okay. I'll show you. Here is why we need it. So for example, y logs. Okay. Let's say you have 3 to the power x is equals to 9. Okay. Can you not write it 3 to the power of x is equals to 3 to the power 2? This is 9. 3 to the power 2 is 9, right? So with this, can't you say x is equals to 2? Correct? That's why for these, we take exponentials. This is nothing but this is exponential. Okay. And sometimes when these things are really complicated, we take logs, because log is nothing but ulta of exponential. Okay. It is exactly the opposite of exponential. Okay. Now, homework. I need you to look at these two things. Okay. Homework 1, adjusted R square. In linear regression, we studied R square. We need to look at adjusted R square. Okay. Then there is something called as VIF. I cannot cover everything. Okay. I'll try to cover things that are important from the interview side and for you to understand. And I'm going to give you some homework that is going to improve your understanding, overall understanding. Okay. You need to tell me what is VIF. It is variance inflation factor. Inflation factor. Okay. And I'll tell you where you will see this. We looked at multicollinearity. You'll find it there. Okay. This will enhance your understanding of multicollinearity. Okay. And the third thing is log and exponentials functions. Just look at their equation. Just look at their graph, a few properties, graphs and properties. That's it. Cool. If you are able to do this, trust me, guys, logistic regression is going to be a cakewalk. Okay. And first two are for you for linear regression. Third, if you do, with me, logistic regression is going to be a cakewalk. Not only the explanation, the intuition, also the hands-on. Okay? These two are really base. Linear regression for regression and logistic regression for classification. Okay? Okay. So cool. Now what is adjusted R square? Let me take this up. First one, what is adjusted R square? So now R square we understood, right? It helps us to tell how better is our model with respect to the average line basis of the errors. And more the value of R, the R square, better the model is. The idea is to be around 1. So now, guys, they notice that there is a slight problem with R square. So adjusted R square came because R square will increase with increase in number of independent features. Why was that the case? So let me give you an example. So imagine you are trying to predict your exam score. Okay. You're trying to predict your exam score. Imagine you're going into the exam. Okay. And you want to predict your marks that you'll score out of 100 basis the number of hours that you have studied. Okay. So the R value, so I'm writing the problem here, predict the exam marks based on number of hours studied. Okay. So you want to predict your marks based on, or for a subset of students, you want to predict their marks based on exam score based on the number of hours that they have studied. Okay. Let's say you get an R square equal to zero 0.8. Okay. Meaning that 80% of the marks can be predicted. It is the model is better, 80% better, and they can be predicted based on your marks, the number of hours studied. Now imagine I give you another feature. I give you their favorite color along with number of hours studied. I give you the favorite color of a student, and I tell you that now go and predict your this thing, favorite color of a student, your marks. Now R square will definitely increase. R square will increase, but this feature have any importance? Will it tell you the favorite color of a student and will predict its his or her performance in the exam? No, right? No. So to penalize the R square, so R square always increases with the number of features that you pass in, okay, to your model. To give some sort of penalty to R square, they came up with something called as adjusted R square. So adjusted R square penalizes your R square. Internally, it is the same thing. It calculates the same thing. There is some relationship between adjusted R square and R square that is up to you to figure out. But in that formula, you will notice that it penalizes your R square. It penalizes R square based on predictors. Okay. It also has based on number of predictors. It gives more importance to the ones where the feature is actually important for your model. So in the above case here, adjusted while the R square will increase, okay, but adjusted R square will most likely be same or it will reduce. Okay, that's the concept of adjusted R square. Now, what is the next one? Okay, VIF. So I also told you that it is coming in multicollinearity. Okay, I give you a hint. So let's look at the other example, VIF. Now VIF is variance inflation factor. It is used to detect the multicollinearity in your data set. Okay. The concept is very simple. The concept is very simple. Imagine you have four features, feature one, feature two, okay, feature three, and so on, and feature four. These are your independent features. Independent features. What VIF will do while doing that linear regression or finding a multicollinearity, it will internally try to plot feature one with feature two. It will try to do linear regression between feature one and feature two, then feature three with feature, or it will do the same thing, but just to maintain the consistency, it will do it like this. It will do with feature one with feature four, and we'll try to see if there is a linear relationship or no. If there is, then the VIF value will become very high. It will become very high if there is a multicollinearity. Okay, it will become really high. And you will have to, whenever you're running your linear regression, you have to remove the feature with really high VIF. Okay, remove it and run the VIF again, run the linear regression again. If you still see some relationship, some feature having a VIF really high, remove it, do it again. That way you'll be able to eradicate your multicollinearity. Okay, all of you with me on both these concepts. So this you don't have to do. It will automatically calculate VIF. It will automatically calculate VIF. There's these things in the linear regression, but you need to know how to implement it, how to even think about VIF. Okay, so that was the idea. Okay, cool, cool. So the other thing is, what was the other thing? Log and these functions. Exponential graph. Okay, we'll go to the images. This is your exponential graph, and there should also be exponential and log. Yeah, yeah, this one should be fine. Yes. Okay, so this one is a to the power x, which is like this, and this is log with base a to x. This is how the graph looks like. Okay, two things that you have to remember for the log is, in this graph, log 1 is equal to 0. Okay, when log 1 is equal to 0, and log of 0 is minus infinity. Okay, and what will this value be? And this is the value of e to the power x, or a to the power x here. E to the power x is also similar. Okay, cool. Okay, so I will remove this 3 we've already covered. Now let's go into logistic regression in deep detail. Now, the idea is that we had this graph, correct? We had this graph which had a line like this, and we had a few males here, okay, which were spam. And then there were a few here which are not spam. Okay, cool. So there were a few here. And here was your keywords. Keywords, high security keywords. We looked at them, lottery, price, and all those. Okay. So this I will categorize as 1. This I will categorize as 0. So we looked at this. Now, how did we come to this? Okay. The idea, we talked about log of odds, correct? We also said this is 0.5 here, somewhere in between. So the idea is that we looked at, now this is one value and this is zero. Originally, I also told you that we have to be slightly different from probability. We have to move towards odds because we have to compare whether it is a spam or a not spam. Okay. Out of not the total, we have to consider the odds. So we had looked at this formula that odds is equal to probability over 1 minus probability. Okay. So if we take the log on both the sides, this will become log of odds and this will become log of p over 1 minus p. Okay. This is what it is. Now, what I also told you, the property of log is of log that you need to remember is log of a divided by b is equals to log of a minus log of b. Okay, this is one property. Now, what happens is, let me pick this here again. So now we have this. Okay, what if? Let's look at two cases. What if? Case one, probability is zero. Okay, if the probability is zero, will it not be this that I will be, my log of odds will become what? Log of 0 over 1 minus 0. Correct? I'm putting just the value of p here. Okay. So what will this become? This will become log of 0 minus. Now we are taking advantage of this property and we are going to say log of 1. Okay. And just now from the graph, what did we see? What did we see from the graph? Log 1 is what? Log 1 is 0. And what is log 0? It is minus infinity. Meaning it will become what? Minus infinity. So this point, when I'm saying it is 0, this is log of odds, right? So if it is 0, can I say, let me put it here. Okay. So we're looking at this case 1. Let's also do the case 2. Let's also do case 2. Case 2. When probability is equal to 1. Now in the same formula, log of odds, I'm writing it again, would be what? It is p over 1 minus p and p's value is 0. Oh, sorry, 1 here in this case, in case 2. Then it will become what? This is log of this. Then this will become log of 1 over 0. Correct? This will in turn become log of 1 minus log of 0. Look, with this property, we are changing log 1 by 0 to log 1 minus log 0. So log 1 is what? Log 1 is 0 and minus of, and what is this log 0? It is minus infinity. So minus is plus infinity. Okay. So what is happening is, I'll tell you geometrically how you have to intuitively understand this. You have to intuitively understand this with this concept. Let me paste it here. Okay. So this graph, imagine it was here. We were here between 1 to 0. Okay. We have looked at 1 to 0. And now will these values which were at 1 with the concept that we proved here, when it is 0, it will go here. These ones will go to minus infinity. Imagine I have this with me. Okay. Here it is minus infinity. Here it is plus infinity. Okay. Now all my green not spam ones will be somewhere in the infinity, minus infinity. Okay. And all our positive ones, which are 1, will be somewhere in plus positive, plus positive infinity, at positive infinity. Meaning now this line, this S curve line is somewhat like this. Can I say that or can I not? It is somewhere like this. Why? How did we reach here? How did we reach here? We know this is log of odds. Okay. This is log of odds, this axis. Okay. Now what we are trying to do is we are trying to put the values of probability. Now, if we do a probability, we know that our 0, whatever males that we have as not spam, which is 0, okay, will go to minus infinity. And the ones that we have at 1, which is, spam here, will go to positive infinity. Why? How will they go? What I have done, I've just replaced the values in the formula. Okay. Meaning that we can move this graph. We can move this graph from 0 to 1 to a minus infinity to plus infinity problem using log of odds. We want 0 and 1. This is the outcome that we want between this. But originally it is like this. So these values, so what we have done, we have just expanded our y. We have not done anything to your x. So here there were keywords. Here also there are keywords. More the keywords, it is going to be spam. Less the keywords, the likelihood is that it is not going to be spam. Okay. So we have just expanded this y. We have just expanded the y. We have not expanded your x-axis. Okay. So basically, the question that I was trying to ask, or I was expecting, that logistic regression has a word regression in it, but it is a classification algorithm. Correct? It is a classification algorithm. Then why regression? It is because of this. Okay. So what happens is, since logistic regression has all the essence, all the mathematical fundamentals of linear regression, it is called logistic regression. So nothing but you have the data like this from minus infinity to plus infinity. Okay. There might be different values for these spam and not spam. But since you want this minus infinity to plus infinity, you want to squash the y value between 0 to 1. Squash as in you want to contract this infinite y axis between 0 and 1, because that is meaningful for your problem. Okay. So the all the concepts of fitting the line and everything is very similar, and also the mathematical concepts are very similar to linear regression and logistic regression. That is why it is called, in the name it is logistic regression, but internally what it does, it is a classification algorithm. Okay. The underlying concepts are like linear regression, but the way we want to solve it is with S curve. We cannot solve it with a linear line. But internally, if you look at it, it is a linear line. But we are somehow changing this linear line to an S curve using some function. And that function is called sigmoid. Sigmoid. Sigmoid function. Okay. And it is generally said that now your y cap is nothing but sigmoid of z. Z is nothing but your value or your line equation. This is nothing but sigmoid. In linear regression, what was it? In linear regression, your y cap was w naught plus w1 x1. Let me write it again. So in linear regression, your y cap was what? W naught plus w1 x1 plus w2 x2, and depending on how many variables you have, it was wn xn. Correct? But in logistic regression, This is your equation. And this z is nothing but, it is some combination of linear line only. Some combination of this linear line. Everyone with me. What you're doing, what you're using this sigmoid function is to squash the output between 0 to 1. This function is just doing that. So basically, you're getting some line in logistic regression. Okay, let's compare linear regression and logistic regression. In linear regression, we were fitting a line, we were looking at the errors, and we were finding the best error. That's your best line. Okay, that is what you are doing in linear regression. Now in logistic regression, what you're doing is you're essentially also doing the same concept, but then you are wrapping that everything inside a sigmoid function. Sigmoid function, which helps you to get the output between 0 to 1. Okay. And sigmoid function works on what? Log of odds. How you can do that? You can do that based on log of odds. Okay. Now with an example. So let me take the same example of churn. Churn example. Now imagine you have this. You are trying to predict which customers are going to churn. Okay. And you have this. You have discounts. You have discounts in your x-axis, and you have number of calls that the customer had to make to customer support. To cust support. Okay. So what would you see? The number of people who have lesser discounts and have more problems, meaning they're reaching out to customer support, will be somewhere like this, right? And the people who do not call that much to customer support for their problems and also have high discounts will be somewhere here. Correct? Let me put in some more values, some more data points. This is how in real world you'll get the data, right? This is how you will get the data, right? Your idea is to find a line that separates this. This is your logistic regression. Idea of logistic regression is to club all the people who are going to churn, all the red dots separately and all the yellow ones separately. Is this line not doing that perfectly? This is what logistic regression is, right? It is trying to fit a line that perfectly classifies your examples or your data sets between yes or a no, between red or a yellow. Okay. Will this line tell me, will this line not fit, or will this line not tell you perfectly? Perfect. Now, one very stark and a very powerful explanation that will clear all your concepts in just one example, in this one visualization. Okay. Which is what is the concept of linear regression? What is linear regression going to do here? Linear regression will try to fit a line like this, right? Because over there, the motive is to reduce the error, to fit a line that reduces the error, not separate them. Correct? It wants to fit a line so that it passes through almost all the data points if it can. If it cannot, then the error should be less. Everyone with me? Now you understand the difference between regression and classification also. So logically thinking, people who have really high problems with the platform and who are not given really huge discounts, they are more likely to switch, right? So those are your red dots. And the people which are your yellow crosses or the yellow people, they are the ones who are having least number of problems with the platform. They don't have to reach out to customer care again and again, and they are being given really good discounts, really high discounts, so they'll be happy, right? They will not churn. So here, red one, churn, probability is high, and here, not churn. Let me write it that way, not churn. Okay. The idea of logistic regression is to separate the red and the yellow points completely out. And for the linear regression, the idea is to fit a line so that the errors from all the data set is really less. There is some linear relationship between number of calls to support customer care and discounts. Okay, cool, perfect, guys. So now this out of the way, let us also do some derivation. Let us do some derivation. I will now mathematically prove it. I have proved it visually and geometrically that this is this, and I've also given you an example how it works. We are just solving something really under the layer of logistic regression. We are going into real details that why it is called regression. One, even though it is classification, how does it fit my data? Okay. And what does sigmoid do? Sigmoid is nothing but it is just a wrapper on this line. It is just a function on this line, which will now help me to say whether it is 0 or 1. It will give me probability whether it is between 0 or 1. Okay. That's the only thing. Now with derivation, I am going to prove that. Okay. So now this will not take much time, guys. Log, sorry, odds, we already know that this is this. Now taking log on both the sides. This is first step. This is second step. Taking log on both sides. It's log of odds, log of p over 1 minus p. Okay. Then we go into, now with the example that I showed you that, this, this curve, this S curve can be converted to a problem which is from plus infinity to minus infinity using this, right? Using log of odds. So what I can say is, in other words, if I, instead of this, I put the equation of line here, which is W naught plus W1x is equals to log of P1 minus P. You understood why I put this value, equation of line? Just now we saw it visually, right? Now the other property. This is the third. Okay, this is coming from here. Proved already. And then the fourth line is property. Now this is for all the non-tech people and people who have not looked at exponential. Okay. Property is that whenever you have to get rid of log, you take an exponential. So the property is log of to the base a for log of x. Let me put n here, log of some number, and if its value is some feature, this can also be written as n is equals to a to the power x. I am not doing anything here. It is the property. I'm just putting it here so that you can quickly revise, and all for my non-tech people as well. Okay. So we are going to do the same thing here with this. We are going to do the same thing here. So this will become what? E to the power W naught plus W1x is equals to probability 1 minus probability. Okay. And now fifth step is that now I will just solve this problem. I will take this here. Okay. Chain rule. I will say something like this. Just be with me, guys. It is going to be multiplied by 1 minus p. Okay. And now I'm going to take this e to the power w naught plus w1x inside. It is going to become e to the power w naught plus w1x minus p times e to the power w naught plus w1x1 is equals to p. Now I'm going to take this p here again. Okay. It is going to become e to the power w naught plus w1x is equals to p plus this minus will become plus there plus p times p multiplied by e w naught plus w1 x1. And now if I take common p out of this, seventh step is e to the power w naught plus w1x is equals to p 1 plus. Now anyone who can see where I'm going with this? The last step is if I bring this here, this side, what will it become? It will become e w naught plus w1x over 1 plus e to the power w naught plus w1x is equals to p. Have you seen this equation somewhere? Have you seen this equation somewhere? Since you have not seen it, what you can do is you can divide. This is an optional, step. This is 8, so we'll go into ninth step. Ninth step is you divide both of these with e to the power this term. Okay, so this will become e to the power w naught plus w1 x1 divided by e to the power w naught plus x1. Here in denominator, it will become 1 plus e to the power w naught plus w1 x1. This entire thing divided by e to the power plus x1. In a nutshell, I will not go into the maths. In a nutshell, this will become this and this will cancel out. Okay. This and this will also cancel out, but this will come here. So it will become 1 over 1 plus e to the power minus of w naught plus w1 x1. And if you say w naught plus w1 x1 is equals to y cap, this is nothing but 1 over 1 plus e to the power minus y cap. What is this? This is sigmoid. Didn't we talk about this? This is the equation of sigmoid. Okay. This derivation, no one is going to ask you. Okay. No one is going to ask you, but I wanted to show this to clarify that mathematically this is possible. This, can I not say that this is nothing but some verification, some function of your sigmoid, which is given on y cap. Okay. So sigmoid will give you the probability. What did we have here? We had probability here, right? So it will give you the probability here when you're trying to look at all the values. It will convert this linear line to a value where it can be looked at as a probability. that how much probability it is to go to spam, how much probability it is to go to not spam. No one is going to ask you this derivation, but it is very important to know, at least from the understanding, that how did people go from this S curve, or started with linear line, go to an S curve. Okay, perfect. All right, guys. So I think we have covered this. Now let me see what I wanted to. Okay, we have already talked about the balanced data and the imbalanced data. Imbalanced data. Okay, we have already looked at the fraud problem. Out of 100 applications, 95 of them are genuine and 5% of them are fraud. Now, if you are a very smart person, okay, why you will think that I'm getting all the applications. If I make a model, or if I tell that whatever application you're getting, just predict that it is what? Genuine. If you just make this, if you train your model just to don't pass anything, just constantly say that it is genuine, whatever loan, the application that you're getting is genuine, then how accurate will your model be? You have 100 emails, out of which 95 of them are genuine, 5 of them are fraud. So this I will say not fraud, this I will say fraud. And if your prediction is, your y cap is 100 of them are 100 of them are not fraud, for all of it you will say that this is your prediction. What is the accuracy? Accuracy is 95%. This is called dumb model. Anyone can make this dumb model. No brain. But is this 95% right? Even though it looks like 95%, it looks like a really huge number. Is it doing what we need to do? If tell me bank processes the loan for these 5 people, you know how many people have gone out of India, right? They have fraud. They are frauds. How much money can they take away with them? All these 5 frauds or 4 frauds or whatever these people are. If you end up giving loan to them, they will never repay. They will run away with bank's money and it is lost to the bank, right? Even though your model is 95% accurate. Is your mind blown? And you are simply saying you have created a very stupid model, that whatever application you are giving to me, just say, yeah, process the loan for this guy. It is always saying not fraud and process the loan. That's not right. So the important thing for here, what is important here? The important thing is that we do not process loan for even a single fraud person or a fraud application. That's how that is what the banks want, right? That is the ultimate goal of the bank. So here with this example, you know that accuracy is not the right measure for classification. for classification problems. Or let me put this this is going to, something that people generally ask in their interviews, that why accuracy is not used. Looking at alone accuracy is not the right measure for classification problems. Everyone with me? Even a dumb model can tell you that, with 95% accuracy, you're not building any model there. You just put one line that whatever in the code, your code will look like this. Just say or predict there's a constant value there which says not fraud. Still, it is having 95% of accuracy. This is why data scientists, machine learning engineers, AI engineers like you are paid really high, because anyone can make that 95% accurate model. But you are the one who need to go in detail and see that what is the ultimate goal of the problem. The goal is, I shouldn't, okay, I can process for all 95 of them, but more important for me is I shouldn't be processing the loan for these 5 people, especially. Okay, I can reject 7 of them. I can reject 7 of them, but out of all these 100, two could be people who were genuine, but I still ended up predicting fraud for them. But I need to make sure all of these, my 7 applications that I'm rejecting, they should be at least closer to fraud. They should have all these 5 loan applications, which are absolutely fraud. There is some collateral damage by rejecting loan for another 2 people or 3 people, which might or are at a risk of fraud based on the probability. Okay. So that is why accuracy is not the alone looking at accuracy is not the right measure for your classification problems. Okay. Especially in imbalanced data set, even in balanced data set, never look at accuracy alone. In classification, we have something called as confusion matrix. Confusion matrix. Okay. We have something called as confusion matrix. Why the name? Because it confuses a lot of people. It confuses a lot of people. That's why the name is confusion matrix. So you need to be extra careful when you're doing classification. Okay. So we know that the outputs can be only 0 and a 1, right? The outputs can only be 0 and a 1. So what will you have? You will have this. Okay. You will have this. So here imagine, okay. So imagine this is your Y cap, meaning predicted. Okay. And here is your Y, meaning actuals. Okay. Now you could be predicting, I'm going back again to the spam and not spam because it is easy to understand that. And we've been talking about that example really well. So this is not spam. Okay. You have predicted it is not spam. All the values on the columns are your predicted, and you have predicted it is a spam. Let me do it this way. And the actuals are, it is actually a spam mail. Okay. It is actually a spam mail, not spam. Let me put that in green. And in actual, it is not a spam. These are the 4 instances that can happen that you have predicted. What does this block say? This is 1, 2, 3, what else? 4. Okay. What does 1 tell us? 1 tells us 1 is y cap is, let me put this as 0, 0. Okay. Prediction is not spam. We already know. I'm not marking it here. Okay. Not spam is 0, spam is 1. So here it is 0. Your y predicted is 0. And y cap is, your y actual is also 0. So this is what? This is correct, right? You have correctly predicted that it is not spam, and in reality also, in actual also, it is not spam. I'm talking about this one. Okay. Let's go to the second number in this box. What is this? This is, you have predicted it is a spam, meaning y cap is equals to 1. And what is your y actual? Y actual is 0. This is wrong, right? This is wrong, right? You have predicted that it is a spam, but in reality, it is not a spam. This is the reality here. It says that it is not spam, but you are saying that it is spam. Okay. Now let's look at the third one. Third one is, what have you predicted? Prediction is not spam. In reality, what it is? In reality, it is spam 1. Y is equals to 1. Y cap represents, or this hat or a cap, okay, represents your predictions. So you have predicted 0, which is not spam, okay, and in reality it is spam. So this is also wrong, right? This is also wrong. You have missed. And the last one, which is the fourth one, 4 here, you have predicted it to be a spam, meaning you have predicted it to be 1. And in reality, it is 1. So y is equals to 1. So this is correct. So these two are wrong, but these are right. Correct? So you need to get the maximum value here. 1 and 4 should be high because they are correct. But 2 and 3, the numbers 2 and 3 here should be low as much as possible because they are your errors. Correct? I am just uncomplicating or unconfusing this confusion matrix with you. So just go with me step by step. Okay? Because if you come back the next week or even the next day, you will get confused which one is true positive, which one is true negative. What is that? What is not that? So I'm just, everyone in the industry confuses on this a lot. That is why the name is confusion matrix. Okay. So just stay with me. I am making it unconfusion matrix for you. Okay. Now, if you look at it, logically, let me copy this to save time. Okay. So the idea is, if I remove this, the idea is all of these, they have two values. They have two values here. I want 100% attendance here. If you look at this, okay, if see, understand what I'm trying to explain, you will never forget in your life what is confusion matrix. And trust me, guys, this confusion matrix is really important and is one of the best pet questions of your interviewers. Everyone asks this. Everyone, in one way or the other, everyone asks this question. Okay. Now you have to fill these two blanks here. What are these two blanks? Okay. One tells you what you have predicted. Okay. The other tells you whether you are right or wrong. you are true or a false. Okay. So here, let's say not spam is what is negative, right? Let's say this is negative and spam is positive because we are trying to get which is spam. So for us, it is a 1. So it is going to be positive for us. Okay. It is going to be positive for us. Now, what you have to tell me is you have to tell me what value will come here. We'll first fill the second blank. This is spam. What have you predicted? This is negative, right? You have predicted negative. And this is not spam. And in reality also, this is not spam. So is this true or a false? T, right? So we are doing true here. What should I fill here in this second blank? What is your prediction? Spam. Spam is positive or a negative? It's a positive. And you have predicted it is spam. But in reality, it is not spam. So this is true or false? F, right? Here again, here, what should I put here? You have predicted what? Positive or a negative? You have predicted what? Positive. And this is, you have predicted spam. It is also spam. This is true. And what will this come? This is, you have predicted negative. You have predicted not spam and it is spam. So this is what? False. Congratulations, guys. You have completed logically. You have completed or filled confusion matrix. And trust me, I'm coming from the industry. I take interviews and the amount of people who get confused between TN, FP, FN, TP, where it should be, where it should not be. The amount of people who fail into this and are not able to answer this are startling very high. This is such a basic, but this is where you create the impression. If you're not able to answer this, interviewer will be like, it doesn't know anything. This is just basic. Okay. So now these are called your type 1 errors. Type 1 errors. And these ones are your type 2 errors. And trust me, guys, even I get confused. Even I get confused. Okay. So this is the way that you can, instead of memorizing, logically you can understand. We'll talk about what are these two errors, type 1 and type 2. But now, can you tell me what is your ideal model? Ideal model based on the spam example only that I gave you, fraud example. Fraud example of 100 fraud or 100 applications. So, based on this, what we have studied, okay, can we say that these two numbers have to be the maximum? Okay, this has to be not spam, this is not spam, and this is spam, this is spam, this is your Y cap, this is your actuals. Okay, so these two numbers have to be really high. So in ideal world, the ideal model, you had 95 of them which were not spam or not fraud. Let me in fact change this to fraud problem. This is fraud. Okay. And this is not fraud. How many of them were not fraud? 95, right? In reality also it is 95, and you would want to, your perfect model will also want to predict all 95 of them as not spam. So this will become 95, correct? And 5 of them were fraud. In reality, your perfect model or ideal model would want to predict all 5 of them correctly, and you would want to make these type 1 and type 2 errors zero, correct? This will give you what? 100% accuracy because your errors are zero. This is the perfect model. The example of the fraud, what did we do? We say that we have 100 loan applications, okay? And out of them, we know 95 of them are not fraud. We know, okay, they are not fraud, and 5 of them are fraud. We know this. So your job as a person who is working as a top level data scientist with some bank, let's say JP Morgan Chase or HDFC or Citibank, Axis, anyone, Mashreq Bank from Dubai and all, even in Swiss Bank, imagine, even Swiss banks, you are given the responsibility to make a model that is perfect. How will you make it? Your goal is that you should be able to predict all 95 of them correctly. You should make them as you should predict that they are not fraud for all 95 of them, and you should also be able to predict that these 5 are only the fraud. That is, your perfect model will have zero errors, because we have already seen that this false positive and false negative are type 1 and type 2 errors. There are some sort of errors. What type of errors? We'll get into it. So your idea is that these two values should be 0 and these two values should be absolutely correct. So your model should predict it is not fraud. And in reality, we know 95 of them are fraud, not fraud. In reality, in actual, we know 95 of the applications are not fraud. Your model should also say 95 not fraud for these 95 applications. So I'm putting a 95 here. Okay. Your prediction of fraud should be exactly the same where these are fraud. In reality, if it is a fraud, your model should also say it is a fraud. Okay. All right. So now what we have seen is we have seen the confusion matrix. We know how to fill the confusion matrix. We know what type 1 errors and type 2 errors are. It is nothing but some sort of incorrect, right? So they have a false in front of it. False positive is your type 1 errors. False negatives is your type 2 errors. And then we also looked at what is the ideal model, So this one would have 100% accuracy. Okay, 100% correct. Let me put it as accuracy also. And here the accuracy is also good. Why? Because your type 1 and type 2 errors are 0. Okay, so we are not looking at only accuracy alone. We are looking at the errors also. Okay, now formally what happens is there is something called as precision. Okay, so there is something called as precision. Okay, let me talk with an example. There are two cases in your spam and not spam. One is you receive a spam mail in your mailbox, in your inbox, meaning it wasn't classified as in spam, but it is a spam. And what is the other thing? The other thing could be that you that I hope this doesn't happen, but imagine if this would happen, how bad it would be. Your offer letter that came through an mail goes to spam. Tell me now, guys, which one is more dangerous here? This thing is harmless, right? This thing is harmless. You are receiving a spam mail in your inbox. It is there in your inbox, but action is not yet taken by you, right? But you interviewed somewhere and you got the job. The offer letter did not reach in your inbox ever. It was wrongly classified as a spam mail. So that is more dangerous to you, right? You know, you're thinking that you are not placed, you did not receive any feedback, any offer letter from the company, but in fact you have already been shortlisted and given the offer letter. So this is dangerous, right? So this is dangerous. This is more dangerous. Now let's think about this. What is this? This is a false positive or a false negative? What is the first one? We are just making our understanding even more concrete with these examples. Okay. First is false positive. FP. Correct. So remember we spoke about two fill in the blanks that we have to do whenever we are doing such things. So what did we predict? It is an actual spam, but what did have you predicted? You have predicted not spam. You have predicted not spam. That is negative, right? You have predicted negative. And it is a spam mail, but it came in your inbox. That is false, right? Your prediction of negative is false. So this will be false negative. And this one, what is it? What have you predicted it to be? You have predicted it to be a spam, which is 1, 0 or 1. 1 is positive in our case. And that is also wrong, right? So all those who said it's false positive, do you understand why it is false negative and why the second one is false positive? So the first one is that you received a spam mail in your inbox. Okay. Imagine that you have a model which is responsible to pushing those emails which are not spam in your inbox, and the ones which are in spam, which are spam according to the model, should go to the spam folder. But this one came to your inbox folder, meaning what has your model predicted? Your model has predicted it is not spam, meaning it predicted negative. Out of these two fill in the blanks, it predicted a negative clause for it, meaning it is not a spam. And that decision is false because it is actually a spam mail. So it is false negative. The other one, second example, is that your offer letter has gone to the spam folder. Rather than coming to your inbox, that would have been the right thing. It has gone to your spam folder. So meaning your model has predicted that it is spam. So you have predicted what? Positive class for it, spam. Okay. And that is false. That is incorrect. So it is false positive. And in this case, false positive is dangerous. Meaning here the idea is that false positive should be minimized. Correct? Correct or no? And true positive should be improved. In this, if you look at this, this value should be minimized and this value should be maximized. That is your precision. So precision formula is TP over TP plus FP. How precise are your predictions? How precise are your predictions? On the positive side, how many are you able to correctly say they are positive out of all the ones that you have predicted as to be positive? Okay. How precise is your output, your predictions? Then second is recall. Now for recall, I have another example. I have noted it down. Okay. So now you have to tell me this. You have again two cases. The idea is that you have to predict whether a person who is having cancer, you have to detect whether it is cancer or it is not a cancer. Okay. You have to, your model has to tell whether, looking at the condition of the patient or looking at the graph, your images of probably chest x-ray or something like that, you have to say whether it is the person is having cancer or he or she is not having cancer. Okay, cool. So there could be two cases. A healthy person is considered as cancerous. We are talking about only the errors. Okay, there are others as well, but I want it to be very clear for you, which is this type 1 versus type 2 errors. Let me put it down here. Type 1 versus type 2. Okay, this is one situation. The other situation is what? A person is cancerous, but you are saying that he is healthy. A cancerous person is considered healthy. Now, first tell me, which one is more dangerous? Two, right? A person who is healthy will be starting taking the medications, correct? There will be some side effects of the medications, but it is not life threatening. And in subsequent tests, it might there might be a possibility that it is detected that this person has become healthy. So they would claim that the medicines have worked, but initially it was like, the person was healthy itself. Imagine it, or relate this with your COVID also. A healthy person was considered to be COVID positive or a COVID patient. That is more dangerous, or a COVID patient, in the test it comes out that he's healthy, he or she is healthy. Okay, related that way also. So more dangerous is this one. Now tell me, what is this and what is this? Which one is false positive and which one is false negative? What is the first one? Let's look at it. What have you considered? What have you predicted? You have predicted that a person is cancerous, meaning 1. Cancerous is 1, non-cancerous is 0. When your motive is to find which one is cancerous. Earlier, in the earlier example, which one is spam? So what have you predicted? You have predicted a positive for this. You have predicted that the person is cancerous, which is false because obviously the person is healthy. Now, can you tell me what is the second one? Second one is false negative, meaning you have predicted it to be a healthy, non-cancerous person, meaning you have predicted negative for it. And that is false because in reality, the person is having cancer. So it is false negative. So here we saw false positive was dangerous. Here we see false negative is dangerous. So depending on condition to condition, things change. Okay. Depending on your data, depending on what is your motive, and depending on what is more dangerous to have, which type of error is kind of acceptable, not kind of acceptable, but is less dangerous to the other one. So here the motive is that you need to reduce F negative, correct? Here you need to reduce the F negative in this one. Okay. You need to say that it is less negative. So the formula of recall is PP over TP plus Fn. Okay. Here the motive is that we should improve our true positives, meaning the ones which are cancerous, we need to improve their prediction. We should also predict cancerous patients. Okay. You're recalling out of all the ones which are positive, you should be able to tell the ones which are positive correctly. And you should have less people who are false negative. Okay. True and false is based on whether it is right or wrong. So here, this one, these are the two blanks that you have to fill, right? Let me close this. In this confusion matrix, it is two blanks. First one is what you have predicted. Okay, positive is the case when what is your goal. So if you want to identify spam ones, that is positive. If you want to identify cancer patients, that is your positive. Okay. And the second is whether what you have predicted is right or wrong based on actual. We looked at these, right? We looked at these 1, 2, 3, 4. All the ones that are correct are having your true there in the first blank. All the ones which are wrong, predicted versus actuals, they are false. Okay. It's not easy to understand this concept, but trust me, if you are able to revise this, I guarantee you'll never forget. The way I have explained it here, it is very logical, and also with examples, you will never forget it, given you understand this. Otherwise, the other option is you can simply go and memorize that, what is TP, what is FP, what is TN, FN, all those things. Okay. I would recommend you think it logically, and as and when you keep doing this, no, it will become second nature to you. You'll do this like this. Don't have to think twice. Okay. So this is your metrics that we call. So we have looked at now what is accuracy. Let us also look at accuracy. What is accuracy? Accuracy is the ones which are true over total, right? So accuracy based on your confusion matrix can be PP plus TN, the ones which are true over total observations, and total observations are TP plus FP, TN plus FN. Okay. Accuracy is nothing but all the ones that you're correct with over total number of observations. You're correct on 1 and 3 or 1 and 4, depending on whatever you're doing. These two boxes. You are correct only here and here. Let me take it from here. 1 and 4 is where you're correct out of total. Okay. So that is your accuracy. And there is this one thing called, which is F1 score. F1 score. This is nothing but a combination, because now I told you that somewhere you would prefer to have a higher precision, somewhere you would prefer to have a higher recall. Depending, so in the cancer problem, you want to have a better recall, but in your spam and not spam, you want to have a better, you want to have a better precision. So F1 score combines both your PR precision and recall. Okay. And how it is related is your F1 score is nothing but twice the precision over precision plus recall. Okay. Which in other words, what was your precision? Your precision was plus TP plus FP. Okay. And what was your recall? Okay. Let's leave the maths. There's enough, I feel. It is nothing but it is twice of TP over twice of TP plus FP plus FN. This is your F1 score. You can either use this one, the bottom one, or the above one is one and the same thing. Okay. If you solve this, no, if you put the values of recall and precision here, you will get this only. It's one and the same thing. Perfect. Awesome, guys. Is everything clear now? Logically, everything should be clear now. Okay. Why we need to look at accuracy in regression? Why we cannot look at only accuracy in classification? Okay. We looked at all the examples. Let's move on to the hands-on part. Okay. Cool. All right. Now let's go on to your hands-on. Okay. So here I have this data which I have already uploaded. It is the heart attack data. Okay. So we've been looking at this all along. So let me go ahead and first, do all these. Okay. So let me first import everything. Import what? Pandas as PD. Okay. I will also import Seaborn because I want to show one thing in Seaborn also. I hope you have covered that. And then there were some others also that we were looking at in linear regression. Idea is same, guys. Idea is same. This is as, okay, get the data, understand the data, okay, then separate your target and train variables, target as well as your test as your train, okay, do the split, get your independent features and your dependent feature separately or your target feature separately, then do the split. After you do the split, train it. After you train it, predict it. After you predict it, evaluate it, whether it is correct or wrong. So here I am importing. Okay. Then let me go ahead and at least for a few lectures, I will not add all these things that I want in one go in the first cell like I like to do it. But here, what did we do? What do we have to do? We have to read in your data frame, which is, let me say this as CSV. What is the name? Part1.csv. Okay, and then we will also do a head of it. Oh, okay. So this is our data. Okay. Now, what is the data set? What have I told you? That once you get the data set, try to understand whatever you want to understand of the data set, so that at least from making the model side, it is not important. But when that's the difference between a great data scientist or a principal data scientist, a great machine learning engineer, AI engineer, data engineer, all those things. That's the difference between the one who is great and the one who is just getting the job done. Okay, get the data, try to understand, even if it is not in your comfort zone. Now, this data set is basically the data set of the people who get heart attack. Okay, now this is your target variable. It has already been given. Okay, I'll explain a few of these. Okay, because most of it is from the biology side based on the test, but this is the age of the patient. Okay, this is the sex, male or a female. CP here tells whether it is chest pain, and it is of four types: 0, 1, 2, 3. I know I've looked at the data, so I'm telling you it is four types. So it is basically whenever you get a heart attack, you more less or likely it is that you will get a pain in your chest first. Some pains are angina related pains, atypical angina, typical angina. If you go into these terms, you'll get to know about it. But for our understanding, these are different types of chest pains. Some are related to heart attack, some are not. Some could be, for example, could be due to gas, some could be due to something X factor, some other reason apart from heart. Okay, imagine it that way. Then this T rest BPS is nothing but your resting blood pressure. Call is cholesterol. This is fasting sugar, blood sugar. Okay. This is another ECG test is done in the heart, resting how it is looking like. These are some other tests. Okay. Old peak is when it is peaking. Slope and all these are all technical terms from the medicine side, but at least the ones that you're able to understand, you'll be able to get to know that okay, these are some of the conditions that are noticed in the patient, what are and some of the values of the tests that we are seeing here. And the target variable is 1 when it is a heart attack, 0 when it is not a heart attack. Okay, now let us look at and describe the data. What are we going to do? We are going to Okay, let me first do this. It has 303 rows and 13 columns. Okay, so patient is 303. We have the data for 303 patients. Now we are going to do df dot describe. We will also do info. Okay. And then, okay. So what does the describe tells me? It tells me all the ones which are 303, the count looks like all of them are having right values. Okay. And then the mean age, on an average, the patient age that we are getting is 54, which is likely, right? People as in when they get older, the risk of getting them a heart attack is more compared to someone who's young, correct? So this connects with you. Then there is some ratio that we're seeing. The mean average is this. We cannot make anything about this because this is 0 and 1. Okay, categorical feature. The only thing that we can understand from this is close to 25% of the people are 0. Okay, meaning if it is a female, it is 0. If it is male, it is 1. Okay, so more than 50% of the data is from males. Then chest pain, what is the, again, categorical value here? So we are seeing 25 percentile, 50, 75 is 0, 1, 2. Okay, it is very equally distributed. Then BP readings. Okay, so here on an average, the BP reading is 130, which is kind of in the normal range, right? And Some people have an extraordinary high BP. It's really high. 130, 120 is considered to be normal. Cholesterol value. See, the person who is having this high cholesterol. Cholesterol is nothing but as in when you keep on eating oil, it or fat, the wrong fat, it accumulates in your body. Okay, it obstructs the blood to flow from your veins, arteries, and veins. Okay, that could lead to heart attack. So a general normal value is below 200, but we are seeing all the patients, at least 25% of them or more, are having value 211. So high cholesterol is related to heart attack. Even without looking at anything, even without predicting anything, we have, it looks like high cholesterol above normal value is related to heart attack. Okay, and similarly you can look at the others. Cool. Now info, we are saying that okay, all are non-null and I'm getting one float value and I'm getting 12 integer values. Okay, and the data set is pretty small since it is this thing, only 300 rows. Okay, so let's go ahead. What can we do next? So I can show you the value counts, meaning how many uh, how many of them are zero and how many of them are one in my target column. In my target column, out of the 303 people, I have 165 of them have a heart attack and 138 of them are not having heart attack. Zero is not having heart attack. Okay. So people also like to visualize it. So let me do a count plot using Seaborn. X is nothing but my target variable. And the name of my target variable is this. My data is df and my palette would be, palette is nothing but a color scheme. Okay, that you want to choose. So there are many color schemes that you can choose. I'm sticking to the one that I have been using a lot. Okay, so what error are we seeing? Palette spelling. What is the spelling of the palette? Palette. Huh. What are we seeing here? Let me just check what is going wrong here. Data is equals to df only. The spelling is wrong here. Okay. So now you see, let me minimize this. Now you see you have plotted around 138 of them are zero and close to 168 of them that we have seen this number, 165 of them are one. Okay. So we have just plotted a simple plot here. Okay. Now what is the next step? What is the next step? Next step is to create your data frame or creating your um, X and Y separately. Okay. So how are we going to do that? Everyone understands this iLock, right? We have covered this. So all the features, all the columns except the last one is your independent feature and only the last one is your target variable. Correct? So let's try to see x dot head. Let me not take much space here. So you have all the columns except the last one. And in your Y, you have only one column, which is your target. Okay. Once you have done this, what did we do in linear regression then? We did splitting of the data. Okay. Now, how did we split the data? From sklearn dot models dot model selection import. What did we import there? Train, test, split. Okay. And then what did we end up doing? We end up creating my x train, x test. Second value is that. Then the third value is y train. Then we have y test. And what do? We call this function, which is your train test split. And what all values does it take? It takes your x, it takes your y, and it takes your test size. I am going to keep it again as 20%. And the last thing that we looked at, random state, I'm going to say 1. Any number, if you want to repeat it, any number. Okay, let me run this. Now, once you have this, let us look at sx train dot shape. It is 242 and x test dot shape. You know what? Let me print this neatly. Give me a second, guys. X train shape is equals to this. These are f strings, right? I hope you know. We also looked at it last time. And I want to say y train. Here I will change it to y. Just for creating some separateness so that it is easy to understand within this class. I'm just printing this. So this will be my test. This will be my test. 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 Okay, let's run this. Okay, so 303, 20% goes to test. So 30 and 30 is close to 61, 30.3 and 30.3 close to 61 goes to my test, and the remaining goes to my train. And I have chosen it to be 80-20 because my data set is pretty small here. Okay, it's only 300 patients data. Cool. Now, what do we do next? What do we do next? In linear regression, what did we do? Create the model. Absolutely. Model fitting. So next we will do what? We will fit the model or build the model. Okay. Now over there, what did we do? Over there, we imported from sklearn dot, what was it? Linear. It was linear models, right? Linear model. We imported there what? Linear regression. What are we doing here? We are doing logistic regression. So we will import logistic regression. Okay, cool. Now what are we going to do? Over there we created a model, which is model. Now I'm just to make it separate, I am creating a instance of that class, which is your logistic regression. Okay, so I am creating this instance of the class in log model so that you are able to understand it is a log model. So log model, and what will my log model do? Okay, let me first show this. Let me run this. Now here earlier we were getting linear regression. Now we are getting logistic regression, right? So log model dot fit is what we have to do. And we have to do fit on what? We have to do fit on train period. Correct? Perfect. So we will do fitting here. Then this is nothing but warnings. Okay. Data conversion warning and everything. Now, what is the next step? Predicting with the model. And everything that you have learned, all the patterns, all the relationships that you have learned, which is log model. So using log model, what are you going to do? You are going to predict. And you are going to predict on what? You are going to predict on X test. And you will save all your predictions in Ypred. So now you have your predictions, you have your test. Let me show you. This is your prediction. Okay. Let me print a few values. Let me also print a few values from your actual data set, your test. It's nothing but 0, 1, 0, 0, 0. Here you are saying 0, 1. Is there some change? No. Looks like your predict. Ah, no. Is there? No. Here it is 1. Last, third, and second last are 0, 0. Here you are predicting this to be 1. Okay. But in reality, it is 0. So you see one error there. Okay. Now we know what we have. What we have the predictions, and we also have the actual values. Okay. We need another 5 minutes and logistic regression is done. So now what did we study? After we predict the model, we have to evaluate the model, whether the performance is right or wrong. So in linear regression, we looked at the evaluation should be done using RMSE, MSE, R square, okay, mean absolute errors. But here, what have we studied? We have studied confusion matrix, correct? So we will import what? Confusion matrix. So from sklearn dot, let me do that here. sklearn dot metrics import. From what are we going to import? What is the name? Confusion matrix. Okay. Python is very intuitive. And now to show you something, but okay, let me show that later. Let me first complete this. We're already 2 minutes up. So here, let me print this and let me call this as confusion matrix equals to. What do we do? First value is what? Actuals, right? First value is actuals. And then second value is your predicted. Then we will print confusion matrix. This is your confusion matrix. Okay. Let me copy paste this. This is nothing but that thing that we were talking about. This is your what? TP, TN. This is what? FN, FP. So you're getting those values here. Okay. Now, another way that I generally try to use is this. Okay. I try to use confusion matrix display. It takes in the confusion matrix itself so that it can print it properly. Okay. Let me put this, and then it has what? Display labels. What is the, let me show you what I'm looking at. Whenever I am stuck, I look at sklearn confusion matrix with labels, and this is the first one that I'm opening. And I go to the documentation, and there is more likely or no, there is an example. So let me copy this. Okay. Your predictions label is equal to CLF classes. I'm putting that here. I wanted to show you this. But ultimately what it does is it shows you this. I don't want to take up much time. The same thing that you're seeing there, it shows it in a pictorial manner. Okay. So that it is intuitive to understand. Okay. Let me delete this and there is another thing that you can do, which is metrics, which is your classification report. This classification report, and then it does what? It is nothing but is the same thing. Just printing it. Classification report. And you're passing in the same thing there. First value is actuals, then second value is predicted. And you get all the things: precision, recall, F1, support is another thing, but accuracy, weighted average, macro average. This is what you're getting, right? All the things that we looked at today are everything here. Okay. So this is your logistic regression. Okay.
Just a quick info, guys. Intellipaat offers an executive postgraduate certification in AI and machine learning in collaboration with iHub, IIT Roorkee, and Microsoft. This comprehensive course is designed to make you an expert in AI and ML in just 11 months by working on over 50 real-time projects and industry case studies. With this course, we have already helped thousands of professional and successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to a new height. So visit the course page link given below in the description and take a first step towards career growth in the field of AI and ML.
Standardization versus normalization. What exactly are these techniques and why do they exist? I believe this is something all of us first need to introspect on if we were to build a good understanding of the concept. Well, to do this, let me just take an example of one sample dataset. In the graph visible on the left side, you can see that there are 13 data points and 9 of them converge towards close proximity, whereas 4 of them lie far away, right? A basic deduction all of us can make is the values that are lying far away have huge magnitude and they can have a large amount of say in the learning process, producing miscued results. Now, if I directly go ahead and perform the training without nudging the data, what do you think would happen? Well, the chances are we will have very less prediction accuracy, right? Especially in distance-based learning algorithms like the KNN, which relies on calculating the Euclidean distance between data points. That is why even in mathematics, ideas like scaling exist. In this video, we are going to break down two critical scaling techniques known as standardization and normalization. We just mentioned one use case of scaling when there are outliers in the data. Now imagine this. You've got a data set with 3 features: age, salary, and number of children. Simple enough, right? Now, age and number of children usually fall within pretty small ranges. Age might be anywhere from 0 to 80, and number of children is likely between 0 and 5. But salary? Oh man, salary can go all over the place. It could range from 0 to millions or even billions. Here's the catch. Because salary has such a huge range compared to age and number of children, it can totally dominate the prediction calculations. And when that happens, your model accuracy can take a drop. So what do we do about it? Here's where feature scaling comes in the picture. It's a way to ensure that no single feature can overshadow the others. Let's break it down, starting with normalization, which is also known as min-max scaling. This method transforms your data to fit within a range of 0 to 1. Imagine lining up all your data points. The smallest one will be at 0, the largest one at 1, and everything else will fall somewhere in between. So let's see how it works. You take a data point, let's call it x. Subtract the minimum value of your dataset and then divide by the range, which is basically the difference between the maximum value and the minimum value. And voila, you've got your normalized value. This is super handy when your dataset doesn't have any outliers. It makes everything nice and neat. ready for your machine learning models to work on. So the next technique we're diving into is standardization, or you may also hear it as Z-score normalization. This technique is highly useful when you're working with datasets that have a normal or Gaussian distribution. So what does standardization do? Well, it rescales our data around a mean of 0 and a standard deviation of 1. It's like giving your data a fresh start, centering it around 0. Pretty neat, right? Now let's get into the nitty-gritty of how you actually standardize your data. Don't worry, it's simpler than it sounds. Here's the formula you'll be using. First, you'll need to calculate the mean and the standard deviation for your variable. Once you have those, for each value in your dataset, you subtract the mean and then divide by the standard deviation. And voila, you've got your standardized value. See, not so bad. By leveling up the competition in your data, this strategy makes it much easier to compare and analyze. Before proceeding with the hands-on, let us have a quick summary about the differences between standardization and normalization. First up, let's talk about standardization. This method rescales your data so that it has a mean of 0 and a standard deviation of 1. On the other hand, normalization is all about squeezing your data into a range between 0 and 1. Think of it like stretching a rubber band until it fits perfectly between 2 points. Now, when should you use each one? Standardization is preferred when your dataset has outliers. Normalization, however, can be your best friend when the scale of your data varies significantly. Just like in our previous example of ages, salaries, and the number of children, all on different scales. Normalization helps bring everything into a neat, comparable range. And here's the best part. All this can be done in just 2 lines of code with the help of the scikit-learn library's handy transformers, standard scaler for standardization and min-max scaler for normalization. These tools save you a ton of time and effort. Now let's go ahead and perform a quick hands-on. So as you can see, this is my Jupyter notebook. I have already written down the code for you guys and we'll go through it line by line. I've imported the libraries in the first cell, as you can see, mainly the pandas, scikit-learn and the stats model. I'm using housing dataset which I've loaded in the df variable. I have performed the basic exploratory data analysis, which is not very important for this video, so I will not go into detail. To understand the importance of normalization, we first need to observe that one of our features, which is area, varies significantly in magnitude and will definitely dominate the learnings of our dataset. So I'll just go ahead and perform the linear regression, and stats model provides us with a great feature called summary, which will help us understand our model better. So as you can see here, we have a good R-square value, which is basically a statistical measure of how well the regression line approximates the actual data. But that is not what we are interested in. We are interested in the p-value. To understand why, we will first look at the coefficients. The coefficients describe the relationship or the correlation between each independent variable and the dependent variable. The p-values for these coefficients in return indicate whether these relationships are statistically significant or not. Ideally, our p-value should be lower than 0.05 to show significance for the coefficients. But as you can see, the p-value is greater than 0.05 for the bedrooms feature, indicating a poor relationship of bedrooms with feature price. But is that the case? Let's check it out by performing normalization on the dataset before performing linear regression. So here I have initialized the scaler and trained the data using fit transform. The fit transform method will determine the parameters and basically transform the dataset. Now if I perform linear regression and look at the summary the similar way, we can see that R-square is pretty much the same, but the p-value for bedrooms has dropped to 0, which is what we wanted ideally. So I hope normalization is clear with this demonstration. Now I'll move on to standardization. I have generated a dataset having normal distribution. Again, I won't go into detail about the code. As you can see, the dataset contains outliers as well. Hence, standardization will be the ideal approach. This is how we initialize the scalar object and then fit and transform the data. As a result, you can see this is what the standardized array will look like. So far, we've explored linear regression, logistic regression. Now let's dive into another powerful algorithm, decision trees. So let's break it down with a simple example. Let's say there's a restaurant owner and he wants to predict whether a customer will order dessert or not. He has collected some data based on the past orders. Now your goal is to build a model that can predict whether a new customer will order dessert based on their age and whether they ordered a main course. Now your first instinct would be to use logistic regression because it's used for classification problems like predicting yes or no. But here's why it's not the best fit for this case. Logistic regression works well when the data is perfectly separable. That is, logistic regression relies on a linear decision boundary and feature space. But in our case, the data is not perfectly separable. Look at customer B and D. They both ordered a main course, but one had dessert and the other did not. This suggests that the decision might depend on a more complex interaction between age and the ordering behavior, something that logistic regression is likely to struggle with. A decision tree, on the other hand, works by splitting the data into smaller and smaller groups based on certain conditions, just like how we make decisions in real life. For example, let's say we first check whether the customer ordered a main course. If yes, then we check their age. If the age is below 30, they are more likely to order dessert. If the age is above 30, they are less likely to order dessert. This forms a tree-like structure where each decision leads to a new branch, eventually leading to a prediction. But how does a decision tree decide where to split? The algorithm tries to find the best question at each step to separate the data into the most pure groups possible. It uses a mathematical concept called information gain or Gini impurity to determine the best splits. The idea is simple. The cleaner the split, meaning all items in a group belong to the same category, the better the decision. But real world data is often messy and complex, and sometimes a decision tree can become too complicated by making too many splits. This is called overfitting, meaning the tree learns the training data too well but struggles with new data. To avoid this, we prune or cut down unnecessary branches, keeping the tree simple and effective. I hope this explanation made things clear. Now let's move ahead with an even deeper understanding of decision trees with one of India's top data science traders. So let's get started.
What a decision tree looks like. Like, for example, I had a node at the top, and then there was two lines. One was a yes, and the other was a no. And then I had a node again, and then I had a node again here, right? And then I had another output, and then I had another output. So see what happens is, yes, in a decision tree, the most important part is this part, and this part, and this part. They are called as nodes, okay? If you actually visualize it in a normal sense, the way trees are written, you will find them like this, okay? You will be finding them like this. So you see, the circular things are called nodes, okay? This is what you call as nodes. Now you see at the end of the list, or sorry, at the end of this particular tree, you're left with certain small options which have no branch. They are just the end, right? They are leaves. Okay, they're called leaf nodes. So I will just show you guys a little simplistic understanding of how a decision tree is sort of looks like. Okay, give me 1 second. I'll just take you guys through some complex understanding of decision trees, and then maybe we'll sort of proceed forward. Hold on, give me 1 second. That is correct. Okay, so now see, the thing is, you will have things like a root node, a leaf node, splitting, a branch or a subtree, or pruning. Now a branch or a subtree is, let's address it one by one. Okay, let's talk about it one by one. Give me 1 second. Decision tree. Okay, let's visualize it one by one. Give me 1 second. Yeah, let's take this. Yeah, see, now listen to me very carefully. This is a very important concept, super critical for your understanding on things. Okay, listen to me. The first root node of a decision tree, you see this, the first root node of a decision tree, my people, the entire fight that you're going to do for decision tree is to decide which root node you have to take. I'll give an example. Imagine, guys, I ask you to make a classification algorithm. Okay, let's say I ask you to make a classification algorithm that, given the age, given the salary, can you predict will the person get a loan or not? So answer will be yes or no. And suppose the age is 23, your salary is 12 lakh rupees per annum, okay? Or 12,000 rupees per month, for example. And your age is 40, and you get 1,65,000 example. So you see the output for the loan would be yes and no, right? Like, so no and yes. So actually no and yes. Example. Suppose I ask you to do this. Now tell me one thing. Will age be used as the top node or salary will be used as a top node? Which node will decide how the tree will be made? Are you understanding? Will age come at the top and then salary go to the bottom and then loan is decided on that, or age? So see, that decision is not based on visual understanding. Like you can't say age or salary. That's not how it works. Whichever value has the highest information gain, only that root node is selected. Are you clear? You have to calculate the entropy of the entire data set. Then you have to calculate the information gain of the age, then information gain of the salary. Whoever has the highest information gain will be selected as the decision node. Are you clear? We'll do the exercise. Don't worry. I'll show you guys the mathematical understanding. Remember one thing. This question is an interview asked question. In decision tree, how do you select a decision node or the root node? It is also called as root node. Okay. Your answer should be, in decision trees, root node is decided based on the concept of entropy or information gain. What will you say? Entropy or information gain. Are you clear? Any one, not both. Any one is used. Okay. Either you can use entropy or you can use information gain. Most algorithms use entropy. Okay. But we will teach both entropy and information gain. Okay. In decision tree, when splits are happening, they are called branches. So every line you see is a branch. Cool. Every line that you see being split is called as a branch. Again, once the decision node is taken, this is called root node. You can call all other nodes as decisions node. And remember one thing, my people. Tell me one thing. If the information gain or entropy was good for decision node 1, the second best will go here. The third best will go here. Did it now make sense? The second most important information goes to the left, the other third goes to right. And if you have more columns, then depending on whichever is the best, second best, third best, fourth best, the split keeps happening. And you, at the end of the day, are left with leaves. Leaves are something that has no branches. It's the end of the decision tree. Okay. Can I tell you guys something? You will be amazed. Decision tree can be used for both regression and classification. This algorithm is so versatile, is so awesome that if you want to solve regression problems, you can even use it. If you want to solve it for classification, you can use it. Look at it. Decision tree classifier. So see, I will file decision tree classifier. Okay. But if I say decision tree regressor, you will find decision tree regressor also. You will find decision tree classifier also. So do you see you have a decision tree classifier for classification and you can even use it for regression. So decision tree is a very, very versatile algorithm. Okay. It can be used for both regression and classification and it can do both the jobs incredibly well. Okay. So just for your understanding, I was telling you that this is such an important algorithm. Everybody needs to understand. You remember the formula I gave you? Entropy was E of S. S is what, my people? The class. All the classes. Elephant. What did we take? Tiger, monkey, and giraffe. All 4 classes is this S. Okay, mathematically speaking, is equal to summation of I equals to 1 to all the classes minus P of I log of base 2, actually log to the base 2 P of I. This is the formula for entropy and I even showed you how to solve that, right? Do you remember? We actually did this example. We actually did that example. Okay. After entropy, Gini impurity. More the classes, higher is the impurity. Yes or no? The more you will add multiple stuff together, the more the impurity sort of arrives. So Gini impurity could be G of S. S means all the classes included. 1 minus summation of I equals to 1, including all the classes, all the probabilities, you square them. This was the formula for Gini impurity, right? Very simple concept. We actually did this. We actually got an idea. So now tell me one thing. Entropy and information gain. See, the concept of entropy and information gain, they are inversely proportional. Are you clear? If entropy increases, the gain decreases. And if the gain increases, the entropy decreases. Now, I haven't taught you information gain yet, so just keep one idea, but it should give you an idea. Tell me one thing. If the entropy, the chaosness, the randomness of an order is higher, won't the information in that system will be lower? Because it is not giving me a proper system, proper understanding of things. Okay. Now listen to me. Information gain. What is it exactly? See, information gain is a measure of how much information a feature provides about a class. Okay. Information gain is a measure of MEASURE, measure of how much a feature, provides information about a class. Now give me 1 second. I will explain you what this particular thing means. In this example of age versus salary, you have how many columns? 3. How many feature? How many target? 2 feature, 1 target. Imagine, for one understanding, I add one more column. Area. What area does the person live in? Good area, bad area, okay area. For area, there are 3 classification: good, bad, okay. How well does good area relate to the target? How does bad area relate to the target? Okay area relate to the target. How much information is a subclass providing to the entire target? What is causing that variable to cause change in the target? Did you get it? The information. If you don't want to think it like this, think it like this. How good does age provide information to predict target? Did that make sense? How much is age important in the prediction of the loan? How important is this variable? Did that go inside your head, seep inside your head? What did I tell you? I told you information gain is a measure of how much a feature provides. Okay. See, correlation is a different concept. Okay. Correlation is when column A, column B are correlated. They both provide the same information. I am basically trying to tell you the importance of A for the prediction of target. Okay. I want you to think of it like this, not correlation. Correlation happens only in the feature space, not feature versus target space. Have you heard of something called correlation and covariance? Point number 1. Never ever get confused by the concept of correlation and covariance. Correlation happens when you have a feature called A, B, and C, and you have to predict a target. How related A, B, B, C, and A, C are is correlation. Okay. Covariance is when A changes, how much B changes. When A changes, how much C changes. When A changes, how much B and C change. That is covariance. One thing changes, what causes the change in another? If I move 1 centimeter, how much the column B moves? 5 centimeter. This is covariance, clear covariance. Okay. We don't check it with respect to the target, the information it holds to the target. Okay. Anyways, no problem. Information gain is a measure of how much a feature provides about a class. Everything will make sense. Give me 5 minutes. Okay. Information gain. It calculates the difference between entropy before split. Okay. Entropy before split and average entropy after split. And average entropy after split. This statement is not going to make any sense to you. Even if I teach it to you, it's not going to make sense. So allow me to jump into a mathematical exercise and you will understand everything. But let's write down the formula first. Information gain for the class S as a function of F is equal to entropy for that class minus summation of, because I want to take an average, the class feature that maps to function F S nu by S. And this is a mod function. That means you cannot take a negative function, entropy of S nu. Now tell me one thing, what the equation tells you. When I initially learned decision tree, when I was going through the concept of information gain, entropy, and all of that stuff, right? It was, of course, complicated for everybody to understand. But then what I did is I solved a problem statement. I actually solved a problem and everything started making sense. So do you see this data set right in front of you? Okay. This data set is very, very simple. Okay. What this tells you is, what was the outlook of that day? Was it sunny? Was it rain? Or was it overcast? What was the temperature that day? Was it hot, cool, or mild? What was the humidity? How was the humidity like? Was it high, normal, or high or normal? And actually both. Wind was weak or strong. Depending on all your feature variables like outlook, temperature, humidity, and windy or wind, did you actually decide to play tennis? Yes or no? This is the prediction that we want to do. This is the prediction that we want to do. If it was rain that day, the temperature was mild, the humidity was high, and the wind was weak, you actually went ahead and played tennis. So this is my actual data set on which I'll be working on. Let's start solving manual exercise. Okay, let's do this. What is the first thing you're going to calculate before even jumping into anything? What did I tell you? The first thing you calculate in the entire data set is the entropy of the data set, isn't it? We calculate the entropy of the entire data set, yes or no? 100% yes. Let's calculate the number of no's and yes. How many no do we have? 1, 2, 3, 4, 5. How many no's? 5 no's. So in the entire data set, how many classes do I have? I have 9 yeses because this is 14. So I will have 9 yeses. And how many no's? 5 no's. Yes or no? Because remember, we have to calculate the category of our output, which is 5, 9 yeses and 5 no's. So if you calculate the entropy E of S, how will you calculate this? Minus of 9 by 14, because the overall data set size is 14, right? Log to the base 2 of 9 by 14. What is the next sign? If you keep minus outside, then you will get plus. But if I don't keep minus outside, I'll still get minus. 5 by 14 log to the base 2, 5 by 14. If you solve this particular example, you will get an output called 0.94. What is the entropy of the data set before even doing anything that we got? 0.94. This is the chaotic, the most mixed answer that we can get, the most highest entropy answer that we can get, 0.94. Answer has come, arrived. Okay. What is the next step? Next step is you are supposed to select each column and test how good is this column, because after calculating entropy, what is the second biggest fight that we do? The next biggest fight that we have to do after calculating entropy, what do we have to do? To decide what? To decide who will be what? Root node. The next biggest fight is, bhaiya, who will be root node? If you don't know how to calculate right after entropy, who to decide as root node, kuch nahi kar sakte aap. You can't even make a decision tree. The first thing that you have to do, I'm saying second first, because entropy needs to calculate first, is to calculate who will be root node. Will outlook be root node? Will temperature be root node? Will humidity be root node? Or windy be root node? Which node decides the best way to split my data, to create my decision tree? So tell me one thing. Can we take outlook as an example? First example, we will take outlook since it's a part of the beginning. So tell me one thing. Outlook. What do we do about Outlook? Now tell me, Outlook has how many categories? Sunny. Sunny, what is the next thing? Overcast and rain. Yes or no? So Outlook has 3 categories inside it. Let's calculate each category. So what is S of sunny? S-U-N-N-Y, sunny. My people, only and only consider sunny. 1, 2, 3, 4, 5. How many sunnies are there? In sunnies, how many yeses and how many nos are there? So in sunny, we have 1, 2, 3, 4, and 5. So basically 2 yeses and 3 nos. Yes or no? 2 yeses and 3 nos. Yes or no? For S of sunny, for class sunny, we have 2 yeses and no. Now, why are we taking yes and no? Because the target is yes and no. Agree or disagree? If the target was 3, we would have taken 3. But the target is only yes and no, so I'm only taking 2. So my people, how do you apply entropy for sunny? Now you have to calculate, okay? Entropy for S of sunny is how much? Minus 2 by 5 log to the base 2 by 5 minus 3 by 5 log to the base 3 by 5. Are you clear? You will get an output called 0.971 entropy for class sunny. Okay? You will get this output 0.971. We will keep it as this is for now. For now. What is the next category we need to calculate? S of overcast. Yes or no? Now tell me, how many overcast yeses and nos do we have? So overcast 1, overcast 2, overcast 3, overcast 4. So together 4. So you will have 4 yeses and 0 nos. All yeses, right? So we will say 4 yeses and 0 no. Let me tell you one thing, my people. If any of the answer is either yes or no is 0, the entropy for that variable becomes 0 automatically because log is added. So multiplication of anything with 0 is a 0. So if any of the categorization either on the left or either on the right is 0, the answer is 0. You don't even have to calculate. The answer becomes 0. It summations to 0. Okay. What is the next category? S of rain. Now, my people, for rain, how many yeses and nos? 3 yes and 2 no. So tell me one thing. Entropy of S rain, okay, for category rain is minus 3 by 5 log to the base 3 by 5 minus 2 by 5 log to the base 2 by 5. Yes or no? Shouldn't this be the answer? If you calculate this, okay, let me help you calculate. 971? Okay. Okay. Tell me one thing. What have you calculated so far? You've calculated entropy for the entire data set before the split. Okay. Can you have a look at this example? Before the split, after the split, it'll all make sense now. This is the entropy of the data for the entire data set. According to the information gain formula, did I not write it like this? Information gain, which is gain of class S for Outlook category as a function of Outlook. Did it now make sense? What is this F? What is this F? Is your class. And S is all the subcategory of the class. For example, Outlook mein sunny, overcast and rain. So this is sunny, overcast and rain. And this is Outlook. Did that make sense? चलो मैं क्वेश्चन में फॉर्मूला ही लिख देता हूं. Everything will make sense, no problem. Entropy of S minus, can you see I've taken minus? Summation of, tell me one thing. I am categorizing for how many subclasses? Sunny, overcast, and rain. So mu, the mu or the nu has to repeat for how many classes? Sunny, overcast, and rain. S of nu divided by S, entropy of S of nu. Okay. If I replace the values inside this, sir, I want to replace the values inside it. Okay, no problem. What is the entropy of S means the entire data set. What is the entropy of the entire data set before the split? 0.94. 0.94 minus. Okay. Now I'm going to write down this formula. Okay. How many times does Sunny repeat? 1, 2, 3, 4. And where is one more? 5. How many times is Sunny repeating itself? 5 times? 5 divided by, what is the total data set size? 14. Into entropy of Sunny minus how many overcast is that? Or how many overcast do you have? 1, 2, 3, 4. So minus 4 divided by 14 into entropy of overcast minus how many rain do we have? 1, 2, 3, 4 and 5. Minus 5 divided by 14 entropy of rain. Did you understand the formula? Because it belongs to all categories. So their calculation is important. So is equal to 0.94 minus 5 divided by 14 into what is entropy of Sunny? We just calculated 0.971 minus 4 divided by 14 into overcast is 0, correct? We had nothing. Minus 5 divided by 14 into 0.9 something 71 entropy of rain. If you replace all these values, you will get a gain of 0.2456 or 64 something. 2464, 2465 something you will get like this. This is the gain for what category or what variable? Only and only Outlook you got for. So you got for Outlook. If you repeat the same exercise for temperature, humidity and wind, whichever value has gain higher, that will be selected as root node. Did it make sense? I'm not going to repeat it again and again because it's a longer exercise. If I do it by hand, trust me, it's going to take us more hours. I just taught you how to do it for one category, and I'm very sure you guys, if you want to try it out on your own, you can do it for multiple categories. But do you see, we used the concept of entropy, and we calculated something called gain at the end. And gain told us how important this feature is in predicting target. Hence, this should be selected as root node. Remember one thing, my people. It never happens that gain of one variable and gain of other variable are always equal. ये कभी नहीं होगा. Okay. Let's pretty much take it like this. Okay. Okay. How many variables are there? How many variables are there? 4. Imagine, for simplicity reasons, the gain of S comma Outlook is equal to how much was it? 0.2464. 0.2464. For simplicity reason, let me say the gain of S comma, what is it? Outlook के बाद temperature. Gain of S comma temperature के बाद क्या है? Humidity. Humidity. ठीक है? Gain of S के बाद क्या है? Wind. Comma wind. Okay. Imagine, for simplicity reasons, okay, this is 0.0289. हाँ मतलब some random values I'm giving. 0.1516 and आप इसको ले लीजिए कुछ भी ऐसा 0.0478 example. Which gain is the highest number among all? Which one will you select as a root node? Outlook. Remember one thing, my people. Decision tree is like a blueprint. Yes or no? Once the tree is made, every decisions will be taken based on the blueprint. You remember the giraffe exercise I showed you? I pulled a giraffe, it goes to the left, then it goes to the right, it goes to the right, and it comes to the bottom. Decision tree is like a pratha. Once it is established, everybody has to follow it. And then you will be segregated in the bottom. And any tree that you make should only have one root node. You can't have two. Okay, hold on. First of all, when you have two root node, is it a tree or is it a graph? A root node decides the flow. Two root node decides. Okay, how do I say this? Like it's a part of data structures. Have you seen a single linked list which is connected to another list? Then you have something called doubly linked list, which has a single and two pointers. Then you have a circular linked list, right? The flow is unidirectional, correct? When you open the tap, the water flows. Or do you pump water through the tap? Are you understanding what I'm trying to say? A decision tree is called a decision tree because it's a unilateral flow, one flow. The input comes to the top, output goes to the bottom. If the decision tree actually will not be called decision tree, has two different nodes, it's not a node, it's a graph. Okay. You have to calculate the process of information gain for outlook, temperature, humidity, wind, and for each of it category unless you exhaust all your feature space. Until the feature space is exhausted, until all the feature variables are taken with respect to the tennis of yes and no, until then you have to do this exercise. You have to keep repeating this manually. Okay. How about you want to see this example in real life? And you know what? Just for fun, I mean, not for fun though, like for proper understanding of things also. What if we take the same exact data set like we did with tennis DF and we solve and see how that works? Then we'll take one more data set. The one that I just taught you right now, this tennis data set. How about I teach you a decision tree classifier? How will it be done in practical with this? And at the same time, we'll take another data set for practical purposes. Let's look at both the data sets, okay? So that you guys will get a pretty good idea. Now tell me one thing. Import pandas as PD, yes or no? Import numpy as NP, yes or no, my people? Hey, Pansas, sorry. I don't know about Pansas, but I know about pandas. Happens. I'm a really fast, you know. I type so fast that sometimes my Pansas library is not to be seen. No problem. No issues. df equals to pd.read csv. Okay. If you guys didn't know this, I'm just letting you know, you can do this. Am I getting the output? Sunny, hot, high, false, no. Sunny, hot, high, weak मतलब false and no. मतलब मैंने weak नहीं लिया है. Weak strong को true false ले लिया है. Sunny, hot, high, false, no. Sunny, hot, high, false, no. Data वही है. If you do df dot shape, how many columns did we have? 5 columns and 40 row. Yes or no? Agree, disagree? Okay. Now tell me one thing. Before I even do anything, will I be able to run machine learning or any analysis on this? High, low, good, bad, true, false. इस पे कुछ कर सकते हैं? Can we do something on it? Is it possible to even approach anything? You need to convert. You need to encode this yes or no. Otherwise, how will you run a decision tree classifier? From sklearn, what do you need to do? From sklearn, because this is a part of pre-processing, you have to call pre-processing. And you have to import label encoder. We are going to import label encoder. Now let me give it a function. Label encoder is equal to label encoder. Say example like this, right? Label encoder. But this function needs to be callable. Are you clear? You need to put a bracket inside this. Here you have no bracket because you're importing a part or module. Here you need to put a bracket because you are calling that function. So df is equal to df.apply. You know what apply is? Apply lets you run the output, the function on entire columns one by one. If you know, in pandas, we have a function called apply. Apply runs it on the columns. Okay. Le dot fit the model and transform the model. Basically fit transform. We call it fit transform. And if I run df dot head of 5 again, is everything converted? Okay. Can I tell you guys one thing and you should take it as an important interview question? If I tell you, will you please agree what I'm saying is an important question? In your interview, this person, your interviewer, is gonna ask you this question. What is dot fit in machine learning? Okay. What is transform in machine learning, and भैया what is fit underscore transform in machine learning? इन तीनों का difference बताओ. ये question इतना important है. I cannot even tell you the importance this question carries in your life. If you are not able to answer this, don't even talk about decision tree. वहां तक नहीं जाएंगे. Can I give you guys a small assignment so that you read it up on your own? I don't be your hand holder every time. I don't become your stick. I tell you in 2 seconds. You're like, अरे हाँ ये तो आता है. Can you guys do a research on this? कि why have I only applied fit transform? Why did I not do label encoder dot fit and then transform? Actually answer ही दे दिया मैंने. But will you please finish this as an assignment? कि in machine learning, why do we do dot fit? Why do we do dot transform? Why do we do fit transform? Label encoder will give it 0, 1, and 2, right? This is going to give it a label encoding. Why don't we do one hot encoding? You can even do one hot encoding. That's not a problem. Because the numbers of subcategories are so low, label encoding works well. It has no problem. The machine learning model does not get biased when it is categories. Let me give you an example. Have you heard of something called nominal categories and ordinal categories, my dear? What is a nominal data as an ordinal data? Which data order matters? In which category order matters? Ordinal or nominal? Example, if you rate your food 1, 2, 3, 4, 5, will the order matter? And suppose I tell you car like Mercedes-Benz, Audi and Ferrari, example, does the order I rank them in matter? Okay. Coming back to the same topic. Does the order matter here? So it's nominal or ordinal? Nominal. The encoding that you can apply to this is both one hot encoding and label encoding. Because the categorizations are so small, it won't make any difference for the machine learning to give a bias. Okay, so label encoder is like a good choice. Not a problem. You can apply it here. What is my feature space? If I just drop, what do I drop? Just the play part. Okay, just the play part for all the axis as 1. And if I take x dot head of 4, did I just get my variable outlook, temperature, humidity, and windy, which is my target variable, the one that I want? And if I want to take y, I just need to take df dot play. That's it. Done it. If I just take this part, my y category is set, right? My y dot head is 5. Yeah. I got my feature and my target. Agree, disagree? Now we will split the data. From sklearn, what have I taught you? Dot model selection. What do we select? Import xtrain, xtest, ytrain, ytest. From sklearn, dot tree, because you're doing a tree based classification, dot tree, import decision tree classifier. The classifier is equal to decision tree classifier. And remember one thing, you want the tree to be split on based on entropy or Gini entropy, Gini impurity. What have I taught you? That we split the tree based on what? Entropy, right? I have taught you that we split the tree based on entropy, right? Like we calculate entropy. Yeah, that's nice. Thank you so much. So what will you write? Criterion is equal to entropy. Classifier dot fit. What will you fit inside it? What two variables need to fit inside a variable? X underscore train and Y underscore train. Yes or no? Did I get a classifier run? Is my classifier basically done? It's running, it's getting the output. Okay. How do you predict the output? Ypred equals to what do we say for Ypred? Classifier dot predict X underscore test. Yes or no? This is all my Ypred answer. Yes or no? Okay. from sklearn dot metrics, okay, input accuracy score of what do you pass? Y test, Y pred. What answer did we get? Oh, 100% we got. Imagine 100% accuracy we got. If you do this, are you starting to get an error, my friend? You see, we got an output. Okay, first of all, I got an X test, comma Y test. I've added. ठीक है, मैंने X test डाल दिया, Y test डाल दिया. But why is it giving me error? Can you tell me? The reason why accuracy scores only work on Y test, Y pred is because for the Y test result and the Y pred results, aren't we comparing what we got? Aren't we kind of getting an understanding that, okay, what did I do to get an output? What did I do to fix this output? Basically, all the test set that I've taken, how many test set have I taken? If I take 20%, does it change the answer? Let's teach you something important, okay? Decision tree classifier, come here. My people, I have used criterion equals to entropy. What if I use criteria equals to Gini? Then kya hoga? Let's try. Am I getting an output called 33%? Okay, so here I changed it to Gini impurity. Okay, I told you one thing, you remember? Either we decide on the basis of entropy to split the data or Gini impurity to split the data. Any one can be chosen. Yes or no, my people? Agree, disagree? Okay. Tell me one thing. Initially, I chose the entropy as the criteria and I ran it. What was my output like? 100%. But suddenly I changed the entropy to Gini and Gini to impurity. Now it is giving me 66%. Isn't it weird? Let me show you once again. Hold on. Cell, run all. Okay. It's giving me 33 now. Okay. Cell, run all. It's giving me 100% now. Cell, run all. It's giving me 100% now. Now see what happens. The moment I change this to Gini, cell, run all, 66%. Okay, cell, run all, 66%. What's happening? What do you think is the reason for all of this? See, coming over here, okay, or coming and trying to teach you how to use a classifier syntax is not my job. My job is to make you think deeper. Okay. My job is to make you think the things you would have never thought of thinking. That is my job. What makes you think this is okay? Let's do one more thing. Let's make you think more weirder stuff. Give me 1 second. पूरा confuse करते हैं आज तुमको रुको. Okay, give me 1 second. Give me 1 second. I don't want any class weights. I don't want max features. I want to not touch this. Default is 2, which is fine. Min sample weight, max features. Max features are actually fine. But actually, you know what? By default, it is, let's take it as square root, I guess. Okay, let's try to change the hyperparameters a little differently, okay? Let's take this to Control Z, entropy. Cell run all. If I run this and I have taken entropy, okay, my criteria, cell run all. Give me 1 second. Okay. What is the final output that we are getting? 100%. Agree or disagree? It is overconfident in its output. Okay. Let me tell you the problem that this decision tree faces, okay? My people, remember one thing. Decision tree is an important algorithm. Very nice, very good. But do you know what is the biggest problem of decision tree? It usually tends to overfit very easily. Depending on the sample size, the data that you have given it to train, if the training set is so small, it usually will overfit. Do you understand, my people? Imagine I have 14 samples and I only gave it 10% of test size. What is 14 of 10%? What is 10% of 14? 1.4. Usually Python takes a lower record size, which is 1. I am only taking one as a test set and the other as a other as a training set. Are you understanding what's happening here? Did you understand what's happening? Hold on. Let's make the test size as, I don't know, 40. Cell, run all. Look, the output is 0.16%. What did you understand from this? Point number one, decision tree is a terrible algorithm if the data set size is lower. Are you clear? It will overfit, and it is usually an algorithm that tends to overfit. Decision tree is a right algorithm if you have a large quantity of data, you have a good equation for test and training. If you have such a small data of 14 records and you're trying to fit decision tree, you think that's a good option? For a minute, logistic regression would have worked better, but not decision tree. Are you clear? There is nothing to be confused here. It's common sense. I wanted to just run it through you and tell you the answer. That just because I gave praises to decision tree in the beginning, that it can do both regression, it can do both classification, doesn't mean you use it for everything. Decision tree usually tends to overfit. It is usually overconfident. अरे मेरे को तो सब आता है. एक बात बताओ, do you all understand the concept of overfit का मतलब क्या होता है? आप समझते हो? Do you all understand the meaning of overfit? Let me go through the concept. Let me go through the concept. Give me 1 second. People, imagine you have exams to give. Okay? You have exams to give. I will give you a question paper, a test paper. 1 plus 1 equals to 2. 2 plus 1 equal to 3. 3 plus 1 equal to 4. Example. In the exam, if they ask what is 5 plus 4, aren't you supposed to solve that problem? Because you're supposed to understand the basics, the pattern of the test. Yes or no? Okay. What is overfitting, underfitting, and right fitting meaning? The meaning behind it is whenever you are asked the question 1 plus 1, automatically you will say 1 plus 1 is 2. Because all you saw is 1 plus 1 in the test. Yes or no? In the training of your mathematics class, you saw 1 plus 1. But the moment I will give you 2 plus 3, you will not be able to do it because that was not taught to you. You will be able to do 1 plus 1, 2 plus 1, 3 plus 1 because you've memorized it so much. You've memorized the data so much that the moment something comes, you've memorized it so well, the output comes. That is overfit. Are you clear? Overconfident, overfit. Only what training comes, I'll able to answer that. The goal of machine learning algorithm is only to pick up patterns, right? And not memorize anything. Correct or not? The goal of machine learning is to understand the patterns behind the data, not to memorize the data. When you overfit, you memorize it so well that you become overconfident. अरे मेरे को तो मैथ में सब आता है, अब पेपर आने दो, फाड़ दूंगा मैं. That is the overfitting problem that decision tree usually has. Can somebody tell me why? Because decision tree are once finalized, will be finalized forever, correct? एक बार decision tree बन गया, it is not going to change, correct? Did that make sense, my people? Once a decision tree's root node is finalized, another nodes are finalized, will it automatically adapt itself or change, or will it remain constant no matter if the data changes also? That is the problem. It is constant. Let's plot it. Let's try to visualize it. Okay. But did you guys get the concept which was important? I'll show you. Okay. I'll show you. Import matplotlib.pyplot as PLT. Okay. As PLT. Okay. As a PLT. From sklearn, skimage nahi, sklearn, import tree. Okay. Here I've just taken matplotlib as pyplot as PLT. From sklearn, I've imported tree. Figure comma axis, or not this, figure comma axis. You guys remember, right? In matplotlib, we have an option of taking sub figures also, multiple sub figures if I want to take it. Like if I do like this, subplots, subplots, like this, like I have the options of taking subplots. Okay. N rows equals to 1. N rows equals to 1. I hope I'm taking it right. I've not done it since a long time. I don't remember. I may not remember the syntax, so apologies for that. What is the figure size or figure size? Let's take it a minimal 5,5 figure size. Oh, let's take it smaller actually, not more. 4,4. Let's take it 4,4. Yeah, I mean, and let's keep the DPI to a minimum of 150, 200. Okay. 3 dot Okay, let me just basically run this. Tree dot. Okay. So if I say plot tree and if I pass in the value of a classifier like this, okay, so I think it should run. Okay. Okay, let's keep the DPI smaller. Let's keep it 100. How? Do you see the tree it created, my people? See, you can visualize the tree. The class is outlook, okay, which is less than equal to 0.5. The entropy was 0.811 according to its calculation. Okay, the entropy was this much, the entropy was 0, and it basically created a tree for you. So can you see I'm actually plotting the tree that the classifier actually made. If I would have taken Guinea, it would have given me a different tree. You can even plot a decision tree and validate the results. It's not that you just run it and you have to accept it. See, this is the plot that the classifier built from the code side. Okay. There is another library called GraphViz. Decision tree. Remember one thing, my people. There is another library called GraphViz. I actually learned about it a little later because I never implemented a decision tree in production. To be frank, no company would have deployed decision tree as a production in their company because there are better algorithms like XGBoost, multiple other better algorithms. So see, this gives you a much prettier result. So this is a library called GraphViz. You can even try this out. See, this is a GraphViz library. So I have imported the tree package from sklearn package, but if you want to make it appear more beautiful, more pretty, you can do that using that also. As in, you can do it prettily in a nicer sense also. That was a point. Okay. Now coming back to this question, okay, you make this test size as 30. Don't make it higher. Okay. Usually, if you take a test size of 30, you get a decent score of 40%. Okay. Remember one thing, my people, there's a thumb rule. If your data set size is smaller, make sure that your test and test size are almost nearer. So 60-40 split is usually taken, or maybe 70-30 split is taken. You don't take more. If your training size is bigger, then you take 80-20. Are you clear? If your data set size is smaller, usually people prefer 60-40 or 70-30. But if your data set size is larger, you prefer a set of 80-20. Okay? The tree that I have now is a little different from the tree in the past. Why is that? What did I change that it ran? Okay, let me run it again. Okay, cell, run all. Is the tree now not different? Let's change the DPI to 150. Yeah. चलो 100 ही रख लेते हैं. Kernel, restart and clear output. Okay, restart and clear output. Kernel, cell, run all. Okay. Look at the tree now. Okay. Is it slightly different from the previous tree? This is happening because, the test keeps changing. Also, I have not used any randomizer here. Here, I would have taken some seed function, which you called as a random state function. If I would have kept it same, it would have been same. You guys got the concept, right? Like whenever you work on decision tree, you fix the data, the sampling of the lowers and the rights, the test and the train, so that they don't get sampled again and again. Okay? Because they get sampled again and again, the value changes because what would have been in training now goes in testing. Okay, so this was just to give you guys an idea about what we solved here versus what we got here is kind of similar, and it also gives you an understanding of how important this library, this package is. But tell me one thing. I want to ask you guys one thing. In your real life machine learning, will you implement multiple algorithms or will you take one data set and on that you will implement multiple algorithms? What do you do? The second one, yes or no? Can we try that? Can we take one data set, implement logistic regression, implement a decision tree, for fun, implement a dummy classifier and print AOC ROC score, print accuracy score, print confusion matrix, and then decide it would be amazing or not? Should we do it on a different practical data set? This was just to make you guys understand few things in life, but this was not like the actual data set that I wanted to start with. This was just like, so it's for fun. Okay. Anyways, df is equal to pd.read CSV of. Now here, I want to take another. How do I say this? Okay. Let's think of it like this. Okay. See, I want to basically take like a different data set for you. I think हाँ यही करा देता हूँ, चलो आपको ये data set भी अच्छा लगेगा. You guys will like it because it's very numeric in nature. You guys will understand. You guys will love it. Okay. I think this data set will teach you a lot in life. Listen to me carefully. Okay. This data set is all about a person's age. Okay. A person's age, a person's, you know what? Give me 1 second. I'll make it easier for you to understand. Give me 1 second. पहले data set समझते हैं. Come here. ठीक है? This is a column called person's age. 63, 60, 37, 41, 56, 57. Any confusion? Second is by sex. अगर 1 है तो मेल है, 0 है तो फीमेल है. CP is nothing but just chest pain. आपका chest pain किस टाइप का है? Do you have asymptomatic, atypical angina, non-typical angina या typical angina pain? ये भी हमें पता नहीं है. But 0, 1, 2, 3 लिखें. Label encoded है. This is label encoded. Thresh BPL is the resting blood pressure of the person. Then you have the cholesterol, the fasting blood sugar, echocardiogram result. Okay. This is the heart rate of a person. Okay. This is the included exercise angina. This is old peak slope and basically बहुत सारे medical values दिए हुए हैं. Did you understand? You see target is equal to 1. आपको यहाँ दिख रहा है क्या? Target heart disease. 1 मतलब नहीं आया, 0 मतलब आया. Given somebody's age, his, her sex, the chest plate and all of that, did the person get heart attack or no? The possibility did the person get heart attack or no? Heart attack or no? Isn't this a logistic? Isn't this a classification use case? तो अपने को clearly पता है कि अपना target ही target है. The target itself is a target. Yes or no? Okay. This is my data set. What is the things that you usually do? पहले तो देख लेते हैं how big is a data set, right? So when we do df.shape, how big is a data set? How large is our data set? 303 rows, 15 columns. 303 rows and 15 columns. Now tell me one thing. If I want to split my X and my Y separately, what do? Won't I just go ahead and drop? What will I drop from that particular thing? I will drop target. Yes or no? I just want to drop target from the column and axis equals to 1. Okay. And axis equals to 1. If I do this, I will get the value of X. Agree or disagree, my people? Yes or no? And if I take Y, can I not just take df dot target or df of target, anything? You can take it however you want, right? So if I do Y dot head of 4, did I just get my X and Y separated properly? I have no issues. Everything is proper and sorted. Very nice. I have my X and Y sorted. But you know what? In machine learning, there is one more problem. Let me ask you what that problem is. My people, imagine you have a person whose column is age and another person whose column is salary. Now tell me one thing. Age is of what limit? Maybe 18 se leke 70 max. Agree? The salary range could be ranging from 15,000 to 1.5 crore. Now listen to me very carefully. Because the column age has a different range and salary has a different range, won't machine learning give preference to the salary column more than the age column because the numbers tend to be higher? Look at the data. Cholesterol is between 200. Age is between 63. CP is a variable which is 0, 1 and 2. And old peak is 1.2, 2.3. Aren't we seeing multiple ranges here? Won't it be amazing to convert everything between 0 and 1? Age also between 0 and 1, salary also between 0 and 1. If everything becomes standardized, my machine learning model won't get confused and will be able to do a better job. I have taken an X variable, I have taken a Y variable because X features and target needs to be separate. Agree, disagree? Now tell me one thing. Can we split the data? Can we basically go ahead and split the data into multiple different types? Like basically, can we do this? Can we say X underscore train, comma X underscore test, okay, comma Y underscore train, comma Y underscore test? Can we do it? Is equal to train test split is equal to train test split of X comma Y comma test size equal to let's keep a test size of 20%, not more. Okay, let's not keep a test size higher. मैंने x train x test y train y test कर दिया. But now I will take something called scalar is equal to. Do you know or do you understand that in Python or specifically in our libraries, we have a scalar called standard scalar. Have you heard of it? I'll show you. See, यहाँ पे, before importing the package, let me also do import statement, okay? From sklearn dot pre-processing import standard scalar run. Okay, what I did, I have imported something called standard scalar. तो अब मैं यहाँ पे क्या करूंगा? I'm going to call standard scalar. What standard scalar is going to do for me? What did I just tell you right now? What standard scalar does? What will it do? X underscore train equals to scalar dot fit transform. Okay. What? Fit transform what? X train data. Because this is what I want to basically transform. I will take similarly X test is equal to, what do? Scalar. But यहाँ पे आप fit transform नहीं करोगे, यहाँ पे आप transform करोगे. That's why I told you we need to know the difference between the test, the fit, the transform, and the fit transform. Are you clear, my people? I run it. I'm set. I'm sorted. And don't worry, इतना कोई complicated चीज नहीं है वो. Fit, transform, fit, transform. It's a sequential process. Can we have like a dummy classifier? Do you know what is a dummy classifier, my people? A random classifier, a random guesser. वो guess करके ही अपना output निकाल लेता है. That is called as a random or a dummy classifier. Okay. It's like a random classifier, no problem. From sklearn dot dummy, okay, import dummy classifier. Okay, I've imported a dummy classifier and I'm running it. How do you call the dummy? See, what dummy classifier will become is, it'll become like a baseline for us. Okay, so let's say dummy underscore CLF underscore classifier is equal to. Now, how do you call dummy classifier? You call it like this, dummy classifier. Or you know what? एक काम करते हैं, छोड़ो, dummy को नहीं लेते हैं. I don't want to confuse you guys anymore. Then you guys will be unnecessarily confused. Let's not take any dummy classifier. Ignore करते हैं, no problem. पहले logistic ही लेते हैं, no issues. ठीक है? I don't want you guys to get confused later on. Okay? Logistic. What is the use of dummy classifier? See, dummy classifier is like a baseline model. Okay? What happens is when you choose 3 different models, you need to know the worst. How worse are you performing? मतलब if you are performing worse randomly, how terrible are you performing? It tells you the baseline कि इसके नीचे तो खराब होना ही नहीं है. If you have a data set and if you have a problem statement, how worse can you perform? The worst accuracy you're getting is 45%, and below this it's not possible. So minimum efficiency that you are allowed to reach, or you're reaching even if the worst case happens, that is dummy classifier. Very nice. Okay, let's call logistic. Now, how do you import logistic, my people? From sklearn, what do we call? Dot linear model. Import logistic regression. Yes or no? I'm just calling logistic regression. Acha. Lage hath. Let's also import decision tree. How do we call? From sklearn dot tree. What do we call? Import decision tree classifier. Agar now that we've imported it also, from sklearn dot metrics, what do we import, my people? First, let's import confusion matrix. आप लोगों को आज confusion matrix कैसा होता है वैसे दिखाता हूँ. Okay, import confusion matrix. Point number 1. Let's also import something called accuracy score. Let's also import something called classification report. You remember I've shown you how classification report looks like. Let's also import F1 score. और अगर AUC ROC score करेंगे तो वो भी निकाल लेते हैं. चलो, ROC curve and ROC AUC score. Okay, और AUC ROC score. ROC curve ले लिया, ROC AUC curve भी ले लेते हैं. ठीक है, because we'll also run AUC ROC at the bottom. So we've imported all the packages. Yeah, most of the packages I've imported, no problem. Now tell me one thing, how do you import logistic regression? Can I say something like this? Log reg is equal to logistic regression callable function, which is a callable function. What do you usually do once the log reg is done? Do we not fit it? Log reg dot fit the model. अब हम fit के अंदर क्या डालेंगे? X test, Y test, Y pred, Y test, और what? X train, Y train, है ना? Yes or no? The log output, logreg dot predict, what do I pass inside it usually? Isn't it the function x test that gives me the prediction of all the y prediction? Okay. Logistic regression accuracy score. So logistic regression accuracy score is nothing but accuracy score of what do I pass inside it? Y test and what do I pass? Y test and y pred log. Yes or no? ये वाला जो हमारा पार्ट है, दिस इज फॉर एक्यूरेसी कैलकुलेशन. लेट मी कॉल इट मेट्रिक्स. मैट्रिक्स. अरे यार, somebody should gift me a good keyboard soon, otherwise I'm going to break my laptop. Okay, I got an accuracy score. Okay, lr underscore f1 underscore score is equal to, what are we calculating here? F1 score. So can I call F1 score? What do I pass inside this? Y test, comma, y pred underscore log. Logistic regression confusion matrix. I'm just printing confusion matrix equals to. I'm going to call confusion matrix, and what I'm going to pass inside this? Y test, y pred log. कोई भी accuracy parameters are all the same. Y test, y pred log, y test, y pred log, y test, y pred log. That's nothing else. Let's make it a little neat. Let's make it a little nice. Okay, print. How do I print this? Print. First F. What am I printing? Accuracy score. What do I pass? LR underscore ac underscore score. This is my accuracy score. Yes or no? Print F double quotes. F1 score. F1 score is always on a test set. I hope you know. F1 score doesn't happen on a training set. ऐसा नहीं होता है. LR underscore F1 score. ठीक है? Print. अच्छा, accuracy और F1 हो गया. चलो थोड़ा better print करते हैं. Star star hyphen star star into 8. ठीक है? इसको भी ऐसे ले लेते हैं. Star and star. हाँ, I'll give a better output. Okay. Print confusion matrix. If I want to print confusion matrix, what do? Just print lr underscore conf underscore matrix. Yes or no? And take the same exact code, paste it here. But do you remember I also taught you a beautiful concept called classification report? If you remember, I also told you there is something called classification report. Print classification report of same thing, y test, comma, y pred underscore log. If I run this, are you getting all uh, uh, matrix, all the metrics that we need to print? So can you see I am printing something called पहले तो accuracy score. Oh baba, 100%. Look at this. F1 score is 100% overfitting. Data भी अच्छा खासा है. Why is it overfitting? We'll come to that, no problem. Do you look at the confusion matrix? Look at the precision and recall. 0 100%, 1 100%. Result तो terrible आया. Yes or no? Agree or disagree, my people? Okay. We all agree the results are terrible. I have run logistic regression. Can I run decision tree on it? Can I copy the whole thing exact as it is, because I don't have the energy to run it again, and I'm going to implement it here. Instead of calling logistic regression, can I call it decision tree classifier here directly? And rather than calling it logreg, let me call this tree. Yes. So instead of logreg.fit, can I say tree.fit? X train, Y train will remain same. Y pred log ke badle Y pred tree. Yes or no? And this will be tree.predict. Did I just change the line number, the first 3 lines as is? Tree is equal to decision tree classifier. Tree is equal to tree.fit. X train, Y train मैंने डाल दिया. Y pred tree को मैंने बोल दिया कि this is tree.predict X test. भैया first 3 lines are sorted. What do I change here? LR के बदले what do I pass here? Tree accuracy score is equal to accuracy score Y test, Y pred tree. Yes or no? अच्छा, ये LR के बदले हम क्या लिख सकते हैं? ट्री F1 स्कोर, तो यहाँ पे हम क्या पास करेंगे, वाई प्रेड ट्री. LR confusion matrix के बदले हम लिखेंगे ट्री confusion matrix and we will pass Y pred tree. Is this done? So LR के बदले हम लिखेंगे tree accuracy score, tree F1 score, tree confusion matrix and classification report will have tree. Agree or disagree? If I run this, भैया ये भी overfit कर रहा है. This also is overfitting. What is the problem? है ना? See, we have a good enough test site. हमारे पास data तो अच्छा खासा है. Why is it still overfitting? You know why it is overfitting? I'll tell you. My people, the moment something overfits, what is the thought in your data? What is the thought in your brain? Something must be wrong in the way I must have run the algorithm, isn't it? Your first thought process is maybe something I have imported is wrong, maybe something I've done is wrong. You forgot the most basic thing here. What is the most basic thing I did while importing the data here in this particular part? See, I have taken this data here, correct? I have taken this data here. df is equal to pd.read csv. I have taken this. Do you see another column called unnamed equals to 0, which is 0, 1, 2, 3, 4, 5, 6, 7. It's increasing, increasing, increasing. And the machine learning thinks that's also a part of the label. Did that make sense to you? So if I put a column here, I say index call equals to 0. Listen to me very carefully. If I run this, did I just drop the column index call equals to 0? That 0, 1, 2, 3, 4 was there. The column that you had, see, this column I'm talking about. If I run this, do you see unnamed equals to 0? Do you see this column unnamed equals to 0, my people? Yes. If I paste it again and run it, it's gone. Let's run it again. Did we get a different accuracy? Now my accuracy is 77% and my accuracy for decision tree is 67%. So tell me one thing. You must be thinking the problem is such a big problem, but where did the problem actually turn out to be? Where did the actual problem turn out to be? In the way you imported the data. So listen to me very carefully. As a data scientist, shouldn't you keep every step in your brain what I'm doing? You think about it, you plan it, and you know exactly what you're doing. Am I making sense? The moment you got 100% as your accuracy metric, overfitting both logistic and decision, you got confused. You thought maybe your program is wrong, maybe the data is wrong. You must have done one thing. You must have ran to your manager. You must have ran to your senior and say, sir, data acha nahi hai, it's overfitting. And if your manager or your senior sees this, what do you think he's going to make you of? What do you think he or she is going to do after they see this is the silly mistake you have done? Yes, that's why I thought that this example was very relevant. That's why I got excited in the beginning, because I have so many data sets. I randomly choose any one data set and I start teaching. Luckily, you guys got a data set like this today, and I thought maybe I'll make an example and teach you guys that it is very important to pre-process the data, to know exactly what is going in your X, to know exactly what is going in your Y, and you print the output absolutely accurately. I was at a point where I told you that you have to be very careful of the data processing that you do before you even start adding the values to it. Now, chalo, rest aside, let's try plotting AOC ROC's curve. But before we do that, let's have a proper formatted and a very nicely documented thing, okay? So let's take another column called model evaluation equals to. Now I want to convert this into a data frame, okay? So pd.data frame. What do I pass inside this? You can take it as an array, right? Like the model versus its accuracy. So we can say something like the model that we chose were of this type and the accuracy, okay? Accuracy was of this category. And if you also want to plot an F1 score, you can also plot an F1 score against it, right? So what model did we implement? Logistic regression, yes or no? We also implemented something called decision tree. What was the accuracy of logistic regression? LR underscore accuracy underscore score. Then tree underscore accuracy underscore score. Then for F1 score, what did we have? Tree F1. So LR underscore F1 and tree underscore F1. If I run this, right? And if I print model underscore EV, is this giving me like a proper analysis of the things that we've gotten, like a proper neatly arranged data frame that gives me an idea about, okay, you know what looks like that uh, you have properly and very neatly arranged the accuracy and the F1, and you have a comparative advantage of proper printing the whole thing out in a nicer way. Now tell me one thing. If I want to plot the ROC curve, so don't you think we need to have false positive rate and true positive rate, if you remember? So false positive rate for logistic regression and true positive rate for logistic regression, comma, what was that another thing that we did? THRESHOLDS, thresholds underscore logistic regression. Remember, we've done this in the last class, and I used a function called ROC curve to pass in y test, comma, y pred log. Do you remember we did this? Y test, y pred log. Okay. If I copy the same thing and if I paste it here, instead of log, I'm going to call this tree. Instead of log, I'm going to call this tree. And instead of log, Control Z, I'm going to call this tree. And what do I need to pass here? Yes, false positive rate, true positive rate. For logistic regression, I'm crossing the ROC curve. Any confusion in this part? What error is it giving me? Give me 1 second. Let's see. For input variables with consistent number of samples. Give me 1 second. I think I've changed something. FPR, DPR, ypred log, ypred tree. Did I have ypred tree? I had ypred tree, right? Tree.predict x test. Oh, tree.predict log reg dot predict x test. Tree.predict x test. I have that. No problem. What seems to be the error? The error seems to be generating from FPR, this thing. Okay, hold on. Give me 1 second. Ah, okay. I wrote it right. I did, right? Give me 1 second. I'm getting the same error. FPR, PPR, thresholds log, ROC curve of ypred log. Hold on. Let me just check the syntax, okay? ROC curve, sklearn. Yeah. Sometimes what happens is when I'm basically trying to print the values like this, I have to sort of be validated with if the results have been coming out right or not. Maybe sometimes I have issues with it. So y true, which is y label, right? I've passed in the y label properly. Y pred is correct. I'm so sorry. Do you see the mistake that I did here? It's y test, which is the y true. And I already have a y score. So yeah, that happens. Oh my God. Yeah. Give me 1 second. Let's see. You have pause label as none and sample weight and drop intermediate. Acha nahi. Haan, ji, we don't need that, right? We don't need that since it's a very simple. Hold on. Metrics.roc curve and y and scores and pause label equals to 3. We don't need pause label for that. Yeah. Y test, Y pred. Y test, Y pred. Y true with the Y score value. Huh, I got that right. ROC curve for that. Huh, okay, cool. Got it. Yeah. I know. Because I usually have the habit of saying ypred. So I passed in ypred twice, not knowing ypred log is the ypred. So that happens, right? So plot. How do I plot a diagonal curve? 0, 1, 0, 1, and then you have an R dash, like a dash line. Or you can change it later on if you want to. I'll show you how you can actually do it. Plot. What is the first plot that I want to do? FPR log, comma, TPR log, right? Like true positive, comma, false positive rate log. What do you pass inside it? You pass label. What is this algorithm that I'm passing through? Logistic regression, right? So logistic regression. What is the next data that I've taken? Plot. What do I pass inside this? FPR underscore tree, TPR underscore tree. What do I pass inside it? Sorry, LABEL, right? Label, yeah, L-A-B-E-L. Label equals to decision tree. And we will do legend and we will do X and Y axis later. No problem. What am I doing here? You guys understand? What do we do properly here is plot.x label, okay? Pass in plot.y label, plot.y label, and what I'm going to pass in on y label. And I will also do legend because legends are important, right? Because I have already passed in the label. I'll say location equals to upper or lower. I think let's keep it best. Okay, location equals to do. I don't need to do plot dot show because you just don't have to worry about it. Let's also take a title. Plot dot title. What title do we take? This is AUC ROC curve for what algorithm I have taken? Logreg and decision tree. Okay. X label. What comes on your X label? The false positive rate, right? And this is the true positive rate. ठीक है? अब हम इसको पूरा ही लेते हैं जैसे तो copy, paste, and apart from false, true positive rate. If I run this, which algorithm would you prefer for the output? Which algorithm is giving you much considerably better results in terms of accuracy in F1? So tell me one thing. For now, I have taught you how to implement only two algorithms, correct? Eventually, when I start teaching you 5, 6 algorithms, can you implement even 10 algorithms together, map them together and choose the best? My people, what I've taught you today is a practical way of doing things in your career, in your professional career. This is how you solve a problem. When you sit in a company, your company is going to give you data. This is how you run the test. This is how you actually implement the algorithm. Are you clear? I've just shown you guys a simple example, but I hope you got the concept of what I meant. Okay. See, मैंने आपको क्या क्या implement करके दिखाया. We have done implementation of logistic regression. We basically did logistic regression, correct? We did linear regression. We did in classification. We've also done decision trees, like specifically decision trees. What we've done. Okay.
Going to start the unsupervised learning, which is known as K-means clustering. What is K-means clustering? Before I get into K-means, I hope you recall what is unsupervised. So far we were doing only supervised learning, but if I may ask, what is unsupervised? Use of unlabeled data, right? That's correct. So see, remember when we were looking at supervised learning, we had a data structure like this. Just hold on. So let's say you used to see a table and used to have different variables, right? Right? X1, X2, X3, X4 up to Xn, n variables. And then you used to have a Y. This Y we call the labels, right? That actually helps you. So this is how we say label data, right? Y stands for your target or response. So in supervised learning, used to have this, but in unsupervised learning, this guy will not be present, right? This will not be there. Okay, so only the X values. So this is what you see in supervised learning. So let me write here. This is supervised learning. And if I just make a copy of it and I say this guy will not be there. So let's say this is X5 dot Xn. You got it, guys? This is X5. Just trying to, improvise that. Yeah. Then this becomes your unsupervised learning. So there are no targets, no labels. Okay. Means no labels. Implies unlabeled data. Cool. So you guys have an idea. So when you are in such situation, right, under unsupervised learning, right, you try to group data into clusters. So it's more like you're trying to find patterns. Since data has no levels, so you find patterns on the basis of similarity and then try to group them into cluster. So maybe I can also write it down. So in unsupervised learning, there is no output variable to guide the learning process. Data is explored by algorithms to find patterns. Given that data has no levels, the algorithm identifies similarities on the data points and groups them into clusters. Okay. So let's try to understand within that there's a concept of k-means clustering. Okay. So k-means clustering, K stands for number of cluster and means stand for averaging the data point position to find the center of the cluster, right? That's your mean. So k-means clustering means you're trying to divide the data, right? Basis the similarity into groups. So let me take a very simple example of demographic data. So demographic data, when you go and visit a mall and you go to a store like Zara or something like, some similar kind of stores, they take some of the data points from you, right? They can collect the customer data and try to divide the customer into different segments. So again, this brings me to this topic of that, when you're trying to go to a certain store, you will be, giving some data to different, uh, different stores. They will be taking your, name, age, gender. They might ask you some personal questions also, like how much your salary and all those things, and then try to, come up with down the line, you will get a mail on a mail, some marketing campaign is happening and you are getting informed, right? So that's what we say customer segmentation on the basis of similar trade. Okay. To solidify this conversation, I can take an example of, let's talk about how to say, have you ever gotten an ad or a call or any message for buying Audi? Anybody in this session? Audi or Merc? Merc is like Mercedes. Never ever, right? I know why. Because they know that we are not their customers, right? How they know that? Because they have the data for us. In India, too, it's very easy to get the data. बहुत आसान है. Now, if you talk about those kind of examples, right? Students never get called for credit card. Those who are really poor laborers, right? They don't give a call for loans, right? Why? Some of the guys get calls for loans, some of the guys get called for credit card, and some of the guys get called for audit, because they have the market segmentation. They know their market. How they know their market? So they have the data of their customers and then divide into different clusters. So can you see on the screen? And this is your customer base, right? On the left. I hope you can see a nice chart there. So this customer base, right? They divide into, as of now, here 4 clusters, saying that these are my recent customers. These are my champions. So they keep coming, keep buying, right? Keep spending money. They are like at-risk customers. Maybe they have not, they have not bought anything in last 1 years, right? And these are my loyal customers, right? So those kind of segments they have done, so that they know that how they can reach out to, to these kind of segments. And to give an idea, I think if my customers are at risk, what you will do to retain them? What should a company will do, right? They'll give some discount, right, guys? Come on, discount or offers. You agree? Those who are their loyal customers, right, they might not get a lot of discount because anyway they are loyal to us, so they might come every time, even keep pulling them, right? Champions and are the ones which are very aggressive. They have done a lot of shopping in recent time. You might not also give any discount to them, But if a new customer has come, you might give some more offer so that they keep coming back to us, right? So those kind of strategies can be used or leveraged if you have proper segmentation. Now you understand the application of k-means clustering can be one simple application can be like this. Okay, so as I go more into details, I'll tell you more about, but this is a very simple example and this algorithm is also very easy to understand. Okay, so how does k-means clustering, work and all I'll talk about in some time. Okay, let's move on. So let's try to answer what is k-means clustering, right? Means how do we define it? In k-means clustering technique, each cluster is represented by each cluster is represented by its center called a centroid, which corresponds to the assigned to the cluster. So if you see, we are saying each cluster is represented by its centroid, right? So center is called centroid, which is the arithmetic mean of all the data point assigned to that cluster, right? So when I'll take an example, you understand, okay? Now the question comes, what is a centroid? So a centroid is a single data point within that cluster, within the cluster, which represents the center of the cluster, and that means the mean. And that's where this mean is related to your k-means. Okay, that's where you got the name. So a centroid is a single data point within the cluster, within each cluster, which represents the center of the cluster called the mean, and it might not be necessarily be a member of the data set. So it can be a calculated value also, right? It's not necessary it's coming from one of the data set, is assigned like the mean, okay? So that is a very important point to keep in your head. That is not necessary that one of the data point will be given the role of the centroid. It may be possible that you might have calculated the centroid, although that value lies within that cluster, that group, but it's not necessary it's coming from one of the data points. Clear? Now, see here. So I'm showing an image just for your reference. Can you see? So there are two groups of the data it has formed. One group is this one, okay? Other group is this one, and it looks very logical because all these blue data points are more closer to this centroid, which is your red color, right, guys? Come on. And these are close to green, right? You agree? Because finding someone close to this is really not making sense, right? Saying this is close. So here you have two clusters. This is cluster 1 and this is cluster 2. If you try to see cluster 1 and cluster 2, they are having centroids, right? So this is your centroid of cluster 1 or for cluster 1. This is your centroid for cluster 2. Clear? So that's how you get to the centroid. So k-means clustering is all about finding that centroid, calculate. It's a calculated value. So calculate that centroid, and it's an iterative process. So first, they will assign any data point or any value as the centroid, and they keep updating it to find and I'll show you the example that how does this iteration work, but they'll keep trying to find the better one. And the whole idea is to minimize the within cluster distribution and maximizing the across the cluster distance. So what is the objective of the algorithm? K-means clustering tries to minimize distance of the points in a cluster with their centroid. So see, it tries to minimize what? Minimize the distance of the points in a cluster. right? There will be only one centroid for one cluster, because okay. For now, you should also understand what is my message here. My message is that you are trying to minimize the distance of the point within each cluster so that you find only one centroid, the better one. Okay. So you might start here. This is my centroid. Then you realize, okay, no, I'm not in the center of the position. So tell me one thing. If I draw a circle, you will try to find the balance where till the time you reach the center. So centroid also works in the similar fashion. But your distribution doesn't mean that every time it will be a circle. Your distribution can also be like this. Then you try to find go there. Our distribution can also be like this. You can go there because here you have more data points, right? So it can be, keep shifting to find the balance. Okay. So that's the point I'm trying to make. Okay. Now, number of groups you can decide. That is also another discussion I will do. But for now, the idea is this. So I'll show one more nice image and you try to understand that what I mean by saying this. You have two types of cluster, right? One is intercluster. You see here, to use white color, intercluster, and here it is intra-cluster. Intra means within cluster. Okay. You know, right? Intra, very famous. Intra-LAN, interland, intercity, intracity. And this is across clusters. So if you see here, within cluster means within a cluster, you want to minimize this distance between each data point. You try to find a cluster in such a way that within that cluster, data points are distance are minimized. That's the objective. And you want to maximize this across cluster distance. Why? So that the separability is highest. So you want to maximize this. I'm writing again, and you want to minimize this within cluster. Here also we'll say within these guys, I'll minimize. So that's the, I would say in a layman term, the beauty of this algorithm. But how will you do it? Okay. So to do that, you have a step-by-step algorithm in place. Okay. Now steps to do. So let me talk in steps. Steps for finding, or maybe I can say k-means algorithm steps. Okay. So there are few steps, guys. Number one, specify number of clusters you want. Specify number of clusters k. So for now, I think starting this is an user input, means you will tell in the model how many clusters you need. Okay. Generally people say 3, 4, right? K equal to 3 or k equal to 4. So this is more like the modeler will give, right, who's building the k-means clustering model. Then second step says initialize centroids by first shuffling the data set and then randomly selecting k data points for the centroids without replacement. Okay, so that can be any weird k centroids, means that's the first one. So you are selecting k data points for centroid without replacement, means you are shuffling the data set, and you are trying to find any random k centroids. Okay. Now in this diagram, if you see, there are 8 data points, 9 data points, sorry, 8 data points, right? The model has randomly selected this as the centroid for cluster 1. Can you see that? And this data point as centroid for cluster 2. I have only taken, two groups, two cluster here. Clear? That's what I mean. So here, this red and green represents the cluster of within the data points. Okay, clear? Now, point number third, what you will do? Now you will assign all the points to the closest centroid. So as of now, all the data points are like, okay, so you will tell me here that, okay, you tell me who is my boss. So how will you find the boss? You will assign all the points to the closest cluster centroids. right? Someone has to go to some boss. Okay. So here idea is that you will find the Euclidean distance, right? And try to assign. Now you tell me this is closer to this one or this one. You tell me. You find the Euclidean distance, the C1, right? So definitely this is not closer. This one is closer, right? So that's why you assign the centroid to the closest point, assign all the points to the closest cluster centroid, and then you realize that you have another image coming as, right? Can you see that? Now I think everybody will be okay with this coming to this guy, right? Except one, I know you might be thinking what's going on there. So this is closer to this. You also know that these guys are closer to this, but we have a doubt that whether this is closer to this or this, right? You can clearly see that it looks closer to this. Okay. But obviously you will not be doing like looking at like who is closer by doing eyeballing. You do a maths, and the maths is that you find Euclidean distance. Okay. So it's not like you are doing just looking at it. So what I'm saying, Anthony, yeah, that's why please pay attention. What we are saying, assign all the points to the closest cluster centroid. The meaning of it, this is my centroid which I have randomly assigned. I was talking about this particular data set, right? Tell me, is it closer to this guy or this guy? There are two centroi, right, for this point. Which one it is closest to? So C1, that's why you have assigned C1. So all these guys have been assigned to C1. All these guys have assigned to C2. Now this guy is a little controversial guy. As of now, it is also assigned to C1, but right, are we going to do something about it? Clear? So now you can clearly see that now the centroid itself doesn't make sense, right? Now this is we have calling centroid, right? But it might be possible that centroid might shift somewhere here. Okay. So once we have formed the clusters, right, you have to, you know, you might have to recompute, and that's where I'm telling it's an iterative process. Recompute the centroids of newly formed clusters. Recompute the centroids of newly formed clusters, and again finding the mean. So this is like using the mean. You have to recalculate this centroid again. So earlier you were just assigning one data point as the centroid. Now you are going to calculate the centroid again. If you look intuitively, guys, if you look intuitively, now you might feel that for the green, I think centroid should come here, somewhere here, right? That's where more balance you will find with this. So this is your cluster one, guys. Can you see that? So centroid might look little bit here and here, right? Depends on how we are getting, and I'll show the image. And for the green one, please pay attention. Green one definitely centroid C2 doesn't make sense. It should come somewhere in the middle, guys. You agree? Everyone here? So if you try looking at, and the algorithm gives you a new centroid, and I was trying to do a more like a by gut feeling, but see, more or less, I was right? So this is the recomputed centroids. It will never come like this when you recomputed centroids. Initial centroids were selected randomly by the algorithm itself. So you read this point. Initialize centroid by first shuffling the data set and then randomly. So it's been random. We are not selecting it. Randomly algorithm picks something. It's written in the first second point. Okay. Then what will happen, guys? Once you have recalculated the centroid, okay, then again, right, then again they're going to repeat it. Means they'll keep moving it around. So they'll keep connecting, again calculating the distance, where it should be, right? If every data point within the cluster is same or not. So that's the exercise it does, okay? That's the exercise it does. It doesn't stop here. It will repeat its step to fine tune the cluster till the time it doesn't find a better cluster. So that's where it will stop doing. Okay. So let me show you one more nice diagram and you will love it, I guess. Now this is how the step looks like, right? So if you don't look at the final one, if you just look at the first one step, right, you will realize that they are first trying to find the clusters. Like this is my, one group. Can you see the blue dots? Hello? So first they thought they will divide like using this plane, right? So two clusters. Everybody please pay attention. Then what if I try dividing like this? So then they divided the data on the basis of similarity again, saying, okay, maybe this can be my two clusters, right? Look at that, how it is changing every time, right? And then it fine tunes. See? So earlier, if you see the cluster points were like this, then the cluster has moved. If you are paying attention, don't look at every steps. Please follow me here. The cluster has moved somewhere here. See? And the blue has moved here. So I think earlier it was here and then it has come here. Guys, can you see that? Somewhere here. Then they realize that what if I move this guy to this completely, right? All these guys are more closer to this. Listen to me. All these guys are more closer to red. So that's why it becomes all red. So the cluster definition has changed. Now what they're doing, they're fine tuning a bit. Can you see that? So now this cluster has to go somewhere center. So that happens in the next. See? So cluster is coming in more center. Then again, this has also come little more in the center. Then they are, trying to do more fine tuning little bit. And then finally becomes your cluster. So one becomes this, right? See, there are only two clusters, but look at the beauty. You might have thought the grouping is being done, right? But see how they evolve to find you the two fine-tuned clusters. So that's why they start randomly. They find the distance, then they update the cluster groups, right? As you can see here, to fine tune, and fine tune. But the steps remain the same. First, they will assign something to as a centroid, calculate the distance, right? And then recompute the centroid, again calculate the all the distance from all data points, distance from the new centroid. If they find that okay, we have to move to some other place, they'll move. Clear? Now I'll talk about some key applications, real life applications. Already I've given one, but maybe I'll just give you few pointers around it. So real life applications of K-means clustering. Okay. So number one, customer profiling, right? Also known as customer segmentation, market segmentation, more or less related to customer segmentation, document classification, right? So different documents can be classified into more 4 or 5 clusters. So document classification, so there they use OCR, which is optical character recognition, to understand the document's nature. And then on the basis of similarity, they group into clusters. Okay. I think there are a few more like geostatistics, understanding the similarity of geologies, or finding astronomy, right? Astronomy is also about finding patterns. So yeah, astronomy is another big area. So where they do all those kind of understanding the planetary positions, and making some conclusions. This is the similarity and patterns, right? Although they also try to predict why, and why can be anything that you can change anytime. Yeah, that's all from my side on this. Maybe I'll talk a little bit more about how to also decide number of clusters, because sometimes people think clusters is like I can always give. It's not like this. What are the cool things about K-means clustering is that you can actually stop uh, going intuitively that how many clusters you need. You can also go by using machine learning concept. You can also find the value of K. So let me give the heading. I'll come back to Imran if I can put the heading. Finding the value of K. You can also find that by using the concept of elbow curve. So let me explain that. So using machine learning only, we find the how many K I should pick. So you can plot the elbow chart. So if you have seen an elbow, right? So this is your hand, but can you see this is known as elbow? Okay. So this elbow chart is just similar, right? Okay. So when you are trying to see that what is your, sum up squared errors, right? And using that, you can see that if you take two clusters or three or four, right? Till the time it keeps adding value to it, you're trying to minimize the error, right? So you will go with more number of clusters. Ideally, you have to find an elbow here in this chart, to be honest. So if you try to fit an elbow here, right, you will realize that wherever the curve for the elbow comes, right, that will be your number of clusters. But how do we decide that? So if you have a sharp decrease, more like a very fast decline in the value of this y, which is WCSS, right? That is mostly your sum of squared errors driven, right? Sum of square error. If it decreases the error drastically, you will keep increasing the number of clusters. The moment it starts getting into a flat line kind of concept, just like this becomes like a flat line, you stop adding more. Because even if you take, tell me one thing, if I take, let's say this is 5 clusters, and if I take 8 clusters, do you see any much difference in the error? Guys, come on. So why do you want to add more clusters to your data? Hello? Does it make sense when I say this, guys? There's no point, right? But if you see, if you take 3 clusters and you take 5 and if you draw a line, can you see that how much error you have reduced, guys? Are you feeling it? And if I say I have taken 2 clusters, right? 2 to you have to anyway take minimum. So 2 to 3, you can also see that you have quite a lot come down. So that's how you can do this. Clear? So testing different number of clusters and measuring the resulting sum of squared errors, which is SSE, and choosing the K value at which an increase will cause a very small decrease in the error sum. An increase will cause a very small decrease in error sum, while a decrease will sharply increase the error sum. So this can be a little confusing language, but that's how it is. So guys, what we are trying to say, please understand, if you go from 5 to 6, so I'll also give you the color coding. If you increase K, increase means what? Increasing K will cause a very small decrease in the error sum, right? If you go from 5 to 6 or 5 to 7, do you see any big decrease in the error sum? No, guys, correct? While a decrease in the K, while a decrease K in K will sharply increase the error sum. So if you go backward from 5 to 4 or 5 to 3, can you see that? Your error sum sharply increase from here to here, guys. Can you see that? Look at this green line. That is the second part of the statement. So in the middle of that, can you see that? In the middle of that, in the middle of this, you find your optimal cluster. Are you feeling this? That's where the language is. That's where you find your optimal number of clusters. So far with me, guys? Clear? This is your optimal number. What is this in this case? 5 is the answer. So you can take it from me. Stopping criteria for K-means clustering. Stopping criteria for K-means clustering. Okay. So there are essentially, 3 stopping criteria that can be used to stop the K-mean. Number 1, centroids of newly formed cluster do not change. So I'm saying that your centroid is fixed, it does not change. Second, your centroids are not changing and your points remain in the same cluster. So nobody is changing the party here. Okay, that can be another one. And third, you can also set a maximum iteration. So suppose your algorithm, you don't want to run it forever. Just like in decision tree, you set, right, how many leaves you want to stop at or how many decision tree you want to stop at in random forest. Likewise, you can do maximum number of iterations. And then you want to say, boss, stop it. I don't care. So in 3 ways, you can stop the K-means clustering. Make sense? Clear? So these are your stopping criteria for K-means clustering. Okay. While we go on and do the hands-on, and let me know once you have the data, guys. Okay, you try loading that data. In the meantime, I'll also get back to you. So I'm also loading the data. So we have those typical import. Let's do it. Import numpy as np, right? Import pandas as pd. Import os. Import matplotlib dot pyplot as plt. Import Seaborn as SNS, right? I might be using a bit of Plotly also in this. So you can import Plotly as py and import plotly.graph objects objs as go. So someone can say hi on Q&A. I can share all these libraries which we are importing. And here you go. Okay, Aryan has shared a big list. Okay, so you should also know, Aryan, which one we're using where, right? Now, let's load the customer data, guys. So df underscore customer, and it's a mall data. So let me read it. What happened? I'm not in this working directory where I am. I'm in, yeah, and data is also there. So what is happening? It was not in the right folder. See, now it came. Okay. This is the data, guys. Can you see that? So you have gender, age, annual income in $1,000, and what is your spending score? Look like a more like a customer profile, right, guys? Agreed? Now to plot scikit-learn we need. So one more you need to build the cluster, and that is import k-means, right? So this is something you should also get it, and then we're good. So guys, first thing first, I'll teach you how to make a basic clustering, right? Basic clustering on 2D. So you can actually use more than two variables. But for now, let's understand age and spending, and then you can go from 2D to 3D, 3D to n variables. That's up to you. First, get a good idea about clustering by looking at this. So you know that the columns are this. Maybe I'm going to pick only age. So I'll say df underscore customer. So I'll select the columns, age and spending. So I'll just say age and spending score. I'll take this guy out and should be good. See, this is my data, guys. Okay. And if you try to plot a scatter plot to understand the distribution, all right, guys, you know how to do it. I don't need to teach, but I'll write plt.figure, or we can use plt.subplots, and then you can write fixed size equal to, let's say 15,7. Yeah, looks good. I think I can give it 15,6, yeah. And maybe I can take 12,6. I'm just trying to get a good shape. plt.show. Okay. And then within this, you have to use plt.scatter. You have to use x equal to age, y equal to spending score. Data, you already know, you have df, and size of the scatter can be 100, right? Age, spending score. Okay, cool, guys. It's really bold. Now better, everyone. So you might think that, okay, my groupings can be, people can think of different types of clusters here. If you are talking about two clusters, you might be thinking, I'll assign this to one, assign these guys to be two, right? Can you think like that, right? Someone can say, okay, Akash, can I do something like this? So how do you do that, right? Means clustering is all about that, right? So I think the first thing first, we need to decide the k value, right? And give some levels to the chart. So First, let me give the levels. So title is, age versus spending score, distribution, plt.x level, and it can be age, plt.y level, and can be spending score. Yeah, see. Now we have to decide the k value. Why we are deciding the k value? So that, we can assign how many clusters we need. For that, I will use the elbow chart. Right, guys? Remember? So remember, elbow chart technique plots the different cost error function. As k increases, average distortion and variance will decrease, right? Cool. And this is some funda, right? The same thing. Now, guys, first need to create the data for elbow. So we'll call elbow df underscore customer, and then I'll pick only two column, which is age, and I'll check spending score, right? This one. Perfect. And now, guys, I want to get only the values. So I'll take, all of it, only the values. This helps you to get the 2D array out of it. Okay. And trust me, you can get the array in multiple ways. See, this is a 2D array. It's the same data. If you see 19, 39, 21, 81, 26. Let me come down and show you. It's the same data, guys. The only thing here is that you are getting a two-dimensional array. Remember, I taught you, so you cannot say no. It's starting with two square braces, ending with two square braces. So it's a 2D array. Are we clear, guys? See, ending with two square braces. It's a 2D array. That's a requirement for the plotting. Then I want to keep an empty list called inertia. So this is an empty list. And now I'm going to go one by one. So I'll say for n in range, I want to go in a range of 1 to 11 so that I can plot as high as 10 clusters. I'll use the algorithm to calculate the elbow, and I'll say k means, and I'll use n underscore cluster that is coming from scikit-learn. I'll put n here, and I'll say init. This is to initialize. K means init means initialize. Remember that oops, might have heard a little bit on oops. Init means initialize. So that's your initialization of the k means. And you want to go till 11. So last is 11. Max iteration, I think, right? I'm putting 300 iterations, which is quite enough. Tolerance is more like how much accuracy you want to maintain, like till where you want to go. 0.001 delta is fine. Random state is 45, again, to set the randomness of the sample. Algorithm is EK, Euclidean, so EKLAN, right? So now this is your algorithm, okay? And then you will fit it to your data, which is your two-dimension array, and then you will append the values you are calculating to this empty list, which is your inertia dot append. You have seen me doing append to a list, and once these values have been calculated, you can keep appending to your inertia. LCAN, not ECLAN. So you will see that inertia has taken your value of the cost, right? Right. And that's where you will also get the cluster. So let me do it. Let me plot the elbow chart. Okay. So again, I will use the same concept of it, plt dot subplots. Maybe why don't we use that, right? Why to waste time? Let's use this now. Now we don't need a scatter here. So I'll say plt dot plot. I need a line chart. And then I will create np dot arrange. Okay. 1 to 11 inertia, and line marker will be O. Okay. This is to just align with the number of clusters. Okay. So this np.arrange, guys, what it does, it creates a value from 1 to 10. Okay. And see, so it gives you like, the value of those data points, right? 1715135, right? Can you see that? 1715135. So are you feeling that you are getting an idea about, hold on, right? You are going to put some kind of this, right? No, 1 to 11 is that, remember, you have created, what is the length of this? Hold on. What is the shape of this? It's a list. So what is the length of this list? You tell me. 10 data points, right? So inertia is just the y-axis. You also need x, right? So that's where I've used this np.rh. So this is your y. This is your x. Line chart, no? So we need to, so that's why I needed an x also, no? Like 1, 2, 3. Now definitely this age will go. It will become your number of clusters and you will start getting to making sense now suddenly. So that is more like your data manipulation to update your x-axis, because inertia just gives you the y-axis, which is your cost. Now you will start seeing a lot of difference, right? And title and I can go, it can be set here, elbow chart for optimal number of clusters, isn't it, guys? Now I also need a line to it. So I'll superimpose plt.plot. And again, it will be same thing, only the marker will change. See, so here marker will be a line this time, and you will see magic. Look at this, right? Isn't it the chart I showed you while I teaching you this, right, guys? Okay. Now, inertia. Okay. So, Indrani asking what is inertia? Inertia is nothing. Inertia is your cost, which is being calculated from this algorithm scikit-learn k-means. So now, if you look at the, let me show you the documentation. Hold on. Right. So if you see here, I've written, init k means, let's understand it. Okay, hold on. See, init means you have more like to initializing the method for your solving. So k means is your algorithm you're using, clear. Init is clear. Right now, what is it? N cluster, how many cluster you want to take? So that's why you're plotting for 1 cluster, 2 cluster, 3 cluster, and what is your cost? Okay, now come back. What is your max iteration? Maximum number of iteration for the k-means algorithm. I talked about it, right? So that's your max iteration. N init is what? Number of times the k-means algorithm will. If I'm running a for loop, for how many times? If it is 1 to 11, it will start from 1 till 10 only to learn. So total how many times I'm running the k-means clustering? For 10 clusters, right? So it will also has to match this, right? That's why I've written the same thing, 11, 11. So this means it will run for 10 times. Okay, and that's where if you see, you will see that I have given number of cluster 10. So it is solving every time, my dear. When you have only 1 cluster, when you have 2 cluster, when you have 3 clusters, every time it will solve and calculate the cost. Model is doing that. I think rest everything you can handle. Simple, clear? Inertia is an outcome of this, right? Inertia is more like your cost. So don't worry too much on it, okay? It's your cost, okay? That's sum of square error if you are trying to divide it into the syntax, okay? Now, once you look at it, guys, you can clearly see that I think ideally you should have minimum 3 clusters, right? See, between 3 and 4, see 4 and 5 same. 3 and 4, you have some delta. I think let's start with k equal to what? K equal to 3. First, we can start with k equal to 3, guys. You agree? That's correct. Very good, Indrani. Got it. Each data point on this elbow chart is 1 iteration with the cost, right? So every time you run it, you get a cost out of it. Let us start with k equal to 3. So again, it's the same algorithm. I'll use k means. 3 means 3 clusters. K means, and then I'll copy everything from right. यहाँ आपको 3 clusters. I think number of iteration can be 3. Maximum is fine. Tolerance is fine. Random state is also fine. Everything is good. Okay. Now you will say algo3 dot fit on your data, which is your elbow, which is your array. Sorry, this is your whatever it is data frame. I think elbow was your array, right? Let me print and see. Yeah, it's an array. And then you can find, so this is your done, model is ready. Labels, 1 you can say algo3 dot labels underscore and centroids. See, centroid will be cluster centers. So guys, you can see that labels will get that, First data point goes to cluster 1. 0 means 1, 1 means 2, and cluster 2 means 3. So there are 3 clusters. That's why it starts from 0, 1, 2. And if you look at the centroids, you will see 3 values. Can you see that? The value of centroid 1, value of centroid 2, and the value of centroid 3. Yes, cool. You have everything to plot the clusters. So I'm going to, guys, now plotting the clusters with centroids. Okay. So again, plt dot subplots fixed size equal to 15,7. Maybe I'll keep it 12,6. The same plt dot scatter. So you already have the data elbow, comma 0, elbow, everything and 1. C can be your color, can be your labels 1, and C map can be bodies. Where it is. Right, and then I also need to plot the centroids. So I'll use centroids colon 0, centroids 1, and you can give the marker like X. Yeah, good observation, Prava. And color equal to red, 200, and bingo, done. See, interesting, guys. Can you see this? Remember the data distribution was looking like this. So this is what you had. And when you try to look at it, guys, can you see it has created a centroid, sorry, cluster like this. Another one is little different, something like this it has done. It's a real data. So you can expect clusters like this. And the other one is this. And the centroid makes a lot of sense, guys. As you can see, center, center, and center. Because of the outliers on this side, it has shifted to us little with this, else it could have been here, right, guys? Agreed? Same story with this one. But see, this is real data, and you have 3 groups of people basis your age and the spending score. So how it is dividing, guys? Those who are spending between 60 to 100 and those whose age is less than, hold on. So the demarcation is like this. Anybody whose age is less than 40 and spending score is 60 is one cluster. And you are saying that I don't care about the age. I only care about the spending score. So anybody who is having 40 to 60, roughly, you have one cluster, right? Another line coming, guys, correct? Hello? You agree? So another line is this one, 40 to 60, and anybody who's spending score is 0 to 30 is another cluster. See, so beautifully it has classified. That is with 3 clusters, right? But if you want more finer cluster, I think you can go with, so I can just see, you have to be very smart. You have to just copy this whole thing and I'll paste it. And now what I'll do, I will say, let's go with 4 clusters. So you have to do nothing. You have to just change here 4, make this guy equal to 4, make this 4 so that you don't overwrite. Let the model solve for 4. Create the level for 4 by calling it 2. See, I'm just repeating the step. You could have written a for loop to do that. Trust me on that. Okay. So let me run it. Ta-da. See. Now you can see there are 4 cluster points. You can just use same data, but you have to use labels as 2, centroids as 2, 2, right? I don't want to see. Now it makes a little more sense that now you have divided this part. Then again, so see, I thought so. Can you see that? So now it has divided like this: 1, 2, 3, and this whole thing is like a 4 cluster. Interesting, guys? And it seems intuitive also, right? So you know that who will be part of your which cluster and how you can target that. That's all from my side, guys. So nothing else on this. You can try to get more in details of it, but I think I'm done from my side on the K-means side. Segments are already there, no? So if you see, we have to just join the data. So you have this data set, right? You have an array here, right? So what you have to do? You have to use label 2 and assign it to the elbow data, right? So maybe let me do it. So you have your elbow data, correct? And you have an array. So you can convert these two into a pandas frame and just, concatenate, right? That to by axis 1, right? So you already have this guy. You know how to convert an array to a pandas data frame, right? So what you can say, df levels for 4 clusters, right? And you can say pd.data frame and your, I think, levels 2 column equal to cluster. Okay, guys, this is my, and now I'll do pd.concat, and I'll say, remember, I have taught you these things, and you have the data df underscore customer, and you also have this guy df levels 4 axis 1, and that will be a combined thing, right? df customer with clusters, right? Correct, Indrani? So you have to do a little bit of data preparation, which I expect you guys to do it. Now you can clearly see that these are your customers in which cluster you are. Now interpretation I did. So while I was drawing this vertical lines, what is the meaning of it? So vertical horizontal line. So anybody who is in the age group of 65 plus and spending score of 60 plus and age group of 40 or so, that's your one group. So you can use this for selling premium products, right? So their spending score is really high. So you can always target this customer for like some premium product, high pricing, high value products, right? Premium means like selling some goods, jewelry item or whatever, XYZ. But if you look at these guys who are part of the bottom one, can you see that? Irrespective of age, their spending score is really less. So you have to give some offers here, and that too on like a low price products, right? LPP, right? So that's the interpretation. So you know that whom you have to target, right? If you don't have this cluster, you might be giving offers to these guys who are anyway premium customers. They keep buying things. They are like people like me who are spendthrift. So you don't need to give them any offer, and you have to position premium products to them, right? And then these are your like mid-level kind of customer. Okay, you got it? So that kind of interpretation comes from the your clustering algorithm.
So let's begin with our very first question, which is what is machine learning and why is it important? Now, as you can see in this diagram, machine learning is a part of artificial intelligence, right? Under machine learning, we have concepts like neural networks and deep learning, right? Machine learning basically consists of dozens of different machine learning methods or algorithms, which we will be covering a few in this particular video throughout our questions. So machine learning is basically teaching computers to learn on their own. Right. So what machine learning basically does is it will show the computer hundreds of pictures of, say, apples and oranges. Okay. So machine learning is basically going to pick these two fruits and show them to the computer. Now what machine learning is doing here is basically it's not telling that apples are going to be red and round. Similarly for oranges, that they're going to be orange in color and they're also going to be round. Instead of giving certain rules, it is going to let the computer figure it out by itself. It is going to go through the hundreds of images and going to figure out a pattern by itself. So this way, whenever a new kind of apple or a new kind of orange is shown to the computer, it is going to be able to figure them out. So this is the basic idea behind machine learning, right? So it basically reduces the repetitive manual work. Like, so say you want to filter out the spam emails, right? So you do not need to do that manually. Rather, machine learning is going to do that for you based on certain keywords. So basically, if an email contains words like free and offer, so keywords like that, so based on that, machine learning is going to help you identify that these emails could be spam. So machine learning reduces repetitive manual work. It helps businesses make data driven decisions. It powers personalized recommendations like Netflix and Amazon. So you guys must have noticed every time you open Netflix, you will be suggested some movie or the other, or some series or the other based on your previous watches. So that is again machine learning behind. It drives innovations like self-driving cars and medical diagnosis. So again, it is not just limited to the basic applications we see like Netflix. In fact, it is seen everywhere like self-driving cars and medical diagnosis as well. So our second question is differentiate between supervised, unsupervised and reinforcement learning. So first let's go to supervised learning. So as you can see over here, we have some raw data, and whatever algorithm we apply, it is going to have labeled data. This is basically supervised learning over here. This is the major point, that we're going to have labeled data. And then we're going to have a prediction. So now let's look at that in detail. So supervised learning, one of the three types of machine learning models, is when the model is given labeled data. That is your input and the correct output. You have it labeled. Your algorithm knows that this is the input I'm getting and this is the output that is supposed to be predicted, right? It is going to learn the relationship between the input output to predict the future results, right? It is used for tasks like say classification and regression. Classification is say your spam or not spam emails, and your regression could be predicting your house prices, right? So basically what supervised learning does is it learns from the examples and it predicts the answers for new unseen data. Right, another example you can consider is we give labeled photos of cats and dogs. Right, we give photos and we label them as cats and dogs. Now it is going to learn to identify animals as either cat or dog in the future pictures. And since we have already told the algorithm when we were giving our data that this is a cat and this is a dog, this makes our data labeled, right? So this is all about supervised learning. Then we have unsupervised learning. Now whenever we give our raw data, it is going to be unlabeled. So this is the major difference between supervised and unsupervised learning. Let's look at it in detail. So basically unsupervised learning is, if you were to consider a real life analogy, a student solving problems without a teacher, right? So it is doing everything on its own. So no answers are provided. The student, or you can say our algorithm, has to find patterns or similarities on its own. So basically unsupervised learning is when the model is given data without labels and must find patterns or groupings on its own. Now in this case, we just have given some random pictures of animals, and now our algorithm, that is our unsupervised learning method, has to figure out on its own which one's a cat, which one's a dog, or maybe it is going to group similar pictures together and then we can identify a pattern between them. So it works like that. So the model basically doesn't know the answers beforehand. It tries to group similar data together, like clustering customers by their buying habits, right? So it is going to find a common pattern between the data and it is going to try and group them together. That is what unsupervised learning basically is. Moving on to a third type of machine learning model, which is reinforcement learning. Now reinforcement learning works like, say you're teaching your pet dog some new tricks. So whenever the dog is going to do something right, or it is going to get the trick right, it is going to get a treat. And if it is not able to perform that particular trick, there will not be any treat, or you can even introduce some sort of penalty. So that is the same way reinforcement learning works. So whatever agent you have, it is going to learn through interacting with the environment, right? So if the agent gets the action right, there's going to be a reward, or there could be a penalty for getting anything wrong, right? So let's look at it in detail. So the model learns through trial and error, train software to make certain desired actions, right? So you can say like a robot who is left out in the open is going to interact with its environment, and through trial and error, it is going to learn what actions lead to rewards and which ones lead to penalties, right? It is going to learn by interacting with the environment. It gets feedback in the form of rewards and penalties. So that is basically how reinforcement learning works. So we have a table over here differentiating the three based on data, goal, and an example. So you can say supervised learning is labeled data, unsupervised has unlabeled data, and reinforcement learning learns by interaction with the environment, right? Then there's the goal. So supervised learning has the basic goal of learning the mapping between the inputs and the outputs. Unsupervised learning finds patterns and groups the similar data, whereas reinforcement learning maximizes the rewards by trial and error. Then we have our example, supervised learning could be classifying emails as spam or not spam. Unsupervised learning could be clustering the customers based on a particular habit or behavior. Then reinforcement learning would be training a robot to walk, right? So moving on to our third question, what is a model in machine learning and how is it used? So a machine learning model is like a recipe, you can say, or a set of rules that basically helps the computers to solve the problems. It's built by learning from data and figuring out the patterns. So basically you have your training data, you extract patterns from the data, and then you use those patterns to predict the results. That is basically how you evaluate whatever you have trained your model on, right? So a machine learning model is, as we discussed, a set of rules or instructions created by learning patterns from the data. It is used to train data to make predictions or decisions, right? So say for example, you're training a student. So when you give that student a textbook, so the student is basically going to study from the textbook and answer the questions based on that, correct? So that is similarly how machine learning models also work. They basically study from the training data that they receive, and then they implement whatever they have learned, whatever patterns they have figured out from the training data set, they implement it on their test data set or whatever new data they receive, and then go ahead with the predictions, right? It is used to understand relationships, classify things, or predict outcomes. So basically there are two steps. First is training the model. The model learns from examples or the data to understand patterns. This is your training data. For example, feeding the model pictures of animals labeled as dog or cat. That is your training data, right? You're giving your algorithm, your model, some sort of data, and you're telling that this particular image is of a dog, this particular image is of a cat. Now it is your duty to understand it, to understand why this is a dog, why this is a cat, and then you test it or you make predictions, right? You are going to show a new picture that the model or your algorithm has not seen previously, and then test it whether the model is able to predict the right answer or not, whether it's a cat or a dog. So that is basically how a model works, right? Moving on to our fourth question, explain overfitting and underfitting with examples. Now let's first look at these diagrams over here. So basically what these dots are your data points, right? You can see all these dots, these are your data points. Now in your first graph, you have a straight line going through the data points, but not really covering or not really touching a lot of them. So this is what is called as underfitted or underfitting, right? Then you have this image over here where your line is basically trying to touch every single data point that is there. This scenario is called overfitted. And then you have your middle image where your line is trying to find a middle path where it doesn't really touch every data point and it does not also exclude all the data points or is not too far away from all the data points, right? So this is called a good fit or a robust fit. This is what we ideally want. And these are the two conditions that you want to avoid. So now let's go ahead and look at them in detail. So overfitting basically happens when your model learns the training data too well. Now, say for example, you are preparing for an exam and whatever materials you have, so instead of understanding the concepts, you try and by heart every single example, every single definition that is given to you in your material. Now, if in the exam you get the exact same questions with the exact same numbers, you are good to go, right? You are going to know every answer because you have by hearted, you have memorized them. But in case you get some unseen questions, that is the time you're going to suffer. So that is basically overfitting. What overfitting is doing here is basically it's trying to memorize each and every data point in your data set, right? So in this case, whenever a new data set is given to your model, it is not going to perform very well, right? It is going to perform very poorly on unseen data. Why? Because it captures all the noise and the irrelevant details. So say for example, you're training a model to classify dogs and cats. If it is overfitted, it is going to learn that cats only have one specific background in the training images. It is going to capture that maybe all the cats are white or some unnecessary detail, right? And whenever you're given, say suppose you give a picture of a white dog, your model is going to classify it as a cat because it has learned or it has memorized that this particular image or this kind of image belongs to a cat. So that is what overfitting means. Then you have your underfitting. This occurs when your model is too simple. Like we saw in this diagram, when you have an underfitted model, your line is not really going to care about the data points as such. It is going to oversimplify the things and fail to capture the underlying patterns in the data, right? As you can see in that diagram, the line is not particularly capturing any sort of patterns. So this leads to again poor performance on both the training data and the new data. Now if we were to consider the example of a student again, so now in this case what the student is doing is he is basically skimming through the pages, just reading the headlines and moving ahead, thinking that he has learned everything about the topic, right? So this is underfitting. Now a model which is meant to classify cats and dogs is going to be underfitted if it predicts every animal as a cat because it hasn't really learned the difference between features of dogs and cats, right? So that is what underfitting means. So here we have a table differentiating overfitting and underfitting. So performance on the training data for overfitting is going to be excellent, whereas for underfitting it is going to be poor. Performance on the testing data is going to be poor for the overfitting models, and for the underfitting model it is also going to be poor. Now as you can see, the underfitting models are going to perform poorly no matter whether it's a training data or a testing data. Why? Because they do not really capture any sort of patterns right from the beginning. So even on the training data, they're not going to perform well. Whereas overfitting is going to do exceptionally well on the training data, but it is going to fail to perform well on the testing data or with whatever new data that is presented to the model. So then we have our model complexity. So overfitting is going to be too complex because as we discussed, overfitted models literally try to learn every single detail of the model or of the data set. So it is going to be way too complex, whereas underfitting is going to be way too simple because they barely capture any details or they barely try to understand any sort of pattern. So the solution is to simplify the model, use regularization or get more data. Whereas in underfitting models, you can use a more complex model or tune the parameters, right? So reading these points, you must have gotten an idea that what is important is a balance between the two to achieve a good or a robust model, right? Your model shouldn't be overfitted or underfitted. That is, it shouldn't be too complex or it shouldn't be too simple. It should be just midway between these two to achieve the best balance, which is also known as the bias variance trade-off, right? You can also mention this point because, let me just write it down. So it is also called the bias variance trade-off, right? So moving on to our next question, what is a confusion matrix and how is it used in evaluating the models? Now, a confusion matrix is basically a table that helps you to evaluate how well a classification model is performing, right? So it compares the model's predictions with the actual outcomes. Basically, whatever predictions your model is going to make, you're going to have some correct values, you're going to have some incorrect values or incorrect predictions. So all that is mapped in a very organized way and shown in a table which is called the confusion matrix, right? So it is useful for understanding the types of mistakes your model is making. So this is what a confusion matrix looks like. You have your actual values, that is, say you have your training data and your testing data. Right. So for your training data, you have your actual values, that is, say you have a column predicting yes and no, right? So it basically goes like this, yes, no, yes, no. Whereas your testing data is going to predict something like yes, yes, no, yes, right? So as you can see over here, this particular prediction is correct over here, whereas all these are wrong, right? This was supposed to be no, this was supposed to be yes, this was supposed to be no. So all this can be mapped in a very organized way, as you can see over here. So our actual values are here and our predicted values are here. So if our actual value was positive and our predicted value is also positive, we call it a true positive. So this is basically a correct value. But if our actual value was positive but our predicted value was negative, we call it a false negative. That means this value is incorrect. But if our actual value was negative and our predicted value was also negative, we call it a true negative. That means it is correct. But if our actual value was negative and our predicted value was positive, we're going to call it a false positive. That means it was incorrect. So this is basically how a confusion matrix maps out all your predicted and actual values to help you analyze how well your model is performing and how much of your predictions are correct and where exactly your model is making mistakes, right? So true positives, we just discussed. The model correctly predicts a positive outcome. False positive is when the model incorrectly predicts something as positive. This is also known as a type 1 error. Then you have your true negative. The model correctly predicts a negative outcome. False positive is when the model misses a positive case and instead predicts it as a negative. So that is called a false negative. Alright. So now that you have understood what is a confusion matrix, let us also see how it is used in evaluating the models. So for evaluating the models, we use terms like accuracy, precision, recall, and the F1 score. Now, accuracy basically means the overall correctness of your model. This is what accuracy is going to test. Precision focuses on how many of the predicted positives are actually positives. Recall focuses on how many of the actual positives are correctly identified. And F1 score is basically a balance between precision and recall. So you can give an overview of how these terms, you can also go ahead and explain the formula for these particular metrics, right? So that was all about the confusion matrix. Let's move on to our sixth question, which is define cross-validation. Now, cross-validation is nothing but a method that is used in machine learning to test how well a model will perform on unseen data. So how is it going to test? It is basically going to split the data into multiple parts. So say you have a data containing 50 rows. So what this cross-validation is going to do is it is going to split the entire data set into say 5 rows each, and it is going to create 10 parts of such 5 rows, right? So it is going to train the model on some parts and test it on the remaining parts. So that is basically how cross-validation works. Now this ensures model performs consistently. So it is going to prevent overfitting, it is going to have a reliable testing, and it is also going to maximize the data usage, right? So as you can see, cross-validation has split this particular data into 5 parts, right? So what cross-validation is doing here is it's going to train the data on these 4 parts and then test it on this 5th part. And it is going to do that until and unless each and every part of it is tested, excluding the remaining 4. As you can see, at the second time, it is going to train the data on these 4 parts and then test it on the 4th part over here. Then it is going to test it on the 3rd part, then on the 2nd part, and then on the 1st part. Basically, it is going to create a combination for all the number of parts that it has created for the particular data set. Now, this is going to ensure that our testing is reliable. So this also prevents overfitting and it maximizes the data usage. Now consider this example where say you're preparing for a spelling bee competition. Now you have a list of 100 words that you need to prepare for. Now instead of testing on the entire list of these 100 words, what you are going to do is you're going to split these 100 words into 10 smaller groups, right? So you're going to have 10 lists, each having 10 words, right? So now you're going to study these 9 groups and then test yourself on the 10th group, right? Now you're going to repeat this process until you have tested yourself on every group. The next time you're going to go ahead and practice on the first 8 and the 10th group and then test yourself on the 9th group. So this is exactly what cross-validation is doing in this case, right? So make sure whenever you go in an interview, you give relevant examples and you are very clear with your explanation so that the interviewer understands that your concepts are clear, right? So moving on to the 7th question, what is the role of precision and recall in evaluating a model? Now let's understand this diagram first. So basically we have our spam emails over here in this section and we have our not spam emails in this section. Simple. Now what our algorithm is doing is, it is predicting all these emails as spam. Now as you can see, the green section is correct because it is correctly identifying these spam emails as spam. Now, but the red section over here is that the not spam emails are also classified as spam. So basically what our recall and precision is doing is, our recall is going to test all our true positive. That means all the correctly predicted spam emails as spam based on our spam emails. So precision basically measures how accurate the model's positive predictions are. So in other words, you can say that all the predictions the model made as positive, how many were actually correct, right? So basically it is going to compare these two sections. Now say for example you have 10 emails in total and 8 of them are actually spam. So in this case our precision is going to be 8 upon 10. Alright. Now let's look at recall. So now recall basically measures how well the model identifies all the actual positives. So it is basically going to compare this entire section, right, as you can see in this image. So out of all the spam emails, how many did the model catch? So say we have 20 spam emails. Alright, and the model actually figured that 8 of them were spam. This is a prediction, right? So our recall is going to be 8 out of 20. This is what the recall is going to measure. So both these metrics work on true positives, false positives and false negatives. So again we will have to use a confusion matrix in order to calculate these. Right, this is the formula for precision: true positives upon true positives plus false positives. Basically trying to predict how many of the predicted positives are correct. Right. Then for recall we have true positives upon true positives plus false negatives. How many actual positives were identified correctly. Right. So a precision and recall basically give the insights beyond the overall accuracy. Now if your model has a very high precision, your model is basically trying to avoid the false alarms. Basically that means very few false positives. Whereas a high recall is going to minimize missed positives, that is very few false negatives. Now these criteria are very important. Let us quickly look why. They are especially important when the cost of errors vary. Now consider a scenario of a medical diagnosis. Now missing a disease, that is a low recall, is going to be worse than a false alarm, right? In cases of medical diagnosis, you're going to prefer that if there is even a slight chance or a slight possibility that a person could have a particular disease, you would prefer a medical diagnosis in that case. Rather, missing that particular disease and hence not going for the medical diagnosis is going to be worse in this particular scenario. Whereas another scenario where you are detecting spam emails, so in case you flag the genuine emails as spam, now say for example you have a very important email and you flag that particular email as spam, which is in the case of low precision, it can be annoying or it can even cost you, say, a missed opportunity. Right? So you need to consider these scenarios in mind and choose which metric, it could be precision or recall, which one you need to be higher in which scenario, right? So moving on to our 8th question, what is the F1 score and how is it calculated? So the F1 score is basically a metric that combines precision and recall into a single number. Now just as we discussed the two scenarios where a high precision or a high recall is going to be beneficial in one case, whereas so the F1 score is basically a metric that combines precision and recall into a single number. So it basically provides a balance between the two, right? Precision and recall. Now, just as we discussed in our previous slide, the medical diagnosis and spam detection situation, where keeping one variable low and the other high is going to be beneficial in one case, whereas it could be harmful in the other. So in cases like this, we need something that is known as the F1 score, which does nothing but provide balance between these two metrics. So the F1 score basically ranges from 0 to 1, where 1 indicates perfect precision and recall. So if you achieve your F1 equal to 1, that means you have a perfect balance between precision and recall. So this is the formula for your F1 score, twice into precision into recall divided by precision plus recall. So F1 score is, like we discussed, very helpful when your precision and recall are in conflict, right? Right. So that is all about F1 score. So moving on to our ninth question, what is the purpose of regularization in machine learning? So regularization is basically a technique that is used to prevent overfitting by adding a penalty to the model's complexity during training. Now it adds this penalty to the loss function during training. Right, this prevents overfitting. Now overfitting occurs when a model performs well on training data but poorly on unseen data, as we already discussed previously. Right, so regularization is going to help the model generalize better on new data. So basically it's a technique that is used to prevent overfitting. That is the main criteria. Now there are two types of regularizations, that is L1 and L2. L1 is called the lasso technique and L2 is called the ridge. So as you can see, without regularization we have an overfitting where our line is trying to touch each and every data point, whereas after regularization we're going to have a better fit where our line is more generalized. It is near all the data points, but it is not really memorizing any data points as such. So the L1 or the lasso regularization is basically when it shrinks some weights to 0. Basically it tries to remove the irrelevant features and it tries to make the model more simpler, right? Whereas the ridge regularization focuses on reducing the large weights. It encourages the model to balance the complexity without exactly eliminating any features, right? So basically regularization reduces overfitting, that is it prevents the model from becoming too complex, right? Or we can say it reduces the complexity, reduces complexity. We've already seen how it simplifies the model. It basically encourages more interpretable weights, right? It improves generalization, that is it makes sure that the model performs well on unseen data as well, right? So the training as well as the testing data is focused over here through generalization. Then we have multicollinearity, that is the high correlation among input features. So say we have two features, that is number of bedrooms and number of bathrooms. So if these two features have a very high correlation, there's going to be a problem in simple models like linear regression, right? So this multicollinearity problem needs to be handled and it can be done through regularization. So these are the benefits of regularization and I hope you guys understood it and will be able to explain it in an interview as well. So moving on to our 10th question, explain the bias variance trade-off. So the bias variance trade-off is basically the balance between two sources of error in machine learning, bias and variance. So we have already discussed underfitting and overfitting. Underfitting, and let me write overfitting over here. Right. So underfitting basically occurs when we have a very high bias, whereas overfitting occurs when we have a very high variance. Right. So now in order to find a balance between underfitting and overfitting, we have something known as the bias variance trade-off. Right. So as bias decreases, variance increases and vice versa. So this is how these two variables are correlated. Alright, let me just clear my screen. Okay, so now the goal is to find a balance where both bias and variance are minimalized for best generalization. Now we do not want any of these terms to have a greater effect on our model. So we're going to have to minimize both of these terms to achieve a better generalization. Right? So as I already told you, if we have a very high bias, our model is going to be too simple that it is going to be underfitted, right? And if we have a high variance, that is, a model is going to be too complex, we're going to have a good accuracy on our training data but a very poor performance on our testing data. So that is what high variance does or overfitting does, right? So consider an example where you're hitting a target. Now if you have a very high bias, your arrows are going to land very far away from the target, but in a very consistent, or you can say systematic error, right? Either they're all going to go, say, towards the right direction. But in case of a high variance, your arrows are going to scatter unpredictably, right? One arrow could go here, one could go here, one could land over here. It is going to be very unpredictable. Some could even hit the target and some could miss it, right? But a well balanced model is going to be a case where all your arrows cluster close to the target, right? So consider a very well balanced model, and in that particular model, all your arrows are going to land somewhere over here, over here, over here, right? All near the target. So this is when both your bias and your variance has been minimized. So that is all about bias variance trade-off. Moving on to our 11th question, what is feature engineering and why is it crucial in machine learning? So you can see in this diagram we have raw data, and then we have something known as feature engineering, and then we come to our ML model. So now what feature engineering is, it's basically involving refining or creating input variables to make them more useful for a machine learning model, right? In order to implement a model on your raw data, you need to have a well refined, or you need to have your input variables that are very useful. So that is done through feature engineering, right? So feature engineering basically involves steps like feature selection, feature transformation, feature creation to improve a machine learning model's performance. So feature selection is where you pick the most important features for your model. So say in a house price prediction model, the area of your house is going to be more relevant than the color of the house, right? Then comes feature transformation. So this involves modifying features to make them more suitable for analysis, such as you can say normalizing your numerical data or encoding your categories, right? So basically you transform your data into a more useful format. Then you have creating input variables or features. So this is basically called feature creation. This is where you create new features from the existing ones. So say for example, you combine the height and weight into a BMI feature or a body mass index, right? So that is called creating your input variables. So the benefits of feature engineering are model accuracy improvement. So by providing the model with the right information, you improve the accuracy of the model, right? Then comes reducing the overfitting or preventing overfitting. This is done by focusing on relevant features, right? So once you reduce the noise or the irrelevant information like color of the house, automatically your overfitting is reduced. Then comes simplifying models. Now, when you eliminate the unnecessary complexity, your model automatically becomes simplified, right? Then your final advantage is highlights the domain knowledge. Now, when you perform feature engineering, it incorporates domain expertise, right? If you have a good domain knowledge, you can make your model much smarter and you can tailor it to the problem, right? So again, feature engineering has a advantage of highlighting your domain knowledge. Moving on to our 12th question, example of when a false positive is more crucial than a false negative and vice versa. So this scenario we have already discussed, but let's look at it in detail. So we know a false positive is when a model predicts something as positive, but it is actually negative. Example, a fire alarm going off when there is no fire, right? Then we have a false negative when a model predicts something as negative, but it is actually positive. So this is missing an actual fire when it occurs, right? So there is a fire, but you missed it. You predicted it as negative, like there's no fire, but in actual there was a fire. Basically, that's what it means. So now that we have covered what is false positive and what is false negative, let's look at an example or a scenario where one is more important than the other. So let's look at the scenario when a false positive is more crucial. So in case of a spam email detection, What a false positive is going to mean is basically you classify a legitimate email, that is an important email, as spam, and now what the consequence is going to be is it is going to get missed by the user. It could be a job offer or a client communication letter, it could be any sort of email, and a false positive is going to mean is that that important email is going to get classified as a spam, right? So this is where a false positive is very crucial. You cannot just blindly mark any email as a spam. Then you have your false negative. So in case of a cancer detection or any say medical diagnosis, right, so a false negative is going to delay the diagnosis and the treatment, which could be life-threatening. We've already discussed. So the model is basically going to fail to detect cancer in an affected person. So this is where a false negative is crucial. Moving on to a 13th question, what does naivety stand for in naive Bayes, right? So naive Bayes is again a machine learning algorithm based on the Bayes theorem. Now this is used for the classification task. Now what the naive stands for in naive Bayes, basically it refers to the assumption that all the input features in your dataset are independent of each other, which is again not true in the real world, right? Now say for a house price prediction model, you cannot have a number of bedrooms and the number of bathrooms, or number of bedrooms and the price feature as independent variables. They cannot be independent of each other because obviously each of these factors are interrelated and are going to affect each other, right? If you have lesser number of bedrooms, your price is definitely going to be affected, right? So it is not true in the real world, but it is an assumption made in machine learning whenever we use naive Bayes, that all the assumptions, that all the input features are independent of each other. So basically this is how the Bayes algorithm works. It basically classifies all, or basically groups the different items into different groups, and this is the formula for the Bayes theorem. So we already saw naive Bayes assumes that changing one feature is not going to affect the others. This is the independence assumption. We have already discussed this. Now this works well with limited data, mainly for one reason, because it does not really need the complex relationships between features, right? So it is again fast and efficient, that is, it makes the computation really efficient. Then again, it is surprisingly accurate, even though in the real world the assumption that the naive Bayes algorithm considers is not true, it is surprisingly accurate in machine learning. So basically, even in the example we discussed, so even when the independence assumption is violated, it will still provide accurate predictions for many tasks, right? So that is one advantage, or one very important characteristic of naive Bayes. Moving on to our 14th question, give an example where the median is better measured than a mean. So now we know mean is basically when you add up all the numbers and divide by the total count, right? So say for example, you want to find the average of 2, 4 and 6. You're going to add 2, 4 and 6, and since the total count of these numbers is 3, we will divide by 3 and our answer is going to be 4. Whereas median is basically finding your middle number when all the numbers are arranged in a particular order, right? They need to be in a descending or an ascending order, and whatever middle number you find is your median. So the median of 2, 4 and 6 is going to be 4. This is the middle value, right? So now when does median outperform mean? Now when do we prefer using a median rather than a mean? So consider a scenario where you have 5 people and you're given their incomes. First is 30k, then you have 35k, 40k, 45k, and then you have 1 million. Now you can notice that these 4 numbers come in a very close range, whereas 1 million lies in a very far range. That is, this particular number is an outlier, right? So if you were to plot these numbers in a graph, 1 million would stand out compared to the rest of the numbers, right? So that is basically what outlier means. So if we were to find the mean of these particular values, we would have a number something like this. This is not accurate, because if we were to find the mean for these particular values or these particular incomes, we wouldn't have such a huge mean, right? our mean has been changed, or it has been influenced because of this particular outlier. So in cases like this, where we have a heavily skewed data, this is when median is more efficient. Now, if we were to find the median for these particular values, it would be 40K, and this would represent the income of these 5 people more accurately, right? So basically, median is not affected by the extreme values or the outliers, as we just saw in this particular example, right? So it gives a more realistic picture whenever data is skewed, like in income or in property prices, right? So whenever you have a high range of your data, you're going to prefer median over mean. Moving on to our 15th question, what are the key differences between bagging and boosting in ensemble methods? So let's understand what is bagging first, right? So bagging basically stands for bootstrap aggregating. Now this creates multiple models by training them on different random subsets of the data. Now each model makes a prediction and their results are averaged for regression or voted on for classification. Now example of bagging is random forest, right? Now in case you're not familiar with ensemble methods, let us quickly discuss ensemble methods. So ensemble methods are basically like building a team, right? Multiple models or players, they all come together to make better predictions. So all these factors coming together basically reduces the errors and increases the stability of the model. So bagging or bootstrap aggregating, let's consider an example to understand it better. So imagine you're dividing your classroom into groups and giving each group a problem. Now whatever answer each group comes up with, you average their answers. Now this method is going to reduce the variance, and it is also going to make the final model more stable. Now random forest is a classic example of bagging. Then we have boosting. Now boosting takes a little bit of different approach. Now models are trained one after the other, with each new model focusing on the errors made by the previous one. So instead of combining the models simultaneously, boosting is going to combine them sequentially. Here each model is going to correct the errors of the previous one. So the boosting algorithm basically corrects the errors or improves the mistakes as the algorithm moves forward. Right? The examples of boosting algorithms are the gradient boosting or the adder boost algorithm. So let's understand boosting by an analogy of real world example where a teacher is helping the students who struggled the most in the last test. So now boosting is going to be a very great way of correcting the bias in weak models, right? So whichever students struggled in the last test are going to be trained separately and help improve their performance in the next exam. So this is exactly how boosting also works. Let's quickly look at the difference between bagging and boosting methods. So bagging basically works in a parallel method where models are trained independently, right? All of the models are being trained at the same time independently. That is, they do not have any sort of connection between each other. Whereas boosting works sequentially. Models depend on each other, where one model corrects the mistakes of the previous model. Bagging focuses on reducing the variance, whereas boosting focuses on reducing the bias. Bagging treats all the data points equally, whereas boosting focuses on correcting the errors only. Bagging is less complex, whereas boosting is more complex due to the dependency. Bagging is good for stable models with high variance, whereas boosting is good for weak models with high bias.
Just a quick info, guys. Intellipaat offers an executive postgraduate certification in AI and machine learning in collaboration with iHub, IIT Roorkee, and Microsoft. This comprehensive course is designed to make you an expert in AI and ML in just 11 months by working on over 50 real-time projects and industry case studies. With this course, we have already helped thousands of professional and successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to a new height. So visit the course page link given below in the description and take a first step towards career growth in the field of AI and ML.